if you so wish. So the first thing to make sure you've all got is Anaconda Navigator, all started up and running. So I'm just going to give you all a minute or so, or 30 seconds or so, to start that up and have it running in the background before I carry on to actually starting the session. Okay, so hopefully you will have Anaconda Navigator started up now and running. It should look something like what I see on my screen here. You might have a slightly different list of apps, or you might have slightly different versions of things, but hopefully it's a similar kind of idea. Now, I said we were going to be using Jupyter Notebooks today. However, I don't want you to immediately click on the Jupyter Notebook launch button. If you do want to use that mode of launching Jupyter Notebooks, it's okay. It's going to work just fine. And if you feel more comfortable there, that's okay. But for the session today, we are going to use Jupyter Lab as the way to start the Jupyter Notebook server. I'm going to explain what these terms mean in a little bit. But if you go ahead on the Jupyter Lab tile, which is probably the first one, and click on the launch button, that should open up in your web browser, one that I prepared earlier, that looks something like this. So I'll just move those to the side so we can see both of them. So click on the Jupyter Lab launch, and that'll open up in your web browser something that looks like this. I'm going to go ahead and make this window here full screen and extra full screen, and the rest of the session we're going to be living inside this window here. So Jupyter Lab is a web-based, I say web-based, it runs entirely on your local computer, but it works in your web browser, even though it's entirely local. And it gives you an environment where you can run Python code, you can write Python code. One of the things it has built into it is its own Jupyter Notebook environment. So the very top icon you should see on your launcher, and if you've been to our previous sessions, you might not be seeing the same view. So just go ahead and you might, for example, have something that looks like this. Just go ahead and close all the tabs at the top. That's perfectly fine. Click on the Python 3 icon under the notebook header, and that will open up a Jupyter Notebook which should fill the whole screen. So having clicked on that Jupyter Notebook Python 3 tile, you should get something that looks something like this. Now this is called a Jupyter Notebook. I'll just give you 30 seconds or 20 seconds or so to get this started up. And again, if any issues, post in the chat. What we have here is a Jupyter Notebook. A Jupyter Notebook is a way of writing and running Python code in an interactive way. And it also provides us with a bunch of extra features which are really useful when we're doing data analysis kinds of tasks. So at the first case, what we can do is we click inside the grey area here and we can type any Python code we like. I'm going to keep it nice and simple. We can print hello. Now, if you just press enter at the end of the line, it just puts another line inside that cell. So it doesn't run the code just by pressing enter. If you want to run this cell, you either click on the plus button just above it up there, or hold down shift and press enter. I'll click the play button this time, but in the course of this session, I'll probably quite regularly be using shift enter or control enter to run the cells. So you will sometimes see me running a cell without clicking it, and that's what's happening there. If I click the play button, it runs that cell and prints hello. It also gives every cell that's been run a number, so you can keep track of which order they've been run in, because in principle it's possible to rerun cells that are further up the page after having run further cells that are further down the page. It can get confusing, and we'll try and cover that later. So I'm just going to switch over to the notes now and copy and paste a few examples from here. So one thing we can do, as I said before, is have code over multiple lines. I'll just show that by typing. So A equals 5, B equals 7, A plus B. If I do shift enter, it runs that cell and displays 12 on the screen. Notice here in this second case, I haven't had to write print A plus B. I didn't need to do this, because the way that Jupyter Notebooks work is whatever the last thing in a cell is will be displayed onto the screen. So here, because A and B has the value 12, it's displayed 12 underneath the cell as the output for that cell. And you see the output and the input have got corresponding numbers. As well as being able to run Python code as we have done in the script so far, it also gives us an extra ability to, didn't mean to make that small, there we go. An extra ability to display output from commands in a slightly more visually pleasing way. Now, don't worry about what this bit of code here does. We're going to be discovering how these things work throughout the session today. I'm just going to make my font a bit bigger. We're going to be discovering how this works throughout the session today. But if you run this, it's going to print something that looks like a nicely presented table of numbers where you hover over it and the lines get highlighted, which is useful when you have larger tables of data. The thing that's really useful, however, is the ability to display plots. So here, again, I'm just copying and pasting this in. We'll be discovering how these things work throughout the course. If I run this cell with Shift-Enter, we get a plot coming up in line. So if you use something like Mathematica, or I think MATLAB can do this, and R notebooks do this too, it lets you run code and get the output from that code right there, and then you can carry on further underneath and, print whatever you want, and you've got the code in line at the point where you ask the figure to be shown. The final thing that it allows you to do is, as well as having cells which contain code, at the top of the window there's a drop-down menu that says code at the moment, and with this cell selected, if I change that to say Markdown, if I click on the Markdown button on the drop-down menu, you see the square brackets at the beginning have disappeared, and now this won't accept Python code and run the Python code. It will instead accept Markdown. Now, Markdown is a way of applying formatting and design to plain text. So you can start headers by doing a hash key, and you can write header. And then if we run that cell, you see it turns the word header into a big word header. You can then double click on it to edit it. You can write bold text and italics, or if I could spell correctly. And you see it formats it with bold and italics. And so what this allows you to do is to interlace with your code blocks of text which describe what your code is doing. And the real powerful thing about this is it gives you the ability to write a whole report with introduction sections, bits explaining your science or whatever it is that you're doing, intersperse that with the code which is executing your analysis, and take that whole report and compile it to something like a PDF and allow you to give that out to people as, this is all the stuff I did and the code's all in there as well. On top of that, it also allows you to give the notebook to other people so that they can take this report you've written and they can run it themselves and see if they can reproduce your outputs. A particularly famous example of this, though it's becoming more and more common these days, was the LIGO collaboration, when they were looking for gravitational waves, published all of their results as Jupyter notebooks, with the data provided alongside them, so that people around the world, citizen scientists, could download these files and run the same analysis that was performed by the people at the LIGO collaboration and see if they could reproduce the science, have a go at tweaking the numbers, playing around with things, and see if they could discover anything in there as well. So it's a really good way of getting engagement with people outside of your local small field and giving them the ability to play around with the code there and then. So there was a question in there that's now looking fine. So yes, there's a question there about the plot not showing up. There's two things. Firstly, it sometimes takes a few seconds for the plot to appear because it's running the code. Secondly, you sometimes have to run the cell twice for a plot to appear. That's supposed to be what this magic little line at the top means, that you don't have to run it more than once. But if your plot doesn't show up, just run that cell again and it should then show up. So to give you all a chance to have a little play around with Jupyter Notebooks, I'm going to scroll down to the bottom of that first page in the documentation. And there's an exercise there, which contains a block of code. So what I'd like you to do, just for a minute or two to get a handle on this stuff, is to copy that code into a few cells in your notebook. And I'll just switch back to the notebook a second. You can add new cells if you click in a cell by clicking the plus button at the top. You can add as many cells as you like by pressing that button there. So I want you to take this block of code, split it over multiple cells, and in between some of those cells, add a little markdown block, which describes just in a few words as a comment what the next little line of code does. I'm going to be going through that on the screen myself just to give you an idea of what that demonstration looks like, and I'll just give you a few minutes to have a play with that yourself. Kunal asks, is there a shortcut for adding cells? Yes, there is. So when you've got a cell selected and the cursor is flashing inside there, if you press escape, you'll see that the cursor has disappeared and it's no longer flashing inside the cell, but the cell is still selected. In this mode here, if you press the A key on your keyboard like this, it puts another cell below where you are. And if you want to add a cell above where you are, you can press the B key on the keyboard, I think. Yes, press the B key and that will add a cell above where you are. How can I go back and rerun? So if you want to, well, you can move up and down with the arrow keys. If you want to rerun all of the cells from the start, if you go to the kernel button at the top, and there is a restart kernel and run all cells button, and that will get everything rerunning from the beginning. So yeah, just take a minute or so now, just have a play with that example, and I'll do the same in my window here. And again, any questions, please do post in the chat, and one of us will be there to help you. Olivia asking, how did I add the text bit? If anyone's happy carrying on, just carry on for the minute while I answer some questions. So, Olivia, if you select a cell so you've got it blue like this, at the top here there's a drop-down menu. By default, code is selected because that's the default cell type. Change that to markdown. And one thing you'll see happen is that the square brackets in front of it disappear. So that's how you know you're in markdown mode and not in code mode. Click inside the cell, and there you can type something like header. So a hash and a space at the beginning of the line makes it a header. 2 stars makes bold, and an underscore makes italic. And if you use the back tick key on your keyboard, which everyone's keyboard's different, but in mine it's in the top left, you can write code block like that. And I'm just going to copy that into another cell so that we've got the example and the real one. So this code here generates something that looks like this underneath. Does that answer your question, Olivia? Great. And Rob, your cells aren't showing the answers after running. So if you could post in the chat there what you've typed into your cell, and then I'll see if I can reproduce it on the screen. Okay, I'll come to you in a second, Kunal. So the first 2 things in the exercise, if I copy those 2 lines there, for example, and I type that into a code cell, if I run that cell there, you're saying you don't see any output. And that's correct, you don't see any output, because in this case here, the last line of code, and I say line in inverted commas, I know you can't see me, but I am, the last line of code in that cell doesn't have a value because it's assigning it to a variable, and the act of assigning something to a variable in Python kind of soaks up the value that you would have been passing in. And so this line of code here doesn't have an output of any kind, it's just performing a side effect. And so you don't get any output from here. If we put in this cell my purchases, and then purchase, there we go, and run that, there we do get an output because that line has a value. And Kunal, how would I tell Jupyter to run several cells together? So, I don't know, let's try something. If I select 2 cells at once, which I can do by clicking on one, holding down Shift and clicking on another. If I press play, it looks like they both run. So you can select a cell, select another cell with Shift Enter or Control Enter I think works, and then press the play button and both of them should run. However, the easiest way to get that to work is to go to kernel at the top, restart kernel and run all cells, and that will run everything. Okay, so a question here about the other things in this drop-down menu. So you see one that says raw. That basically, in the mode where you want to generate a PDF, Jupyter won't do anything to the cell before just putting it in the PDF. So it's just really, really basic and raw. So you never need to use that one. Heading, I don't know what that one does. I'm guessing it's just a shortcut for a markdown cell. The only 2 cell types I ever use is code and markdown. That's all I've ever needed. Okay, so hopefully you've all had a chance to have a little play around with the notebook. It does take some getting used to. I do strongly recommend getting used to using some of the keyboard shortcuts. So it's going to make your life a lot easier if you keep your hands on the keyboard rather than moving around. So for example, I'm in this cell here. I can press Escape to deselect the cursor, press up on the keyboard, and then press Enter, and then now I'm typing into the cell above. If I press Escape there and press B, I'm now in the cell below. I can press Enter and then type A equals 7, for example. I can run that with Shift Enter, and then I can move down to the bottom cell here and then run that cell again, for example. I've done all of that without touching the mouse at all, and that's going to make your life easier as you become more accustomed to using Jupyter notebooks. Okay, so moving on to the next section here. First thing we're going to do is, in the notes, at the bottom of every page there's a next button. Go ahead and click on that next button now. And in general, Christopher will probably be posting into the chat the link to the current page we're on. But in general, you should be able to just follow through in the order I'm going. I think Christopher might be helping someone with a question at the moment. So, introduction to pandas. So this course is about data analysis in Python because it's a very, very common thing that people in all walks of the university have some kind of data they want to analyze. Maybe it's in a spreadsheet, maybe it's in a text file, maybe it's downloading from a website. Often what they want to do is ask a few questions about it, for example, to select a subset of the data or to merge it with another form of data, and often to plot a graph at the end. A lot of science comes down to a bit of analysis and plotting a graph, as I'm sure you're all aware. So the idea of this course was to get people to the point where they can do that set of tasks without having to do sort of too much complicated things. We want to kind of find a critical path to getting the solution done. So in Pandas, the primary tool that provides these features that you need to do those things is a tool called Pandas. Now, Pandas is a third-party module. It's not core Python. It's written by people around the world, writing stuff in their own free time, written by people like you and me. But it's included by default in Anaconda, which is one of the reasons we use it. But the reason it's included by default in Anaconda is because it's by far one of the most popular Python packages out there. It provides a couple of basic pieces of functionality. The first of which is a series, which is what we're going to be covering first. And the second is a data frame, which we'll come on to in a little bit. But to get a little sense from people in the room, could you let me know if you've ever used Pandas before? Or if you've ever done anything with Pandas or just had to work on code which has used Pandas before? So we're seeing a few people with yes, a few people with no. Okay, good. So lots of people have never used it before. You're the perfect target audience. However, those who have used it before, hopefully will go through some things which will clarify stuff, explain how stuff works underneath. And again, if there's anything that you're really comfortable with, feel free to move through a little bit faster or ask questions about how you can do other things about it in the chat. Yeah, so a few people have used it. Most people haven't. Wonderful. As I said, Pandas provides a few different tools. The first of which is the series. Now, a series in Python, in Pandas, you can access by importing it from the Pandas module. So I'm going to start a new notebook, and I'm going to do that by clicking on the plus button up in the top left where it says New Launcher, and I'm going to select a Jupyter Python 3 notebook. I'm going to save and close the old one because we don't need that one anymore, and I'm also going to rename the notebook by right-clicking on the tab at the top, select Rename Notebook, and I'm going to call this Pandas. Giving your notebooks a sensible name is a good idea because just having everything called Untitled 1 and 2 and 3 isn't going to make your life very easy. So we start off by from Pandas import series. So from the Pandas module, we're importing the class series. I run that with Shift Enter, think about it for a moment, and we've got access to a series. I'm going to copy this line of that list because otherwise I'll get a different set of numbers to you. So the way that you create a series in Pandas is by calling the series class like a function, and you can provide any list of data to the series object because at its core the series is kind of like a Python list. It works in a very similar way superficially, and we're going to be investigating some of the differences shortly. So the easiest way to make a series is to give it a list of numbers. So here inside the round brackets, I've given it a list of numbers with the square brackets. These are all integers in this situation. If I run that cell, it's going to, because I haven't assigned it to a variable, it's going to display the value of that object. And this is a view we're going to have to get very used to seeing. We're going to be seeing a lot of series, or whatever the plural is. So I'm going to explain now what the things on this screen mean and what we should be paying attention to when we see them. Now, the first thing you hopefully notice is that this line of numbers on the right-hand side are the same numbers and in the same order than those we passed in the list at the top. 14, 7, 3, minus 7, and 8. So the first thing to notice is that series has maintained the order that we pass things in, and that makes sense because you'd hope that a series is serial and maintains ordering. The next thing to look at is on the left-hand side, we have the numbers 0, 1, 2, 3, 4. These are the index. You can think of these as being the row number or the row label, because we'll see in a while that the row label can be strings as well as being integers. Because we haven't told it what labels we want to apply, it's automatically generated the numbers starting from 0, because remember that Python always starts counting from 0. The final thing to be aware of is the D type. D type means data type. In this case, it is an int 64. Int means integer. 64 means it's a 64-bit integer. 64-bit integers can get very large. They can get as large as 2 to the power of 64. So the largest integer you can have inside this thing is pretty much that big. Except actually it's only that big because it goes positive and negative. So you can hold very, very large numbers inside here by default. The reason that it tells us what the type is here is because Pandas is going to use the type of the data to perform certain optimizations as it does stuff, which is useful when we're dealing with millions of numbers and we want to do mathematical things to them. It's going to do it nice and fast. As I said, here we didn't specify an index, so it generated one for us. We can go ahead and give an index to it. Index equals, so as a second argument to series, we pass a list of, well, whatever you want. But here I'm going to use a couple of strings, single character strings, but strings nonetheless. And when we run that, we see printed out on the screen the same numbers as before, but here we have a set of indices. Just take 30 seconds or so now just to have a go at making sure you can import pandas, you can generate these series, and I'll be back in a moment to carry on to the next section. Okay, got a question there in the chat from Dan. Is it impossible to index from a sliced range? Okay, so you're asking, for example, if you wanted to do something like, you wanted to have the numbers, something like 1 to 6 in there. That's fake syntax, that won't work. So if you wanted to do something like that, you should be able to use the range syntax and do 5, 10, and that will give us, nope, am I missing a bracket? Oh, because it's a comma, not a colon. There we go. So in the index there, I passed in the range function, and so it started from 5 and gone through to 1 less than 10. Is that what you meant, Dan? Great. And Adam, is there a shorthand for copying a previous line? Yes, there is. So if you've got a cell selected, you press escape so that your cursor's not in there. I think if you press Y and then P, Y and then P. Nope, someone said there's a help if you need it. Edit. Copy is C, paste is V. Okay, so you select it, you press C, and then you press V. There we go. So C to copy, just pressing the C key by itself, and then V to paste. And you can delete a cell with pressing D twice. I'm not expecting you to remember all of these. There is a way to get the keyboard shortcuts, but I can't remember how you do it It's probably in there somewhere. If anyone can see how to get the Jupyter Notebook help up, then that would be great. Okay. So let's go ahead and actually do something with these things. So I'm going to go back to, actually, which one? I'm going to try and keep up with what I've got in the notes. I'm going to go back to this cell here. So I'm going to delete these other cells. So we have here a series. I'm going to assign that to a variable s because I'm unimaginative. And see, this time, because we've assigned it to a variable, it hasn't printed anything out. But we can have a look by writing s, and then it shows up on the screen. Escape and B to do another cell, or press the plus button there. So we want to ask something of it. I said that series are like lists, and they are like lists in many ways. One of which is that you can use square brackets to select items out of them. And in this way, they're actually starting to act a little bit more like dictionaries, because we don't put a number in here per se, although you can if your indices are number. You put in here the row label that you want to select. So in this case here, because we labelled them A, B, C, D, and E as strings, we can pass in here C. We run that, and it gives us back C is the third item, C is the third item, so C gives us what happens to be number 3. If we do it with A, we get 14. So it gives us back the value from the list, from the series, sorry. If you're used to R and their pandas, their data frames and so on, they would give you back a list with one item in, which is 14. However, pandas just gives you back the number itself. So it's saying that the value from this list associated with the value A is 14. We're going to see later on some more advanced things that you can put inside these square brackets. But if you just put a single item by itself, it's going to look up that row, find the index label that matches it, and return it back to you. You can also edit in the same way. So we can do S and we can edit, let's edit E, and we can set the value to be something else. So we can say this should be minus 999. Run that, it's done it. New cell S, and we see that E has been updated and changed. So there's 3 exercises after this bit here. Don't necessarily worry about doing all of them. In general, there's a few more exercises than you really need. They're just there to stretch you if you're interested. Just take a minute or two to have a go at those, and then I'll move on to the next bit. Right, it's a question there from Adam in the chat. So compared to MATLAB, this is basically a way of storing data, but can we add in strings as well? You absolutely can. So in the examples here, I've been having integers as my types here. If I take my series example and make a bit of space and do it here, you can absolutely put this is a word, and actually let's run it without the S at the beginning, and you see we've got some data here, which is this is a word. So you can put any kind of data in here at all. You'll notice this time the D type has changed to object. That's its sort of generic, I don't know anything more than it's some kind of object. That means that you're losing the ability to have efficiency and speed when you're dealing with these things. So if you wanted to do mathematical operations to this series, it would become slower than it would be if they were all integers, for example. In general, it's a good idea for each series to have one kind of data, so have these all as strings or all as integers or all as floats, but it is possible to mix them together. Suddenly my shortcuts stopped working, so if your shortcuts won't work if your cursor is flashing there. So if you want to, for example, copy or do a cell underneath, make sure you pressed escape so that the blue outline around the cell disappears and it's just grey and there's no flashing cursor there anymore. That means that when you do something like A to do a cell above, it works correctly. So give that a go and see if that helps. And I'll delete that cell. So from those exercises we've just been going through there's a question there about how does a pandas series differ from a list or dictionary? And while these ones above are just having a play around and having a go with these things yourself, I'll answer this question about how a series differs from a dictionary and a list. I wanted to point these out because it's useful to have an understanding. Because one of the things you need to get used to in programming is choosing the right kind of container for the data you're dealing with. And so knowing how they compare against each other is a useful first step along that. So they're like dictionaries because you can just access by any kind of key. But importantly, series are ordered where dictionaries aren't. We'll see later on that series can have repeated indices. So while you can't have a dictionary with the same key repeated, you can have that in a series. It's generally not a good idea, but sometimes it does make sense, so be aware of that. And series are sped up and made fast by using NumPy or NumPy behind the scenes. A list, again, they're in order, and you can index by integer in principle. But a series lets you access stuff by key, as we saw, and again, it's made faster. So on the whole, it takes the best bits from both and makes it faster, but there are some situations where you don't want something quite as difficult to interact with as a series. It's not built into Python, for example. So, series operations. Let's have a look at an example, and I'm going to be asking for some audience participation in a moment. So here we have a list. If we wanted to double all of the items inside that list, let's do something like my list times 2. Now, could you post in the chat there and let me know what's going to happen when I do the list multiplied by 2? Is it going to double all of the numbers? And you can cheat by trying it yourself. Yeah, okay, good. Lots of people saying yes. Let's see what happens. Oh, that's weird, isn't it? So because this is a built-in Python list and not a series, it isn't making the assumption about it being numerical data. A Python list is just designed as a container for information. So what it's actually done is it's taken our list, 368,410, 368,410, and it has doubled it. And it's doubled it in the most literally minded way you can imagine. It has just repeated itself again. If we wanted to double every item in the list, we'd have to manually loop over it, put the doubled items into a new list, and that takes some time. And takes some lines of code as well. With only 5 items, you're not really going to notice any slowdown. But if you have 1 million items, putting it in a Python list and looping over it is going to be slow. So let's take this same list and let's make a series called S. In fact, let's call it S1. Let's have this different name from before. And so we're taking our list, we're converting it into a series and giving it a name. S1 now looks like this. So it's those same numbers, but it's a pandas series. If we multiply that by 2, it's done the correct thing. So it hasn't duplicated the list, it has applied this operation to each item in the list. And because it knows that they are integers, it is able to do this in a very, very fast and efficient way. Right, so the code will go green. Yeah, so while it's running, it goes green apparently. So that's the difference between the two, David. So this allows you to run this numerical operation on everything inside this list. Now, this is useful if you've got numbers inside there and you want to be able to double them or find averages or things like this. But as well as doing numerical operations like times 2, or we could do minus 2, that works too. So 3 has become 1, 6 has become 4, etc. We can also do Boolean operations, so logical questions about our data. So instead of doing a mathematical operation which changes the numbers, we can ask questions which are going to give us back true or false answers. So for example, we can say, is S1, I'm going to change this cell here just to be S1, so we've got a reference, is S1 greater than 6? And we run that, and it gives us back the answer, but it's giving us back the answer for every single row. It might look like we're asking the question of, is this whole series bigger than 6? But actually what this ends up meaning, I'll just scroll down a little bit, what this ends up meaning is for each item in the list, ask each of them, are they greater than 6? So 3 is not greater than 6, 6 is not greater than 6, 8 is, 4 isn't, 10 is. And so it gives us back this list of trues and falses. There's a question there from Olivia. So this means in lists I can only do these kinds of operations through looping. Realistically, yes, there are ways to make it look like you're not looping, but you are always looping. So what this has given us here is ability to ask these questions and get back trues and falses. You see that the D type has changed to bool for Boolean. We'll see in a moment how we can actually use these ourselves, but have a quick go now, just to have a play with the series, try doing multiplications on them and try doing greater thans, try less thans, or equals tos, and things like this, and see what works, and see if you can get stuff to give you output that you expect. And I'll be back in a few minutes to move on to the next bit. Jeanne's asking, how do you get just the numbers from the series? So you want to get not all of the stuff around it, you just want to get the values, and you can get that by writing dot values. And that gives you back the array with just the values out of there. Okay, great. So a few good conversations happening in the chat there. So Bo's asking, is NumPy faster than Pandas or not? So Pandas, as Christopher says, uses NumPy behind the scenes. Everything underlying it is NumPy, and it's just using Pandas as a way of giving a nice interface on top. Yeah, as Christopher says, always one step ahead of me is he. I'm going to go, again, I'm going to just make some more space underneath, and I'm going to come back to our S thing from before. I'm going to change S so that the last item in it, actually no, I'm going to redefine it so that it's the example from before. There we go. So, S, A, B, C, D, E, and the numbers. I showed you before that with an S you can do something, oh dear, you can do something like S is greater than, let's say greater than 4. And it gives us back some trues and falses. Now that's useful as a first step. It gives you something which, if you look at with your human eyes, you can see that there are trues and falses, and so you could kind of try and cross-check, and you could say, okay, so which items are greater than 4? A is true, B is true, and E is true. Okay, so that, and that have passed my test. Okay, that's good. However, we are lazy because we are programmers. The best programmers are always the laziest programmers because we make the computer do the work for us. We shouldn't have to do this manually because software is there to automate our lives. So making another cell below, I'm going to take this S greater than 4 thing, and I'm going to kind of double things up. I said before that when you write S and you put brackets in it, you can put inside here something like A. The spaces here are just for clarification in a moment. The S's here are to, the A here is going to select row A from S. So I said if you put a single item in here, it's going to give you back that single item. However, there is a special shortcut mode that if you put inside these square brackets something that is a list of trues and falses, or more specifically a series of trues and falses, it will use that series of trues and falses as a mask. And anywhere where there is a false, it will not show the data. And anywhere where there's a true, it will show the data. So here we can paste in our S greater than 4. So S greater than 4 is inside those square brackets. And when we run that, it gives us back just the things that passed the question. Now this here is obviously a simple example. It's just asking a small question about your data, is it greater than 4? But you can ask more complicated things. You can say, if S is multiplied by 2, is it still greater than 4? And here we see that we've got extra data has come through. Now while C, i.e. 3, isn't greater than 4 itself, if you double 3 to 6, 6 is greater than 4, and so it passes the test. And so you can put relatively complex questions inside your square brackets here, and that's going to give you the ability to filter down your data and discover the things from it that you really, really want. Hopefully throughout the session today we'll be seeing more examples of this, but at this point I want you all to have a go at doing that yourself. Have a play with the putting different numbers in here, try making different series yourself, and see that you can reproduce this and make sure you understand how it works. If any of you have any questions about what this does, how it works, or what kind of extent you can take it to, please do have a chat with us in the chat there. And apart from that, I'll be jumping back in again in a minute or so. Okay, so hopefully you've all had a chance to have a little play around with querying your data like this. There are other ways of querying data in Pandas. We'll be seeing how they interact with larger forms of data in a short while, but there are also other techniques out there. I do recommend having a look through the pandas documentation after this session. Some of it is very technical and dense, but some of it is written for relative beginners, so you should be able to get some useful information out of it as well. I'll point you towards it towards the end of the session. So the last thing I wanted to cover on series, which is going to be useful later on, is how you can do things between two series. So here I've defined two more. I've got S2 and S3. One's got largish numbers in it, and the other one's got smallish numbers in it. As before, we saw that we can do S2 minus 5. That subtracts 5 from all of the values inside S2. So 23 goes to 18, for example. But if you've got two series which are the same length, you can do S2 minus S3. And it will subtract the corresponding elements from the two of them. So it does 23 minus 7 is 16, 5 minus 6 is minus 1, and so on and so on. And again, it does this very quickly. It will, even if you've got like a million items inside here, it will be able to subtract one from the other in a fraction of a second. So you generally don't have to worry about the speed, as long as your D types are showing up correctly as int64, and as long as these are a similar size thing, this is always going to be a nice fast operation. You don't generally have to worry about that. If you do get to the point of having to worry about your data being far too big, we'll give you some information at the end of the session to come and talk to us about how you can get help after the session. So moving right down to the bottom of this, what was the title of this page? Was Introduction to Pandas. Moving right down to the bottom of that page, there is a final exercise here, which I will just go through with you. So create two series of equal length with no specified index and containing any values you like. Perform some mathematical operations on them. That's what we've just done there. Now, what happens if they've got different lengths? Let's have a look. So let's make S3 shorter. So S2 we've got 5 elements in, S3's now only got 4. If you subtract one from the other, I didn't run that cell again. Classic thing that happens if you change a cell but don't run it, then the values that are set inside it don't get updated. So you have to make sure you always run a cell after having edited it. So here we see that S2 minus S3 is done 23 minus 7, again, 16. 5 minus 6, minus 1. All the way down till it's got to 7 take away 4 is 3. Then it's trying to do 5 take away, well, there's nothing there. And it's important to be aware of the difference between 5 take away 0 and 5 take away... And at that point I just paused, because there's nothing to subtract from it. There's no definition of what you, if you do 5 take away something that just doesn't exist, what the answer should be. It's not 5, it's not infinity, it's not anything. So to handle this situation, pandas and generally most Python and other programming languages have a type called nan, which stands for not a number. And so any situation where you do something that represents something that isn't a valid number will put a nan in its place. Now nans are viral, so if you do nan times 3, that's going to be a nan. If you do 5 minus nan, that's going to be a nan. So nans become sticky and they hang around. Another good question in there from Anna. Why are they floats now? So I was about to come on to that, but I'm glad you pointed it out. So 23 minus 7, integer. We've clarified they're integers from before. But now for sometimes it's 16.0. And for the pure mathematically inclined out there, you might think that 16 and 16.0 might be technically different things, and they are in programming languages. The reason it's had to do 0.0 here and turn them into floats, and you see it's a float 64, is because the whole column of values has to be of the same data type, and there is no way to represent nan inside the integers. Integers go from minus a big number to positive a big number, and there's no bits of information left over to represent nan. Floats, however, do have a special little set of bits built into them which represent nan. So as soon as your column gets nans involved, your numbers are going to turn into floating point numbers. Now, some of you might not be seeing floating point numbers here because this is one of the things that's changed with the recent release of Pandas 1.0. It's now a little bit different, and you can have integers with nans because they do something a bit cleverer. So in the future, this might not be happening, but it's worth being aware of. Okay, good. So with that, we are going to move on to the next section. At the bottom of that page, there is a next button. And we are on to data frames. Now the term data frame, as far as I'm aware, was stolen from the R programming language, either from the language itself or from one of the packages, I'm not actually entirely sure. At its core, you can think of a data frame as a table of data. So a series is a one-dimensional list. It is something which just goes along in one direction. They are originally technically designed, I suppose, for use as time series. So in our examples before, we had indices which were numbers, automatically generated 0, 1, 2, 3, or A, B, C, D. But you can have an index being a complicated value, like a timestamp. So a series might be used, for example, to store all of the samples from an experiment. Maybe that's all of the temperatures throughout a day, or all of the atmospheric concentrations of CO2 throughout a year. That's a one-dimensional set where there is a one piece of information, but repeated. And each piece of information, each row, has a label saying when it was collected. So that's what a series is. A data frame is a table of data. And so where you can think of a series as being a column, a data frame is a set of columns all connected together. At its core, a data frame is made up of a bunch of series put next to each other, making up a table. That's what they do. And as soon as you start operating on data frames, start asking questions from them, you are going to start getting back series. And this is why we've started with the simpler series type, because very quickly data frames devolve into a series, and that's how you start operating upon them. So we'll start by importing this, and I'm actually going to start a new notebook. I'm going to save the old one, but I'll leave it open. I'm going to start a new notebook, and I'm going to call this one data frames. And we start by from pandas import data frame. Now there's a question in the chat about how often do you have to do this import. Generally you do it once at the very top of your notebook, and then it persists for the rest of that session. This next bit I am going to copy and paste, because there's no way you want to sit here and watch me type out all of this. That would be very boring for everyone involved, and I would absolutely definitely make a mistake. So this is just a plain old Python dictionary. Each key is a string, and each value is a list of items. Each of these three lists are the same length. The way this is going to work is each key is going to be used as the label for a column, and each value is going to be used for the values in that column. So we go ahead and run that. Now, at the moment, that's just a plain old dictionary. If you want to turn it into a data frame, we should go ahead and use the, if I could spell, data frame class, which we've just imported at the top, and we pass it our data in the same way we passed our series, our list, to the series. There's a convention to name your data frame df, and that's a bad idea because it doesn't describe it, so I'm going to rename this to census. I think that's how you spell census. Then in the cell below, I am going to print it out, census. You're going to see me lots of typos in this session. There we go. Just going to make sure I've got my chat window open. Good. So you can see here, we've got a table. We hover over it and we see all the lines showing up nicely. So I didn't mean to scroll there. We've got three columns because we had three items inside our dictionary: city, year, and pop. City, year, and pop. In the city column, we had Paris, 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 and then 4 Londons and then 4 Romes. We see the same thing here. So it's maintaining the order of the data. At this point, we don't care about our dictionary anymore, so I'm actually just going to scroll down to the bit that matters. We've taken our data, we've printed it out. You can think of each of these columns as being a series, and you'll see there are 3 columns, so there are effectively 3 series being involved here. If you remember before, every series had its own index. The way that a data frame works is it combines all the indices from the parts together and gives one overall index all the way down the left-hand side. And now, because we haven't specified an index, it's assigned one for us. Again, the integers displaying from 0. So I'm just going to give you a few seconds now just to copy and paste and run that code yourself. Make sure you can import the module. Make sure you do this line here. And make sure you can get to the point where you've got a table displaying in your code. So give you a little bit of time there just to have a go at that, and then I'll jump back in. Okay, so I'm not seeing anyone shouting for help in the chat, so I'm going to assume that on the whole things are working well. And again, if I'm going too fast or too slow, please do say something. So there's a few things that we can do with these data frames. First of all, you see this data frame here already fills up most of my screen. I do have my font size set quite big, but it fills up most of my screen. In the case that you've got hundreds or thousands or millions of rows, this isn't going to be tenable. So one thing you'll often want to do is just have a little peek at the first few rows of your table, just to kind of get a sense of how it's looking. And we can do that by writing census.head, and then you give a number of how many items you want from the head of the table. In this case, maybe 3, and you see it prints out the first 3 items. Similarly, you can do, tail, head and tail, beginning and end. These are quite common terms in programming languages, so you'll see these cropping up a few times. The other thing that we want to be able to do, and it's going to lead into some of the really powerful stuff we're going to be doing throughout this session, is grabbing data out of our table. So we start with our census. With our series, when we put stuff in square brackets, if you remember, it would select by row. So you might think you put census 1 and it would give us out this row here. But actually, the way that data frames work is that they select by column first. So in here, we have to write something like city. That will give us back the city column. So to reiterate that, a series selects by row, a data frame selects by column. That's half true, and I'll explain exactly how this can get more messy in the future. If you'll remember that we selected by row in our series, but we could also put in those questions with the trues, falses, and that worked too. And we'll see things like that carrying on being the case. But on the whole, if you just put a single item in, it's going to look for a column by that name. And if we look for something which is not there, it will give us a big scary red error, which if you scroll down says key error not there. That's it saying there's nothing by that name. So let's go back to city. This has given us back a series, exactly of the type we were dealing with before. The only extra thing it's got is now it's got a name. It says name city, and so we can remember which column it came from. We can check the type of it by wrapping the type function around it, and we see that it really is a pandas core series object. So that means we know exactly how to deal with it. So let's start through that again. Census, square brackets, city. So we could say something like, I want to select all of the rows where the city is Paris, because those are the census informations that I want to do my subset of my analysis on. Because this is a series, we remember before that Boolean operations on series give us back a list of Booleans. We expect to get the same thing. And we do indeed get a list of trues and falses, where the trues are the rows where it was Paris and the falses are elsewhere. Now, as before, we can take anything that's a list of trues and falses with associated indices, an object like this, and like before we passed it into S, in this case we can pass it into census. And inside those square brackets, I'm going to copy and paste this thing here. And the reason I put those spaces around it is because the proliferation of square brackets can get confusing. So these outside square brackets are asking a question of census, and so they're going to give us a subset of census. These inside square brackets here are selecting the column on which we're asking this question. So this here is a list of trues and falses. It's going to mask and select down just the rows from the census table, the thing up above, which match this question. And so when we run this, we get back just these items here, which match Paris. Have a little go at that yourself, make sure that's working, and then I'll carry on to the next bit. So we selected here census, and to select a column out of it, we just put something in the square brackets. it's quite common that you actually want to select by the row index. And so to do that, you do .lock, which stands for location. Not the best name I know, but it does work. And if you put the number 3 in there, it's going to give us back the row that matches the index 3. So it gives us back Paris 2010 2.244. So this is a way that you can get rows of data out of your pandas data frames. But the reason it's made a little bit more difficult than getting the column out is due to the way that the stuff's laid out in memory, effectively. It has to ask more and more difficult questions and do more work in order to extract a row than it does to extract the column. You can think columns are pre-prepared, but rows it has to go and find the data and reassemble it into a series. So getting rows out is possible. It is slightly slower. So it wasn't slow, but it was slightly slower, and that's why they make it a little bit more difficult to get access to. We can also add new columns. So here we have census, and we have a look at that table. It looks like this. So we can add a new column to it. For example, a column called continental. Again, spelling catching me out. And we can assign a value to it. So this is going to make a new column with that name. And so the value we assign to it needs to be a list of numbers to fill the column with. The easiest way to get a list of values to fill the column with is to generate one from one of the other columns. So for example, let's put some spaces there to make it clear what's going on. df city is not equal to London. So this is going to ask of the city column where it is not equal to London. That's going to give us back a list of trues and falses. We're going to take that list of trues and falses and make a new column out of it. It's not called df, is it? It's called census. Thank you. There we go. So now we look underneath and we print the census table, and there's now a new column here which has got our information in it. And we could then use this in queries as we go forwards. To delete that, we can use the del keyword, which is valid Python in many contexts, but is very uncommonly used. And you can delete a column, such that when we then look at it again, census, it is now gone. So you can add and delete columns at will. Have a go at the exercise at the bottom of the data frames chapter. So do this same thing that I've just been doing there. Have a go at selecting some data out of it, and then see if you can find all of the cities which have a population smaller than 2.6 million. At this point, I should point out that I've done a very, very bad scientist thing, and I've got a column here with numbers in, and I never told you what units they are in. I assume you can work out they're not individuals because you can't have 2.148 of a person. They are in fact in millions. So when it says smaller than 2.6 million, it's asking for a value that's smaller than 2.6. Have a go at those for a few minutes, and then I'll update everyone before we jump onto the break. So I want to go through the answer to one of the exercises there. So the bottom of this page, this middle exercise here, select the data for the year 2001. We'll see how to do that first. Then the question, which city had the smallest population that year? Now, to answer the second part of the question, does require a function that you haven't been taught yet. So I'm going to teach it to you now and show how we can do this and build it up stage by stage. As Crystal was saying in the chat, the best way to solve these things is to start small, do one small bit at a time, and slowly build up your line. Because even a line of code like this one can be a little bit hard to parse when you're first looking at it. So either build it up part by part, or give temporary variable names to each step and then use those variable names in later steps. But let's get to the exercise. We have, let's make sure I've got my thing here. So we have df year. That is, oh no, it's census, isn't it? Teach me for reading off my notes. Census year. These are all the years. The first thing we want to do is grab all the stuff for the year 2001. We can do that by selecting where the year is equal to 2001, trues and falses. So let's pass that back into the census dictionary, census data frame. So this is going to give us back all the bits from census where the census year column is equal to 2001. There we go. We've reduced our data down. Now, the question in the exercise was, which city had the smallest population that year? So if you just looked at this and said Paris by reading the numbers, that's a successful way to answer the question. I can't fault you for doing it that way. But bear in mind, you could be dealing with much larger tables, or it might be running from data which is streaming in live, and so you can't look at it manually. So let's look at how we would do this using pandas to do it for us. The first thing to look at is we've got this information here. The next question we want to ask is, what data in the population column is the smallest? Well, let's start off by getting the population column. That's given us just the data out of that column with row 0, 4, and 8. Notice it hasn't renumbered the indices, it's maintained their original numbers from the original table, 0, 4, and 8. And what we can do is take this and assign it to a new variable, because I don't want this line to get too complicated. So I'm going to call this pop, and we've got a variable called pop, which is the same thing, but it means we're always able to refer back to this set of data. If we look at pop, let's get rid of that highlighting, we could do min. Calling min on a series gives us back the smallest value in there, so 2.148. We could use that number and then refer back to the table and find the column, so we find the row which has that population value inside it. But that's a manual process, and we want to use the computer to do our job for us. So there's a function built into it, and this is the one I didn't tell you about, called idxmin, which stands for index min, i.e. give me the index of the row which has the minimum in it. In our case, the minimum is this, and so the row, the index of the row is 0. So this should return us 0. If we change this to index max, we see we should get 4. And we do. But we don't want max, we want min. So given that, we now want to use the fact that we know which row had the smallest population in the year 2001 by going to our census table, grabbing the city column, because we want to get the city out at the end of it all. Actually, no, let's do it the other way around. Let's do this. No, let's do city column first. City, which gives us back the city column. And then that's a series, so we can ask a question of the series by chaining together these square brackets and put inside there this question we asked. This is 0, so it's going to get the 0th row from the column here. We run that and it prints out Paris. So that is how we answer this question. Remembering that pop is actually this thing here. So if we wanted to, we could copy that. We could use our thing here, replace pop with it, get rid of these spaces, and run that. And we should get the same answer. We do. And when you look at that line of code there, you realize why I split this onto multiple lines with multiple variable names, because while this answered the question, it's a very dense and difficult way of understanding it. We've got just over an hour left today, so we've got two main topics I want to get through still. The first of which I'll jump into now, and want to make sure we get round to making plots before the end of the session, because for a lot of you, that's going to be the reason that you came. So, I've made a new notebook here, still got my old ones open, so we can refer back to them. But we're going to start off, let me just get my notes up. We're going to start off going through how we go about reading a file. So switching back to the notes. Pandas has built into it lots and lots of ways of reading files from either from your local hard disk or even downloading them directly from the internet. It's got a variety of tools for different file formats. One of the most common you're going to see is comma separated values, CSV files. But I would not be surprised if many of you are also dealing with Excel spreadsheets. In some domains, you'll also come across file types such as HTF5 or even SQL or SQL databases too. Beyond that, there are a number of other file formats which Pandas supports, but those in my experience are by far the most common. To show how Pandas gives us the ability to read in these different data formats and to deal with the inevitable messiness that comes with them, we're going to go through an example now. In my experience, files that you're reading in are never quite in the format you want them to be. You might wish that they were perfectly laid out, neat, everything there, nothing missing. But realistically, the real world gets in the way and we have data which is messy. Either it's poorly presented, poorly laid out, or just has stuff missing from it. So if you've already come onto this page, we had to update the page in the break because something had changed and it wasn't working anymore. So make sure you refresh this page before you carry on copying the examples. So I'll refresh that now to make sure mine's refreshed. There we go, refreshed. So here is a CSV file example. It's available at this link here. So this here is the contents of that file. It's got some text at the top which describes what's going into the file and sort of an explanation about what's inside it. Then it's got the actual table of data itself. You'll notice it's using semicolons instead of commas to delineate the different columns in the table. It says up here a -1 signifies a missing value. So we've got some -1s, which mean there's no census data for that year. There's also some places where we've just got 2 semicolons next to each other, and that's meaning that in this gap here, there's again missing data. So there's lots of missing data. It's in a strange format. It's got some stuff at the top we're going to have to deal with. And I'm going to go through now how we can deal with this stuff and how we can get pandas to read it in a nice way. So we start off by importing pandas. There is a convention that when you import pandas, you import it as PD. It doesn't matter. You could do all this just with import pandas. But when you come to finding examples online, you'll see people using PD dot something quite a lot. So it's worth getting used to seeing that. Make sure that's imported. So the function that we're going to be using today is something called pd.read_csv. There's a whole bunch of read_somethings. In fact, let's just have a quick look at them. This is just loading up. Read CSV, FWF, JSON, HTML, etc., etc. I won't read all of them out, but there's a lot, as you can see. The nice thing that Jupyter Notebooks give us is that if we've got a function and we don't know how to use it, we can just use a question mark and then run that cell, and it's going to print out the documentation for it. And you see here the documentation for read CSV is long. This is an example of what might be considered a bad function because it's got far too many arguments to it. But it's one of those situations where they've tried to find the balance between functionality and usability. On the whole, I think they found it correctly, but there are a lot of arguments. These are just the arguments and their default values. Scroll down further, and it has a description of each and every argument in there. So we're going to be referring back to this along the way so that we can see what we need to do. To that end, I'm actually going to switch back to the notes here, and there is a link after import pandas PD to the manual. So I'm going to click on that link, and this is that same thing but on the web page because it's going to be easier for us to search through it on the web page. So the first thing we do is pass in the file that we want to read. Now I've prepared a file for you at a link which I'm going to copy and paste there. Again, this is in the notes. This is just defining a string. We are going to pass that string to the read CSV function. And there we have it. It has downloaded the file, opened it as a CSV file, and has attempted to interpret everything that's inside it. As you can see, it's done a job, but it hasn't done a brilliant job. It is naively assuming that everything in there is a CSV file, and is asking for us to explain anything that is outside of that loose convention. So the first thing we'll see is it's included the comments at the top, all that stuff that was explaining what was inside the file. I'm going to reorganize this. You can do this in Python. You can have a function call with arguments, one on each line. And I'm going to have to use another argument to this function to tell it that it should skip some of the rows. So I'm going to go to the documentation, and I'm going to Control F and search for skip. Now, skip initial space. Let's do match highlight all. Skip rows. That sounds like the one we want. So let's look for skip rows. Skip rows, and go down the page. And here is the documentation for that argument. It says the line numbers to skip. That's what we want. We want to tell it how many line numbers we want to skip. So let's go back to here and pass in skip rows equals, and I think it is 5 we want to skip because there were three comment lines, then 2 blank lines. If we run that, there we go. Those comments at the top have disappeared, and already it's looking a little bit better. We've just got the data left over. The next thing is that this CSV, again in inverted commas, isn't using commas to separate the values. It's using semicolons because I was trying to be deliberately obtuse when I designed this file so that we could learn together. So again, we go back to the documentation and go to the top, and we want to find out how to tell it which thing that it should use to separate the columns. So let's just start looking for sep. There we go, sep. There's an argument called sep, which if we go down to, delimiter to use. Now delimiter means the thing you use to separate stuff. If it's none, it tries to guess what it is and it assumes that it's a comma. And you see here the default is the comma. So let's do sep equals, and then it's a string, it's a semicolon we want to use as. And so now we run this, and there we go, we're basically there. So we've had to tell it what file, what to skip, and how to separate it, and it's pretty much done the right job. You'll see in those places where we had those consecutive semicolons, we've now got nans showing up, because there is missing data. They are not numbers, they're not 0. Population of 0 is a valid population. These are not values. However, you will see that there are these -1s in there. And if you remember from the documentation that we had at the top of the file, it said a -1 signifies a missing value. You'll notice partly that it's changed it into -1.000. Again, because of the whole nan thing, it's converting them all into the same data format. But we want to tell it that a -1 is not a valid number. It is in fact actually signifying missing data. So there we can write, well, let's have a look through. Let's have a little browse at the top. This is generally the way that I work when I'm using a library. I sit here and I stare at this and see if I can work out what's going on. So let's try searching for nan. Nan. NA they're using here. Okay, so NA filter true NA values. Let's have a look at NA values and scroll down the page. Additional strings to recognize as nan. Okay, so we give it a list of strings and it's going to use them as nan values. NA values equals -1. And now we should see these -1s turn into nans. Let's watch that happen. 3, 2, 1, bam. There we go. It's now representing all the missing data as nans. The last thing we might want to do is that here we have 3 columns which contain data, some of them missing, some of them aren't. But we have a column here which is unique, and in a census you would normally use the year as the primary index by which to say which year you care about. You say the first thing you talk about is which year you're talking in. We haven't told it what index to apply to our data frame, and so it's generated the 0, 1, 2, 3 defaults. However, we can tell it that it should use this column as the index, and so it will take these numbers and use them as the index and have it not as a column of its own. And we do that by passing in the index col argument. We switch to the documentation, index col, columns to use as the row labels. That's exactly what we want to do. Equals year. When we run that, we see the year has become bolded, it's now down there, and we've got our data frame all working together. And because we've done that, it means we can do something like census equals this. Census, like we did before, to get the city column. Oh, hang on, no, it's not called city anymore, is it? It's called, it's a different layout. Let's get the information for London. And you see here it's giving us a series with the columns being the years, which means we can say something like 2001, and it gives us back the population for London in the year 2001. Lets us very easily navigate down our data. So for the exercise here, go to the bottom of the reading from file chapter, and there is a link to, and I'll just go there myself. There's a link to this DAT file. So do the same thing that I just did, but doing it over this DAT file instead. And if we look at that file, okay, it's not going to let us look inside it. That's annoying. Actually, we can have a look at where it came from on the Met Office website. Loading, loading, loading. Loading, loading, loading. That's not going to load. So in the meantime, just take that URL there and paste it into the same read CSV thing we did above, and try doing that same thing. Try just fiddling with the data, try adding in skip rows, changing the separators, things like that, and see if it starts to look how you want it to. And if you get stuck, have a look at the answer, and otherwise I'll go through you all with it in a little bit once you've had a chance to play yourself. Okay, so got a question in chat from Jesse. Let me just get that loaded up. So you're writing this string here and you run it and it's saying invalid syntax. And the reason that's happening is because on Windows, they use the / character to represent folder separators. However, in almost every programming language, / is used for control characters. So for example, \n is a new line. And so it's reading your string here and seeing this as \U, which I think is how you write Unicode characters, and \W is something else, etc. So one thing you could do is replace all your slashes with /, because they work fine on Windows. Otherwise, as Chris says, do an R at the beginning of it, which makes a raw string, and then that will work successfully. Okay, so I'm just going to go through the first part of the exercise there. So the first part was just to open the file and get it all read in correctly. So leaving that other stuff on the screen there, I'm just going to paste that in, and I'm going to comment out the magic bits so we can kind of build it up bit by bit. Feel free, while I'm doing this, to just carry on going through the exercise yourself. If you've done this already, you don't have to listen to me. Feel free to carry on through the other bullet points, looking at negative temperatures, etc. But for those who are interested, I'll just go through this on the screen. So we read the CSV in from that file. I've commented these out so those aren't being applied. And we look at it and it looks all wrong. All the files are in the wrong place. It's got all this extra information at the top, which we want to skip in the same way we did with everything else. So when we run this again with the skipped header, suddenly we're getting data that looks correct. Again, it's assuming that it's comma separated values, but our table, as we saw was not comma separated, they're separated by spaces. So we want to tell it that instead of using commas, it should use white space to separate the columns. And if we now run this, we see that it works. I'll point out one thing about this data because we are going to be using it in the next section, and in fact for the other exercises. The year column here isn't the year in which the data was measured, it is the average temperature for that year, in the same way that the October column is the average temperature in October. The final thing we have to look at, and if we look at the end of the table, this will be clearer with tail. In 2019, there's a bunch of 999s at the end. And that's because I downloaded this file and put it on the website in October 2019, about 6 months ago. And so there's obviously no temperature data for the future from their perspective. Now, it tells us in the format on the Metaphors website that -99.9 and -99.99 both represent missing data in the same one that our -1 did before. And so we can use the NA values to set them to nans. So when we run this, we see the nans showing up at the bottom. That last bit there is very easy to miss. It's also very easy to miss the difference between with 1 9 in the decimal place and with 2 9s in the decimal place. Yes, there's a question there about whether delim whitespace is the same as /s plus. It's a very good question. And in fact, I can answer it by going to the documentation and looking for delim whitespace. And it says right here, equivalent to setting sep is equal to /s plus. Now this, for those who haven't come across it, is called a regular expression. These are very powerful ways of matching patterns, which we don't cover in this course. If you are experienced with them, you'll recognize what this means. In essence, it means a bunch of white space. But to avoid people needing to know regular expressions, they've added in the delim whitespace argument to make that easier for people. Bo asks, how can I set all negative values as nan? So I don't believe there's a built-in way to do that using NA values, unless you only have a subset, a strict set of negative values you're dealing with. The way that I would deal with that is to read the data in and then do a second pass where I loop over that column or apply a function to that column which replaces any negative numbers with nans. So there's a function called apply, which applies a function you give it to every row, every item in a series, and you could do a if statement inside that function, which would check things out, which would compare it to 0 and then return none if it was less than 0. So I would do it as a second step after the reading in. I don't think read CSV has got built-in functionality. You could argue that read CSV has got enough arguments already without adding in any more. Yeah, exactly, as Christopher's done there. So I'll see if I can demonstrate that. So let's get rid of the NA values one here, and it just has these 999s. And if we on the row below do df, where df is less than 0 is equal to none. So that's going to find all the places where the df is less than 0, and it's going to set them to be none. So when we run that, and then look at df.tail, let's see if this worked. Crystal's reputation's on the line. It did indeed work. So I would do that as a second step. Okay, so I assume that people have managed to read in that data file using the example in the notes, and I should point out again, I don't know if I have pointed it out yet. On every exercise, there is almost always, I think always, an answer link. So if you click on that, it will take you to the answer, where this is the lines of code that I just copied and pasted from. So if there's ever an exercise you're stuck on, you can always find out the answer and get a little bit of help. But do try and have a go yourself with these things first. So I'm going to have a look at these other two exercises here. How many years had a negative average temperature in January, and what was the average temperature in June over the years in the data set? So there's a few kind of slightly more complex questions we might want to ask there, but the sort of thing that if you're doing meteorological data are the kind of questions you might want to be asking. So the first thing there was how many years had a negative temperature in January? So we've got our DF, which again shouldn't be called DF because that's a bad name. It should be called temperatures, but let's just carry on for now. Let's start by looking at January because that's the month that we care about. That's the column. If we ask a numerical mathematical question of that or a logical question of that, it's going to give us back another series. So we can say where Jan is less than 0, that's going to give us all of our negative values. You see it's done falses. It's done a ... in the middle because that jumps from 1663 to 2015. There's several centuries of weather in the middle. Some of them are going to have an average January of less than 0, but for some reason the first 5 and the last 5 don't. We take these trues and falses and we pass it back into DF. And that's filtered down our data, so we see that all of these first column here values should all be negative. So 1684, 1695, 1709, etc. all have negative values. If we want to find out how many there are in here, the easiest way to do it is to call the len function on the list. No, my computer's having troubles. There we go. So I've just passed this data frame into len. No, I need to... That gives a different answer in my notes. Because I've got an extra pair of square brackets there that I put in accidentally. There we go. So dfjan is less than 0. df of that, there we go, is 20. So there are 20 rows which have an average January temperature of less than 0. I think there is also another way of doing it, which I'm going to try and work out live with you all in front of me, which is always a risk when you're programming. There's a bunch of functions you can call on data frames. So the result of this whole thing here is that it's a data frame. So there is, for example, I think it's summary. Nope, not summary. Count. This is where I should look at the documentation, but I'm being the wrong kind of lazy. So there we go, call count on a data frame. It tells you for each column how many items are inside it. I think by default it doesn't count nans, but it will count anything that's not a nan. So here's another way we could have done it. We could have said data frame of January.count. Or if we wanted to, we could have taken from our data frame, we could have grabbed just the January values, and then we could have called .count on that, which would have given us 20 as well. There is, as they say, more than one way to skin a cat. I don't like skinning cats at all, but if you're going to, you can do it with code. The other question that was in the notes, which I'll just move down for, was what was the average temperature in June over all of the years in the dataset? So again, average temperature in June, thing to start with is looking at the June column. Here's a bunch of data. If you want to find the average of a series, because remember when you get a column out of a data frame it gives you a series, there's a function called mean, which you just call directly on the series and it returns you the single value of the mean. 14. So over the last several decades, in some measurement location in the UK, which is where this temperature data was collected, the average June temperature, or the average of the averages, I should say, is 14 point something degrees. If we look at the Jan temperature, we see the average Jan temperature is 3. This tells us we are probably in the northern hemisphere. Yes, question there about why the first example I did up here didn't work. I think it's because I accidentally missed off DF there when I was typing and overwrote it. So it was giving us the length of this list, which is a list of length 1, and so it was just giving us 20. We could actually, I think, have not do that at all, and that gives us all of the trues and falses, which is 361. So we want to be able to select just the data from it that is has the true value, which is those that are matching this predicate 20. So there's a question there, how do you set the index column if it doesn't have a name? That's a good question. So the data we were dealing with here actually had its first column, the one that had the dates inside it, didn't have a name. I'll just see if I can... I don't think I have the original file anymore. Let's have a look. This is a peek behind the curtain at the material. One thing I didn't point out earlier is that the website you're reading for the notes, everything on there was written using Jupyter notebooks. So these are actually notebook files which get compiled into HTML and presented to you. But let's have a look at the file that we're dealing with. This one here. So you'll see here, this first column here with the numbers in doesn't have a column title. And so Pandas has taken a guess and has decided that this must therefore be used as the index. That makes sense. And so it's decided to use it as the index. If you have a column in there which doesn't have a label, then what I would normally do is explicitly tell it what the label should be. So instead of it having read the file for the labels, I would say, give these the names, year of measurement, January, February, March, etc., 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 year or average. Then once that's done, I would use the labeled that I've now given it a label as a thing I pass to the setIndex function to say, use this column as the index. So I do it again in kind of 2 stages. So Jesse, your question about you've got a list there, can you use a mask expression to find values? I don't think so. I'm often wrong. So let's have a look at the documentation. Actually, do I have it open already? No, I don't. And let's have a look at NA values. I did skip over it earlier. So NA values takes a scalar, like just a number, a string, a list like, or a dictionary, and it is optional. By default, it's this. So there's no option here for the type of this to be a function. So there's no ability here to pass in something which is either a function or something which maps something. So built in, there's no ability to do that. So I would suggest using the feature that Christopher found for us earlier, where we did, commented that out. And then we did, we did df less than 0 equals none. But instead of doing df less than 0, you could do some other predicate inside there. So back to the notes here. Been through these exercises. We've opened and read this separate file. Make sure you keep that bit of code around because we're going to be using it in the next section. We have done some questions on the data. We've asked about negative annual temperatures and the average temperature in certain months. And this is the useful kind of things you do. So obviously in this course, we can't get fully into depth about doing every single type of analysis. We have another course, which will be running a few times after Easter, so in the next month or 2, called Applied Data Analysis in Python. And there we actually learn some analytical techniques for studying more complicated things about your data. But a lot of the time you just want to do relatively simple filtering, and that's what we're doing in these sections here. The other thing that you often want to do with your data is not to look at it in a form that looks like this. I mean, it's nice to be able to look at your data in a table, but really you want to be able to see a better visual way of representing it. So for example, here we see we've got 11s and we've got 13s and we've got other things happening. It's hard to see trends in a table because you can't see anything really happening. You can see a bit of a trend. So if you look at the July temperatures, they slightly go up. They're 13s up to 16s. You know, there's maybe a trend there, but it's hard to see in a picture. So we are going to move on to the next section, which is plotting. Got just over half an hour left, which is perfectly on time. Moving on to the next section, which is the matplotlib URL, plotting data with matplotlib. Matplotlib is the de facto default plotting library for Python. If people could just post in the chat whether they've used matplotlib before or not, that would be an interesting kind of sample to get a sense of where people are. Yeah, so there's a lot more people saying yes, they've used it. I mean, I wouldn't expect everyone to have by any stretch, but it's hard to avoid using matplotlib if you've ever done anything sciencey in Python. Now, what I'm going to show you in this first section here, while it uses matplotlib, you don't actually need to know any matplotlib at all. It's a very shortcutty way of doing things, because Pandas has built into it an interface to matplotlib, which does all of this stuff for you. So let's have a go at doing some of this stuff. So I'm going to leave my df here, which is our weather data. The simplest way to plot something is to take something like a data frame and do a dot afterwards, type 4 letters, 2 brackets, and then run the cell. And at its core, that's everything you have to do. One of the things I really love about Pandas is they've optimized it for the most common use cases. It's very common that you want to just draw all of your data and just have a look at it. And looking at this plot here, can any of you see anything wrong with it? Post in the chat if you can see what's funny about this plot. Yeah, exactly, David. The y-axis is going down to -100, yet if we look at our table, we see that all of our numbers are... Oh, hang on. Looks like I made a mistake. When I was playing around and showing you the examples, I accidentally forgot to change it back so that these -99s weren't in there. And this really illustrates one of the brilliant reasons to use plotting. It's not just for having something to put inside your paper you can publish at the end of the day. It's so you have something which can visualize the shape of your data very quickly and easily. So looking through this table, we might have seen these -99s because they're at the end, but if they happen to be in the elided section in the middle, there's no way we would ever have noticed them without doing a plot. So doing a plot immediately draws on the screen. We see the green down here behind the legend. You can just about see the line going down all the way to -99.9. So what we want to do is go back to our reading function, which is further up the page. Where is it? Here it is. Make sure we've uncommented out this bit here because I was doing a demonstration. Run that, and then have another look at df. We see that df is now nan, it's the Batman. And when we plot it now, we see our data, while not pretty, is now at least laid out with the correct values. So the next thing you would usually want to do when you're plotting something is not plot all of your columns all in one big plot. You'd want to kind of pull out some kind of particular piece of information. And so instead of doing df.plot, we can instead do df year. Oh, sorry, I forgot the quotes. So df year, that is our series. And if you do plot on a series, this one here is plotting a data frame. This one here will plot a series. We get just that set of data. We get a plot of that time series. And this is where you see the very sad fact right in front of your eyes from publicly accessible information that definitely, on average, over the last 400 years, the temperature of this part of the UK at least has been increasing. There's a certain trend of, I don't know, looks like 1 or 2 degrees, which is fairly significant when it comes to the mass of air in the atmosphere. So this, I think, is a really nice way of seeing actually global warming happening right in front of your eyes. Now, a plot by itself like that is nice. We can see our data and it's good for exploring things. But you usually want to actually do something to your data. You want to be able to label it and give some information to your reader. And so the way we do that is we say, we take the result of this df year plot thing, which as it happens is the thing that's being printed out here. It's a matplotlib thing. And let's give it a name so we can refer to it later. So year plot, run that again. Same thing happens, but now it's been stored inside this variable. And because we've stored it in that variable, we can do things to it. We can say year plot dot set y label is temperature. And then when we run that, we'll get a Y label appear on the left-hand side. Oh, I can't spell. Thank you. Year plot. There we go. Now that's all showing up how we want it to. And temperature is showing up on the left-hand side. Now in the notes you might notice I've got some weird stuff going on, where after temperature I've written $$ circumflex / circ C, and written an R at the beginning. And this bit in here, if any of you have used LaTeX or Tech before, it's a way of representing sort of mathematical symbols. This means superscript, draw a circle, so that's going to do a small superscript circle, and the letter C. The R here is needed for that same reason I said earlier, so the backslash isn't interpreted by Python. So when we run this, we get, oh, the brackets are in the wrong place. There we go. We get degree C, so you should always have your units on there. So have a go at that yourself, reading the data, plotting the thing. The exercises are further down the page, just above halfway, about a third of the way down. Reproduce that plot, try tweaking the labels, try putting the X label on, see if you can guess what the function is to set the X label. Try plotting some different months, and then we'll move on to the next little bit. So David, as to your question about what kind of object R is, everyone else can just carry on for the minute, you don't need to listen to this. I'll demonstrate. In summary, it is the same thing. So if we look at type, no, if I could spell I would, type of hello, it is a string. If I look at the type of R, hello, it is also a string. So the way that Python uses this R in front of it is it kind of uses it to pre-process what's literally written here before it turns it into a string. Normally Python reads a quote and it happily plods along until it sees another quote, and it does stuff to things in between like new lines. What the R here does is it changes the way that it reads through this string before making a string out of it. And what the R really means is don't do anything until you see another closing quote. Adam, to your question about square brackets and round brackets, as Christopher says, exactly right, square brackets are used for indexing and round brackets are used to call functions. When it comes to things like pandas, it's a little bit more complex than that. It's completely true that that's what it does, but I tend to think of it more about square brackets are used to ask queries of the data, because you can do more than just ask for a single index. You can pass in, for example, that series of trues and falses. So because you can put more complex things in there, I think of it more as a query syntax, where lists and dictionaries have got a very simple syntax, but series and data frames have got a more complicated query syntax. But as per the language, square brackets means index operation. And the next little section is other kinds of plots. So you might have noticed we never specified what kind of plot we wanted. Pandas just defaults to, if it's .plot and you're doing it over a series, or a data frame which is just a bunch of series, to do a time series plot effectively. It treats it like that. Now, different kinds of plots actually need different kinds of data. And this is something that I think when you're taught about bar charts and histograms and stuff at school, it isn't always quite made explicit. But I see a lot of people making mistakes by just thinking, I've got some data and I want to represent it in this way. And maybe the two of them don't actually make sense together. For example, you shouldn't just, or you could, but maybe it wouldn't make sense, just take all your data here and plot it as a bar chart. Because arguably it's continuous data. Maybe it's continuous, maybe it's not. That's really where it starts to get a bit blurry. But for example, if we wanted to do a chart of the temperature in each decade kind of could be thought of as a independent singular value, and so we want to plot a bar chart of the temperature in each decade going across the sheet. So let's have a little look at how we can do bar charts. So at its most simple, I will do the thing I just said I wasn't going to, and show you that you can do .plot, and then before doing the brackets there, you can write bar .plot.bar and then call that as a function. It's a bit of a weird syntax for people who are used to Python, but there is a way to make this work. You run that, and it does a very, very, very dense bar chart where everything's smashed together and you can't really see very well what's going on. Now, that's not a very useful thing to do. Really, we want to look at a sort of a simplified view of this. Here we've got 300 or 400 pieces of data. Bar charts don't work well with that many pieces of data, so we want to simplify this down. So let's delete that cell and start again. So I'm going to introduce, while I'm technically introducing bar charts, I'm going to introduce a few other bits of syntax in here, which I think are useful things to know about. So first of all, we've got our data frame. If we want to get out just the years from this data frame, the years here are in the index column. They're not a column by itself, so we can't just do square brackets index because there's not a column called index. Instead, there's a shortcut which gives us the index, which is just dot index. That gives us back effectively a list of all of the index values. What we want to do to turn this column here and group these by decade is to have our table here, and the way we're going to do it is we're going to make a new column on the right hand side which has inside it the decade that each row is in. This first one will say 1650, 1660, 1660, 1660 and so on up to 2010, 2010, 2010 all the way to 2019 being also 2010. And to do that we're going to do a little bit of string manipulation, and so I'm going to sort of play along with this, and if people have any questions along the way, ask in the chat and I'll try and pay attention to both windows at once, but otherwise I'm sure my helpers will keep up. So we're going to make a new series which contains this column here but turned into a string. So df.index, and we're going to turn that into a series. We're turning it into a series so that we can add it as a new column. Now the index of that new series has to match the one we're going to insert it into, so it has to use this same index here. So this is very repetitive, but df.index. And if we look at that, I forgot to import pandas on the screen. From pandas import series. Here we have index column, values column. They are the same as each other, and the d type is integer. However, we want to have these as strings because we're going to be doing string-like things to them in a moment. So we apply to the data in that column the string function. Looks the same, but now the d type has changed to object. And this we are going to call years because these are the years that we're dealing with. We're going to take that and we are going to apply another function to it. And the way we're going to apply this function is something you might not have come across, and that is a lambda function, which is a way of very concisely applying a bit of information to something. So this x here is going to represent each year, each row from our series. And so we're going to take each row, and that is going to be a string, which is 4 characters long, like 1659, for example, or 2019. And we are going to take the first 3 characters from it, and then add the string 0. So we're cutting off the units number from the year and replacing it with a 0. And if we look at that, we end up with 1650, 1660, 1660, so on, 2010, 2010, 2010, 2010. So this is now our data which represents the decade that we're in. We can then go back to our data frame. And assign that series we've just created with the decade strings to the decade column. So it's going to make a new column called decade. And so now when we look at df.head, we see we have a new column decade which has 1650, 1660, 1660, and so on and so on. So in order to plot our data by decade, we first had to make a column which represents a sort of a consistent piece of information for each row that we want to group together. Because the next thing we want to do to our data, a thing you can do in pandas, which we haven't come through yet, but I'm going to introduce now, is grouping. So if you have a table of data, you can group together rows based on certain conditions. In the example earlier, we had that continental column we created based on whether the city was or was not London. So we might, for example, want to group our table we had earlier by is this continental or is it not? Then we could look for getting summary statistics for one group, summary statistics for the other, and then we can compare the two against each other. In our case here, we want to find summary statistics by grouping together based on the decade. We want to have we're going to make a new table which has one row per decade. And the row per decade is going to be made up by averaging the stuff that are in the rows that are inside said decade. Let me just switch back here. So to group things in pandas, we do df. Remember, df is this table here. Dot group by decade. If you just give a column name, it will group by all the values that are the same in this column here. So it will make one group which contains this one row here, 1650. It will make another group which contains all of the ones that are 1660. Another row which contains all the 1670s, 1680s, 1690s, and so on. So it'll end up with one group per decade. Then we tell it what we want to do to each group. If we just look at what we get here, you see it gives us back not a table which has the groupings in, but some kind of intermediate object. And that's done for performance reasons. But we can tell it, now what we want to do to each of those groups, we want to find the mean of each group. And when we run that, we get back this. So you see here, it's made a new data frame. This is not the same data frame as before. The index is now based on the thing that we grouped by. So the decade is now the index, because we told it to group by decade, and so it's taken that to mean decade is the important thing, so use that to index our data. It's then made a row for each decade, where the values in that row, for example, this 2.60 here, is made up by averaging all of the rows from the previous table, which are in the 1660 decade. So 0, 5, 5, 1, and then some more that are hidden down here. So that gives us 2.6. So this has given us a table which is now actually small enough to fit on the page. These are all the decades between the start and the finish. I know scrolling's difficult when it's like this. So let's change this to dot head, just the first few rows, or dot tail, the last few rows. Good, Christopher's doing a brilliant job keeping up with me in the chat. So the very last thing we want to do is assign this to give it a variable name. Let's call this by decade. I can never spell decade. So this variable here is that data frame that we just saw, by decade. So if we call dot plot on by decade, we will get a line plot over the decades, just like we did before. But you see how we've reduced the noise in the data because we've averaged over the values within each decade. We don't want to plot all of them. We want to plot just the year because we want to reduce the data we're plotting still. This is where we really see that upward trend very, very clearly. Before it was slightly lost in the noise, but now you can clearly see over the last 100 years, the temperature has shot up. You could say the same thing between 1880 and 1720, so maybe they were worried as well, but we know there's a global trend now, not just a local one. To make this into a bar plot, we follow plot with dot bar, and there we have it, a bar plot over the decades. So in summary, to do a bar plot, you just follow the plot with dot bar, but you do have to think about the kind of data you're doing things to. So if you want to do group by, you need something to group it by, and then you need to call the group by function. Last thing on this pandas-driven plotting chapter I wanted to cover was saving a plot to a file, and I saw that someone in the chat already got to this point and having a go and they were having issues, so I'm going to go through it on the screen up here. I'm just going to delete that file because I don't need that one anymore. There we go. So let's make a new cell. And let's see about how we go about saving this file. Now, in Matplotlib, like in many tools that are around, especially in programming land, there is often more than one way to do it. Now, a well-designed API will give you one clear and obvious way to do something, but it's not always possible to only have one way to do it. So I'm going to show you a way to do this. I'm sure that some of you, if you've done these things before, have alternative methods, but this is the way that I've used, and I think it's nice and reliable. Also, it has the advantage that it works outside of Jupyter Notebooks. So if you're doing your plots just in normal Python scripts, this is going to work well there as well. So we start with our df year dot plot. It plots it to the screen and we've got the thing showing up. However, it's plotted to the screen and has kind of got rid of the context that was around it. So I'm going to show you now how to explicitly specify some of the things that Matplotlib and Pandas is assuming for you. So the way that Matplotlib works is it works on these axes idea. Now an axis in Matplotlib terminology you can think of as being a plot, a single XY plot or 3D plot or something like that. Now Matplotlib also allows you to have multiple plots all on one page. The terminology it uses for that is one page which might have multiple plots in is called a figure, and then you have multiple axes within a figure. So if you want to do multiple subplots on one page, you need to start thinking in terms of figures and axes, and that's going to make your life much simpler. So the way that you'd start by doing that is calling the, well, first of all, you'd have to import matplotlib dot, is it plotlib? Let me just check something. I always forget this. pyplot as PLT. So because we're going to be using Matplotlib functionality directly in a moment, rather than just Pandas interface to it, we have to explicitly import Matplotlib. Until now, Pandas has been doing that for us behind the scenes. We then call plt.subplots. This is going to return to us by default a figure which has inside it one subplot. If we want multiple subplots, we could put in 2 there, and we get a figure with 2 subplots, or 2 axes. By default, it just gives us 1. We give them names, it returns us 2 pieces of information. It gives us the figure and the axis object. So the figure is the page, axis is a plot that we can start to draw on. By default, this plot here is empty, there's nothing inside it. We want to plot our data into this axis, which is inside this figure. And we do that by passing the ax argument to the plot function equals ax. So if we run this again, it should look exactly the same as how it did. What happened there? Subplots, sorry, it's plural. There we go, exactly how it did before. If we change that to 2, it's going to complain because we are getting back 1 axis object, but we're asking for 2. But we can do that if you unpack the arguments. Once we've got this, we can then refer to this figure object, which knows about everything that's inside it. And so we can end the line with fig.savefig, and we give it a name, myplot.png, let's say. And it's going to save that. And you see, as I press that, myplot.png appeared over here on the left. Let's prove that happened by deleting it and running that cell again. It appears over here. We can open it up and we see this is the plot. In Markdown mode, we can code Markdown. We can then display that plot by using the Markdown syntax for showing a picture, which is my plot.png, and then it shows up in Markdown mode. This is a picture, so we can have hello, bye in front of and behind it. So that's how you save figures. And if you have your analysis pipeline from reading in your file, doing your analysis, all the way through to saving your figure, you can then run that anytime and update all the plots in your analysis in one go, which is a really, really nice way of working. So in the last few minutes, I'm not going to do any more code because the very last section in here, if you go to the bottom of the Matplotlib chapter and press next, there's a section called Making It Prettier. So this section, again, I suggest you have a look through in your own time because there's quite a lot of very dense code. Do email us if you have any questions. But to summarize, With matplotlib, you can go from making a plot which looks like this, which is using the default colors, default axis labels, etc., until you get a plot, excuse the scrolling, that looks like this. So there we've changed the axes, we've changed the colors, we've added in labels and written mathematical texts, we've put in a legend, and it's able to present things in a nice way. So matplotlib gives you the ability to do that, but if I scroll up just a little bit, you see that the code can sometimes be a little bit complicated. So have a look at this section in your own time later on. I tend not to go through it in the class because it's just a lot of repetitive stuff. But do have a look at this, go through it step by step. It should explain what's happening along the way, and you can see how you can start to design your plots to be a little bit better presented. Moving on to the summary now. That's everything I wanted to talk about in the course, basically. So thank you all for coming along today, and I'll hopefully see you again in a course in the future. So the way to start Anaconda Navigator will depend on which operating system you're on. It varies from place to place, but hopefully the instructions that were provided with it gave you the ability to get at least as far as a window that looks something like this one here. So it's the green Anaconda Navigator with the circle and a bunch of tiles on the screen as well. Anaconda Navigator is the way that we are getting access to Python. So Python is provided for free. It is a completely free and open source piece of software. There are lots of ways to get it installed onto your system, but one of the easiest that we found, particularly for these training sessions, is the Anaconda system. So Anaconda provides us with the programming language Python, as well as a bunch of tools which we can use to write and run Python scripts. Some are basic tools and some are very advanced, and you see a selection of some of these on the screen here. For the course today, we are going to be using a tool called Jupyter Lab. Note that Jupyter Lab is different to Jupyter Notebook. Jupyter Lab is a web-based, simple development environment which allows us to write and run Python scripts and more, but that's the extent that we're going to be using it for today. So go ahead and press the launch button on the Jupyter Lab tile, and I'll do the same, and that should open up in a web browser the Jupyter Lab environment. Takes a few moments, you see, your web browser should pop up. It thinks about it quite hard, you get spinny things, and then we are here. And with that, I'm going to put Anaconda Navigator away, make this full screen, and nice and big. So you should end up in an environment something like this. If you've already followed through the video explaining how this stuff gets set up, then you'll automatically be left in the environment you last left it in. So it should all be laid out correctly. So the things we're going to be doing in the session today is writing Python scripts and running Python scripts. So there's two different tools that we are going to be using. Firstly, we're going to be using the text file environment to write our Python scripts. So I click on text file, and that has opened up this whole window here as a text file. It's just a text editor. I'm then going to open a terminal. To do that, I click in the plus in the top left, and then at the bottom here, I press terminal. I now have a terminal covering my screen. To make it easier to see everything that's going on at once, I'm going to click and drag on the terminal tab over to the right hand side so that I have the text editor on one side and the terminal on the other. This is all covered in the first video that we sent out, so if anything here isn't working or you've just missed what I did, feel free to have a look at that first video. It's only a few minutes long to catch yourself up. I'm just going to do something which you don't need to do, so ignore this. It's because I've got my files in a special place to avoid confusing things. There we go. So we're going to start off by writing our very first Python script. But before I jump ahead and do that, I'm just going to give you all 30 seconds or so to make sure you're up to speed with this. You've got your text file open, you've got your terminal open, and it looks largely the same as what you see on my screen. Bear in mind, anything you have in this bit on the right might look slightly different, but it's basically the same. Hopefully everyone has now got their environment set up like you see on the screen here. So we're going to go ahead and run our first Python script. So before we can run any Python code, we first need to write some code. So let's go over to the text editor on the left-hand side. And the first thing we want to do, because currently this file is called untitled.txt, the first thing we want to do is rename this file so that it has the correct file extension. So Python file should end with .py, not .txt. And secondly, untitled is a undescriptive name for what we're going to be doing. So if you right click on the file name in the file browser on the left hand side and go down to rename, so right click and rename, and we're going to select all of that text, including the .txt, and I'm going to call it script.py, and then press enter. And you'll see it's renamed here, and it's renamed up here. You should also see that the little icon next to it has now changed into the logo of the Python programming language, so we know that it's understanding that this is a Python file. With that, we can go ahead and start writing our Python code. We're going to start with what is probably the simplest Python program you can write. And I'm going to explain the different components that go into it. And from there, we're going to build up into more and more advanced scripts as we go through the session this afternoon. So the first thing we do is write the word print. All lowercase and without any spaces before or after the word. And we follow that with an opening and a closing round bracket. This is the print function. Functions in Python are usually lowercase. They can't have any spaces in the name of the function. And a function is called by following it with an opening and a closing round bracket. Some functions don't take any different parameters or arguments, so they don't have anything in between the round brackets. The print function, however, does take arguments, and the arguments it takes are things that we want to display onto the screen. So to give information into the print function, we have to put something in between those two round brackets. So what we're going to put inside there is some words. We're going to ask it to display some words onto the screen. The way that you represent words, or as they're known in Python, strings, is using pairs of double quotes. So if you do a double quote and another pair of double quotes, and then in between them we write hello. So what we have here is the word print, followed by an opening round bracket saying that we are calling the function. Then we have the thing that we're giving to the function, the information that we want the function to process, followed by a closing round bracket to say that we've finished giving information to the function. You'll notice here that the text has been coloured green and red and so on. The specific colours aren't really important, it's just the way that the text editor gives us a bit of information. So it's telling us that it's understanding what's been written. Other editors that you can use won't have this particular colours. They might use blue and red or blue and pink or any other colours in principle. The other thing to note is that the text here is just plain old text. There's nothing special about the program that we're running this in. We can write Python scripts in a basic text editor like Notepad, or you can use advanced integrated development environments like Visual Studio. All of them work in the same way. They're writing simple text files which are then going to be interpreted as Python code. So in order to run this script, first thing we need to do is make sure it's saved. So one way to do that, I think, is to go to File and Save Python File. Make sure you always save your scripts before you run them. Now that we've saved that file, we can go to the terminal. So we're going to write our Python scripts on the left and run them on the right. To run your Python script, there's a few different ways you can run your Python script, and I went through the options for that in the second video that was linked and it has been posted in the chat. So if you get any errors coming up, go and check out that second video, and that will explain what the other methods are and what kind of error message you might see, and have a go at them. And if that doesn't work, let us know in the chat and we'll give you a hand. But the way I'm going to be doing it on my screen is by running the program Python. So I just write the word Python, ignore the $sign, that's just something that's built into my terminal. That's there by default, you see, that's just telling me that this is a terminal. I write the word Python, followed by a space, and then I give it the name of the script I want it to read, script.py. And so what's going to happen here is that this program here, which is called Python with a lowercase p, is going to read the file that I give it, which is this text file over here, and it is going to read that file one line at a time. It's going to look at the text on that line, it's going to interpret it, assuming that it's written in the language Python. Python is a language as well as a program. So as long as we've written some text in this file in the Python language, then the Python program is going to be able to understand it and do the things that we've asked it to. It's going to read it one line at a time and do the things on that line, then read the next line and do the things on that next line, and so on until it gets to the end of the file, at which point it will exit and say, I'm all done, success. So to tell it to actually kick off that process, in the terminal over here, after writing python space script.py, we just press enter. And we see here it has done what we've asked it to. It has printed, this is a bit of computer jargon, print in computer jargon generally means display on the screen. It doesn't literally mean print it out of a printer. It's a holdover from the olden days of computing, when everything was literally printed out on a printer. But it's displayed the text on the screen, hello, the same as we wrote in our file over here. It has then returned us back to the terminal prompt, the same as it was before, with a flashing cursor, ready for us to run the same thing again. So I'm just going to give you a minute or so now to have a go at doing that yourself. I'm also going to point you at the course notes. So what we're going through here, at the bottom of the first page is a next link. We're having a go at the chapter titled Getting Started here. On the whole, I'm going to be just doing the examples as they are in the notes, and I'll hopefully have Gareth keeping us topped up and tracked as to which chapter we're on. But here we are just going through this very first chapter titled Getting Started, in which we've written a text file and we've run that text file, and then a little bit of an explanation about how that all works, which I've just gone through. So have a go at that yourself, just take a minute or so, and if that's all working, then we're going to carry on in about 1 minute. That should be enough time. Mengdi, so the colour in the terminal doesn't matter at all. Mine is all multicoloured because I'm running ZSH on Linux, which has been set up to be all multicoloured. On most systems, it's just going to be plain black. So if you see hello printed out, then everything's working great. Some questions from Livia and Bryony saying you're getting syntax error, invalid syntax. That's, again, a number of different ways that this can be caused. There's two main types of errors that Python has. There's errors that happen while the program's running, like you've tried to divide by 0, or you're trying to use some information that it doesn't know is there. The other type of error is a syntax error, and that's when your file is written in something which isn't valid Python language. So the first thing to check is that your Python script looks exactly the same as it does over here. That you're using double quotes and not backticks or anything like that. That you're using round brackets and not square brackets or curly brackets. And that everything is in the same lowercase print as you see here. Do you get anything else printed out in the terminal apart from the syntax error? Could you copy and paste the entire thing of you running the script and the output in the chat, and that might help me work out what's going on there. Okay. I see what's going on here. So this will happen if you've accidentally got yourself stuck in the Python interpreter. There's a thing that happens if you just type Python and press enter. So don't do this, I'm just demonstrating. If you do this, you end up in an environment where you've got these 3 arrows here. Now this is like a terminal, but it's slightly different. If you end up there, type exit and then open and close round bracket and press enter. And you should end up back at the non-3 arrow terminal. Once you're back at the normal terminal, you should be able to type Python script.py and you should get the text printed out. So I'm just going to clear my terminal on the screen there so that it has a bit more space. Don't worry about doing it yourself, just clearing out what we see. So in Python, there are a bunch of different types of data that you can have. The types of information we've used so far has only been one type of data. We have had a string. They're called strings because they're kind of like a string of letters chained together. It's another bit of jargon which you will get used to. So we have a string here. Hello is a string. Strings are designated by having open quotes at the beginning and open quotes at the end. But as well as strings, there are also different kinds of data types. I'm just going to run the script over here. As a shortcut and a tip, if you're in the terminal and you press the up key on the keyboard just once, it will bring up the previous command you ran So you can press up on the keyboard and then press enter, and it will rerun that same previous script. I'm going to change this print function here now so that it prints something else. So instead of printing hello world, I'm going to print a number. So 3.14159, that's more than enough digits of pi. You'll see here that the number is green, where the string was red. That's just a decision that the highlighting in this text editor has decided. Again, the colours aren't particularly important. They're just there as a visual aid. You'll notice again there's a black circle here, and I'll point this out in the video, but make sure that before you run your script, you save the file. On Windows and Linux, it's Control S, and on Mac, it's Command S to save the file, or you can go to File, Save Python File. I'm going to use Control S. So now if I run the script by pressing up and enter, we get our number printed out. Okay, so we've got strings, we've got numbers, and we also have integers, which don't have decimal places. That works very well. So if we save that and run that, we just get the number 3 getting printed out. So Sam in the chat is asking, why don't you need quotes for numbers? So the reason for that is Python uses syntax to work out what you're trying to tell it. There are fundamentally different types of data that you deal with in programs. There are words which as a human you interact with because you're trying to describe something to someone, like saying hello. And when Python is reading this, it will see the string and it will say, okay, I know that you're not, this stuff inside the quotes isn't special in any way. It's just something that a human will understand, and I don't need to worry about what's inside those quotes. If it sees just, as it's reading along the line, one letter, one letter, one letter, and it gets to here and it sees a number that's not inside quotes, it's going to treat it as that particular mathematical number. And it's important because something we're about to see in a moment, that mathematical numbers in Python you can do maths to. You can do 3 times 2 or 3 divided by 4, and that's going to give you another number. Whereas something like hello, it doesn't make sense to divide hello in quotes by 3 because there's no description of how you divide a string by a number. And so by being explicit from the beginning about what kind of data you're dealing with, it lets Python know what kind of operations can be done to it. A thing to be aware of is that the string 3 is different to the number 3. This one up here, Python will just see as some words which humans understand and it doesn't have to care about. This second one here, it will see as the mathematical number 3, which it can do something with. So anytime you're dealing with numbers in Python, generally you won't put any quotes around it because you want the mathematical concept to be the thing that you're talking about. That said, it is sometimes useful to be able to talk about the types of data you're dealing with in a more kind of abstract sense. So in that example there, we just had a print function and we were just throwing the thing that we wanted to be printed straight inside those double brackets, and it was reading whatever we passed in and it was printing out to the screen. It's quite common to want to give names to your data so that you can refer to it multiple times, or to work as an aid to the reader so they understand what's going on. So for example, 1.3.14, that's good enough. Here we have a Python script which doesn't do anything. It's simply a number. So this here is a piece of data. We can give data names by assigning what's called a variable. And the way that you assign a variable to a piece of data, or assign a name to a piece of data, is by writing the name of the variable you want to create, followed by an equal sign, followed by the piece of data. So this is going to make a new name pi, which contains the value 3.14. This means that later on in our script, we can write print, and instead of writing 3.14, we can go ahead and replace the number literal that we would have put there with the variable name pi. And so when print pi gets read by the Python interpreter, it's going to say, okay, here's some letters. They're not numbers, they're not in quotes, so this must be a variable name. It's going to look up what that variable name is. It's going to see that it's this value here, and so 3.14 is what is going to be printed. So if I save this file and run the script, we see that it prints out 3.14. From the outside, it's looking basically exactly the same, but inside, we've broken it up into two parts. The parts dealing with our data and the part dealing with our output. So take a minute or two now to have a go at that yourself. Take any print function you want to do, anything that you'd want to print, but break it up over two lines. One line which takes that thing that you want to print and gives it a name, and then another line which has a print function which accepts that name as an argument and check that it prints the correct thing to the screen. Be aware that variable names can't have spaces in, they can't start with a number, and there's a few other constraints which you might find as you go along. I've introduced variables. A variable is a way of giving a name to data. And so in your head, it's worth having a sense of the difference between a piece of data, like 3.14, and a variable like pi. They can often be used in the same context, but they're fundamentally different elements of the language. So it's worth kind of working out in your head as we're going through the exercise, thinking about how data and variable names differ from each other. We've always seen a few ways. For example, a string has quotes around it and a variable name doesn't, so they look different, but they also serve slightly different roles in the language. So hopefully as we go through, you'll start seeing how that works. So I'm going to delete all this text and start with something different. So let's make a variable called distance in miles. And you'll see here I've used underscores between the words. There's a convention in Python to write your variable names as lowercase, to use full words in your variable names, and anywhere where there would be a space to use an underscore. Other languages have other conventions, but this is the general convention in Python, and it's the one I'll be following. And let's give it a value 30. So here we just have a number 30, which has no context or no information about it. Because we've got context here in the name of the variable that it says distance in miles, that tells us what this 30 actually represents. And so it's useful when writing Python scripts to give your variables descriptive names because it will help you understand what the numbers actually mean. If I want to make another variable called distance in kilometers, I could go ahead and just assign this a value. Now I don't even know what that would be, but it'd probably be something like 50 or so. But of course that is not using the computer to my advantage. I could Google it, find out what 30 miles in kilometers is and write the value in here. But a more flexible and reusable approach is to work out what the conversion factor is and to do that conversion ourselves in our code so that we can change one variable and always have the other one automatically updated. And so when assigning a variable, on the right-hand side, you can do more than just write a piece of data. You can also refer to other variables. For example, distance in miles, and we can multiply that by a number. And I'm going to copy the number from down here to avoid errors. So here we made a new variable, and the value of this second variable is based on another one. So then when we print distance in kilometers, and then I save this file and clear it and run it, we see printed out it's 48.2. It's about 50, but it's a much more precise answer. This means that we can come back to our original script and we can change this to be 5,000 miles, and we can find out what 5,000 miles is in kilometers just by changing one number, rerunning the script, and we find out that it's about 8,000 kilometers. So this is starting to show the value of using variables rather than hard coding your numbers. It's also showing you how you can use variables which are based on other variables. As well as multiplication, there are other mathematical things that we can do. So I'm just going to copy and paste this one from my notes down here. No one wants to sit here watching me type all day. And so here we have a variable which is a floating point number, a decimal place number on the right hand side. We're making a new number which is that plus something, and then we're printing that out. In Python there are 4 primary mathematical operations you can do. Plus, well, uses the plus sign. Minus uses the minus sign, as you would expect. For multiplication, it uses a star. And for division, you use a slash. So those are the 4 primary different types of operations that you can do to mathematical numbers in Python. Going back to Mengdi's question earlier about why some things are in quotes and why some aren't, I'm going to show you an example now of how Python sees the differences between those two types of data in the program. So I'm going to make a variable here, and I'm just going to call it my underscore number, and I'm going to set it to 67. And I'm then going to say my other number equals my underscore number plus 100. And then I'm going to print my other number. So we run this script, we get the kilometer thing and the Celsius thing printed out, and we get 167 printed. So it's successfully printing out the thing that we had. If, however, we put this 67 in quotes, Python is no longer seeing my number as being an integer. It's no longer seeing it as being a mathematical object. It's seeing it as being a text type object. And it doesn't know how to do mathematical things to text objects. So if we now run our script, we will see the first of our Python errors. It is unable to do the addition operation because it's no longer doing it to 2 numbers. It's trying to add a bunch of letters and a number together. And it's going to say that it's assuming that you made a mistake. It's not going to just implicitly convert something. It's going to make sure that you're going to be explicit about what you're doing. And so if we look at the error over here, the way that I read Python errors is by starting on the last line. It says type error. So that's telling it it's an error to do with data types, where types are things like strings or floats or integers. The error message itself is saying it can only concatenate strings and strings. Remember, this is a string, which means that my number is a string, which means that we're doing my number, which is a string, plus an integer. And so it's interpreting this as us trying to take one set of letters and stick another set of letters on the end. And that's what concatenating string to string would mean. Concatenate means stick next to each other. However, it's finding an integer, and so it's saying, I don't know how to do that, and so I'm going to bail out and stop. And when you get an error like this, the program will stop running, it will return you back to the terminal, and it will print an error like this on the screen so you can work out what's going on. So always start with the last line, because sometimes that's enough to let you know exactly what you did wrong and to let you know what's going on. If you've got a long program where your errors can crop up in all sorts of different places, it's worth looking at the lines above, which tell us where the error came from. This line here tells us which file we were on, which line we were on. We see it's on line 14. This is why programmers always have the line numbers turned on in their text editors. And then this line here in the output is the exact line that we had in our text file to give us context to let our brain jump back to the error a little bit more quickly. So with that, I'm going to ask you to have a go now at the exercise at the bottom of the data types chapter. So there's an exercise there to edit script.py so that it's made up of adding 2 strings together. So originally it said hello Python. In fact, I'll show you how it looked beforehand. It had something like my words equals hello Python, and then it was print my words. It might have had a different variable name, but that is not important. So have a go at taking this little program here, but breaking up this line here into 2 separate variables, one which has the word hello in, one which had the word Python in. Make a third variable, which is those 2 things added together, and then print that out and make sure it looks how you expect. Once you've done that, carry on to the end of that data types chapter. There's a section there on printing multiple things. So have a go at that, reading through that, and having a go at that exercise as well. Mengdi there has a question about, is there a difference between my underscore words and my words with or without the underscore? So the first thing I would say to that question, Mengdi, is the best way to find things out is to try them for yourself. you'll often discover something really interesting if you have a go with something and it works or doesn't work how you expect. That said, I will go through that with everyone because I think it's an interesting thing to look at. So here we made a variable called my_words. If I delete that underscore and put a space here, and then we try and run this script, I'm going to clear this and run the script, we get a syntax error. And the reason we get a syntax error on that first line is because Python starts reading at the beginning of the line, it sees the word my, and that's a variable name by itself. So the only thing that's able to follow a variable name by itself at the beginning of a line is an equal sign. It only makes sense if you're immediately following it to assign this variable a value. Because it sees the space as a break between two different variables, it's expecting there to be an equal sign next and not a space and some words. So this is telling us, the fact that we get a syntax error here, that my space words doesn't get seen by Python as a single thing. It gets seen as two separate things, a thing called my and a thing called words. And because they don't make sense next to each other, it's not understanding what you're trying to say here. So we need to put an underscore in. Sorry, an underscore. If we try that again, we'll probably still get an error. We do, but this time the error is on this line here because the same thing's happening. As an argument to the print function, it's expecting a single variable name. Here we're giving it two variable names separated by a space. It doesn't know what that means, and so it's going to give us a syntax error. So we need to have underscores. We could do it without any underscores at all and no space. That would work perfectly fine as well. The underscores are just there for visual clarity. Okay, so I'm going to show the answer to that exercise you were just working on. Hopefully you had a chance now to have a go with it. So as I explained to Mengdi, underscores are used for visual clarity and you can't use spaces in place of them. So we have our string here. We are going to change it into word 1, which is going to be hello. It's going to be word 2, which is going to be Python. And then my words is now word 1 plus word 2. We save and run this. And we see hello Python printed to the screen. The last section on that page was taking this example and making your life easier. You'll notice that you had to put a space here because when you add strings together, it doesn't automatically put a space in for you. If we get rid of that space and run our script, we get hello Python, all one word, which is not usually what we want. So what we can do with the print function is get rid of this line entirely and simply print word 1, comma, word 2. The comma here is telling the print function that we're giving it two separate variable names. It will take one, it will print it, then it will do a space automatically, and then it will print the second argument. So if we save and run this, we get hello Python back again. With that, I'm going to move on to the next section. At the bottom of that page there, if we press next, and we go down to the bottom and press next, we end up on a chapter called lists. So this is when we start getting a little bit more interesting with things. So far we've been dealing with single pieces of information, a single number or a single set of words, a single string. But quite often in real life, and therefore quite often in programming languages, you want to deal with something that contains multiple objects. The example I always come back to that I think most well represents real life is a shopping list. You go to the shops and you have a list of things written down on a piece of paper. You have one shopping list, but inside that list you have a set or a list of items that you want to buy. You can think of each item as a string, but we need in our language some way to describe the list as a whole. The way we do that in Python is with a thing called a list. A list is a built-in type in Python, and it's what's called a container. It contains other pieces of data. So I'm going to switch back over to my editor, and I'm going to make a new file. So I'm going to go to File, or not File, I'm going to click on the launcher, and put it here, and make another text file. So I've still got my old file here, but my new file here, I am going to rename it to list.py. So you saw list.py at the top, and then we can go ahead and close script.py. We don't need that one anymore. So I'm going to go ahead and make one of these containers. Like anything else, we start by giving it a name. You almost always want to give your variables names, and this is a really good way of making sure that you understand the kind of thing that's inside it. Same as before, we follow it with an equal sign because we want to give it some data. In the past, we would just write a number here, or a string, or do some kind of numerical work on some other data type. To make a list, we use square brackets. And I'll point this out at this point, that in Python, there are lots of different types of brackets used in different situations. It really matters which type of bracket you use. So far, we've used round brackets for calling functions. And here we're going to use square brackets to create a list. In between those square brackets, we put the things we want in our list. For example, cat, that's a string. We follow that item with a comma. Notice the comma's outside of the quotes. Dog, and let's put a number in as well, 261. So you see here we've got one list, one object that has three pieces of data inside it. Penguin, yeah, let's do a penguin as well. Thank you, Gareth. Penguin. You can have as many items as you want in a list. It's not limited to just 3 or 4. You can have lists with thousands of items if you so wish. You can also have lists with no items in. If we write it like that, that's a list with no items in. When we print our list, we can print it like any other variable. My_list. What's going on there? There we go. And we run it with Python list.py because our script is now called list.py. Run that and you see it's printed out the things that we put inside our list. It's got the square brackets printed out on the output to remind us that this is a list we're printing. It's got commas separating each item, and it's got quotes showing that these are strings. You'll notice that when you print it out, it uses single quotes, whereas when we made it, it had double quotes. That's because in Python, single quotes and double quotes are almost interchangeable with each other. There is a subtle difference between the two, but largely they mean the same thing. The convention is usually to use double quotes when making strings. However, regardless of what you make your string with, when it prints out, it will print with single quotes due to an older conventions. You know what conventions are like, they change every week. So have a go at that yourself. Make a list with some items inside it. Try putting some strings in there, some numbers, some floats, all sorts of different things. And make sure that you can print it out and it shows up on the screen correctly. Okay, so hopefully you've all managed to print a list out and that's all working for you. So we're going to move on and do something a bit more useful with a list than just making a block of a list and then taking that whole list and showing it to you on the screen. With a shopping list, you don't just deal with a shopping list on the whole, you deal with the items inside the shopping list. And so we need a way in our language to get access to the items inside. So we're going to make a new variable called myElement. Element is jargon generally for an item inside a list. Though the jargon isn't very consistent and you'll see it change later, but nonetheless it's often used for that. To get an item from inside a list, we write the name of the list and we follow it with square brackets. These square brackets that immediately follow the name of a variable are different conceptually to the square brackets we used when we made the list. If you've got square brackets by themselves with a space beforehand, that's you making a new list. If you've got square brackets and they immediately follow a variable name, which is a list, that's you accessing things from the list. It's you asking a question of the list. We can put something inside those square brackets, kind of like a function call, to tell it what piece of information we want. So we can write, for example, number 1. And we want to not print the whole list, we want to just print that one element. So, audience participation time for those who are listening. Who wants to let me know in the chat what's going to get printed out when I run this script? And don't be shy. Okay, we've got some cats and some dogs. So those who are saying cat might be confused about how it could possibly be dog. Let's run it and find out what actually happens. We do indeed get dog. The reason for that is that in Python, everything starts counting from 0. When you're talking about elements in a list, the first element is actually the 0th element. This is item 0, this is item 1, this is item 2, and this is item 3. Everything in Python starts counting from 0, and it is very consistent with that, and so it's a thing that's worth remembering. If we change this to mylist 0, at this point we should indeed get cat printed out. By that logic, if we want to get penguin for Gareth there, if we do it with number 3, we should get penguin printed out. Next, pop quiz. What happens if I put in 7? What's going to get printed out here? Any guesses? Great, everyone's telling me that it's going to print an error. I expect by this point many of you are used to seeing errors because Python does throw them at you quite readily if it thinks you've done anything even slightly wrong. Over time you will learn to appreciate and love Python exceptions and errors, but when you're learning it can feel like you're being told off. The thing to remember is that it's just trying to tell you that it doesn't understand what you're telling it, and that it's thinking you might have made a mistake and it's trying to give you the information you need to fix it. Let's run this and find out. We do indeed get an error. Like before, we start reading at the bottom line. It is an index error. It's called an index because this operation with square brackets is sometimes called indexing. The actual text of the message here, list index out of range, is telling us that the list, my list, the index we're asking for, 7, is outside of the range of valid numbers. We only accept numbers from 0 to 3, so 7 is way out.
5 is right out.
And so it's going to give us an error. There's no valid answer we can give here. Notice that because it failed on line 3, which is here, the program stopped running. It didn't print an error and carry on. It stopped entirely. It never even tried to print my element. As soon as you get an error raised, the program just stops at that point and tells you what it knows about its state at that moment. So we know that 7 doesn't work, but 3 does. So far we've dealt with 0, 1, 2, 3. Those all worked. We've tried bigger numbers, 4, 5, 6 and 7. Those don't work. What do you think happens if I put in negative numbers? -1. Who wants to have a guess about what -1 is going to do? Costas thinks penguin, and you're not sure. Ricardo's guessing the same thing. Let's find out. Let's run it. We do indeed get penguin. We get the last element. So the designers of Python realised that all the positive numbers, including 0, if you count 0 as a positive number, are potentially valid inputs, depending on how big the list is. But you would never have any meaningful meaning applied to a negative index. It just doesn't make sense because we are counting. We aren't dealing with mathematical comparisons and so on. So they realised that because all the negative numbers are free to be used and they don't have any ambiguous meaning, you can use negative numbers for whatever you want. And they decided that -1 should mean the last item. And in fact, beyond that, negative numbers just count backwards along the list. So -2 will give us 261, -3 will give us dog, and -4 will give us cat. If we try and go to -5, we'll see that once again, we get an error. I'm just going to clear my screen up so that it doesn't disappear off the bottom. -5 gives us an error because indeed there's no negative things over here. It doesn't just loop around forever. It's bounded by the size of the array. The last thing I want to show you on this section, which comes to Rachel's question, and I'll come to your question in a moment, Rachel, once I've covered the basics of slicing, and that is, so far with indexing, we have simply selected individual numbers. We've asked for this element, or another element, or we've asked for something which doesn't exist by going off the beginning of the list or off the end of the list. It's quite common with lists or with any kind of container which has things in an order to want to grab a selection of items. So let's say we wanted to select items dog and 261. We can do that by using what's called a slice. It uses the same kind of syntax as we have here. So we still use the square brackets, but inside the square brackets we tell it where we want to start selecting from and where we want to end selecting from. So we want to select from here to here. So dog is item 2, and we want to go as far as but not including penguin. No, sorry, dog is item 1, see, even I get mistakes. And we want to go as far as but not including penguin, which is item 3. The way I like to do the numbers here, because 1, 3 doesn't intuitively say to me those 2 items, is that I count the commas in the list as a way to remember what numbers I should put here. I imagine there's a 0th comma here, because 0 is invisible, so there's no comma. So this is comma 1, this is comma 2, and this is comma 3. So if I want to select from this comma to that comma, I do 1, 3, and that's going to give me this slice of the list. So when I print this, I get dog and 261. It's this subset of the list. Now, coming to Rachel's question, she asked, is there a way to get, say, the last 3 elements? Because if you do -3, -1, it will print the last 3 and 2 elements, but not the last element. Okay, so let's work up towards that question. So here we've got 1 and -3. If you remember earlier on, number 3 referred to penguin, but also number -1 referred to penguin. So we can replace that 3 with -1 and say we want to go from comma 1 to comma -1. A little bit confusing, I know, but the more you do it, the more you'll get used to it. So this is going to give us that same set of numbers. Likewise, this is comma -1, -2, and -3. We could change this to be -3, -1, and we print this, and we get the same bit of information. Now, Rachel was asking, how can we get it to include penguin as well? If we change this to a 0, that's not going to work. It's going to try and go from here to here. There's nothing to represent this comma at the end. It's going to try and go backwards. And in fact, if we try and do this, it will give us an empty list because we've tried to index backwards, and so it's just going to fail. If we want to go right to the end of the list, there's a special shorthand, and that is you just leave that space there blank. You say go from -3 to infinity, effectively. And so when we run this, it's going to do dog, 261, and penguin. Likewise, if you do a blank at the beginning, it represents the beginning of the list. So just a colon by itself inside square brackets means right from the beginning until right at the end. So have a go at these exercises on this page here, the lists chapter. So get through as far as the slicing section if you can. The last thing I wanted to cover in this list section is how you can go about changing lists. So far the lists we've made have been static objects. They haven't had anything changing in them as we've been using them. But of course, lists are most useful if you can use them to collect information as you're going through your program, collect information in them, and then do something with that information at the end. So let's change our list here so it just contains animals. Let's delete this my element thing because we're not going to be grabbing something out of it. And let's print my list. This is now just going to print cat, dog, penguin. Let's pretend that what we're doing here is making a list of the animals that we have on our very strange farm. It's got cats and dogs and penguins. Maybe it's our pets. Maybe we've got a pet penguin. Maybe we're that lucky. In order to add something to a list, we write the name of the variable and follow it by a dot. After the dot, we write append. Append is a function, and so it takes brackets to call the function, just like print does. Inside those brackets, we pass an argument, which is the next thing that we want to add onto the list. Someone give me an example of an animal to add in here. Rat, there we go, wonderful. So when we run this, we will see we get cat, dog, penguin, and rat, all our pets. So what's going on here is we are referring to our list. This is the object, this is our data container that we have. By writing .append after it, we are calling a special kind of function, which is often called a method. That's just a bit of technical jargon, but they are relatively interchangeable terms, method or function, on our object. So the fact that it's a dot followed by the name of the function says that this function is going to be affecting this piece of data. And depending on what the append function does, it is going to take whatever's passed in and do that thing to my list. In this case, the append function takes whatever is at the end and takes whatever is passed in and adds it to the end of the list. Emma is asking, how do you add rat to be the second in my list? So there's two ways of interpreting that question, and I'll try and cover both of them. One is that maybe you are asking how you can overwrite the second item. So maybe you want to take what would be dog, second being number 1, remember, and you can assign that to be rat. This is going to take this list, then it's going to find my list 1, which is dog, it's going to overwrite it with rat. If we run that, we see that dog has become rat. If, however, you want to insert it into the list, this is where I can't remember everything. I believe there is an insert function. Let me just Google it, because that is how we learn. Python insert list. It's into the Python 2 documentation. We want the Python 3 documentation. Here we have the list.insert function. It takes 2 arguments. The first argument is the position, and the second argument is the item. I can never remember which way round they go. So we want to insert at position 1, and we want to insert rat. So when we run this, we see cat, rat, dog, penguin. Hopefully one of those 2 things is what you are asking about, Emma. So if everyone's okay with lists, we can loop over them, we can grab items out, we can change things to do with them by appending to the end, and as we saw there, overwriting or inserting. So after the list section, we are on loops. So hopefully as we go through this, Olivia, I will explain the answer to your question, and I'll just read it out now so that I remember what it said. At the beginning of the loop section, you assign 2 variables called word with different strings. So does the variable store all the data that you assign to it? Okay, so I will go through that now. I didn't realise how soon it was. So let's make a new file, and let's call it loop.py. New file, text file, rename, loop.py. So the example I start with is writing something like, we've got word, hello, we're coming back to our examples from the beginning here, and then we print word. We run that, print hello, of course it does. We've done that several times so far. I think we're all comfortable with printing and variables now. If we want to print 2 things, we could do word equals Python, and then print word. When we run this, it runs line 1 to assign the variable, runs line 3 to print out hello, then runs line 5 to assign a variable, and then it runs line 7 to print hello. Olivia's question there was that we have assigned the variable word with the data hello, and then a few lines later we've assigned the same variable name with a different piece of information. What happens at this point in Python is that Python will forget anything about the history of the variable word. It will no longer know anything about the data hello. It will just know that word equals Python. Anything to do with hello from this point on in the program would be lost. It has no memory. It just remembers the most recent thing that you've done to it. The reason we get both hello and Python printed out is because we printed this one before we assigned the variable. This is one of the ways that variables in programming and variables in maths are different from each other. In maths, if you say something like a variable equals a number, you're stating some kind of mathematical fact that is then going to be always true for the rest of your analysis that you're doing. And so saying that word equals hello and then word equals Python doesn't make sense because it can't. A variable in maths can't have two different pieces of data associated with it. In programming, however, because we're going through sequentially, it does one and then it overwrites it with a second. The second thing that I hope you're thinking about this little bit of code here is that it looks very repetitive. We've basically written 2 lines of code and then written exactly the same 2 lines of code with one tiny little change. Every time we see something being repeated like this in a program, we should always think there's got to be a better way. Programmers are lazy. The best programmers are very lazy because they make the computer do the work for them. So let's get rid of this. Let's make this a variable words and let's make this into a list. So here, instead of 2 variables and printing one at a time, we've got one variable, which is a list which contains 2 pieces of data. And we're currently printing the variable word, which previously was referring to one word and then the other. But what we have here is a container, a list. What we conceptually want to do to this container is for each item in that list, we want to print that item to the screen. When you want to do something to each item in a list, we use a thing in Python called a loop, or in this case, it's called a for loop, because we are doing something for each item. And so we introduce that using the word for, and you'll see immediately it goes green and bold in our editor here, so we know that it's understanding what we're writing. I'm going to write it out, and then I'm going to explain what these different parts mean. So the way I like to think about the structure of a for loop is first we just look at this line up here. This is the part that introduces the fact that we are going to be repeating ourselves. There's 5 different things in this line. 1, 2, 3, 4, and then the colon at the end, number 5. In every for loop you write, the for, the in, and the colon are always there, always in that order, and always spelt exactly like that. Those are the fixed scaffolding that we use to construct our repeating for loop. The places that we have flexibility and artistic license inside our for loop are in the other 2 locations, here and here. I'm going to start with the second of those, between the in and the colon. This is where we write the thing that we want to loop over. It is the thing that is the list that contains items that we want to do something to each item of. We want to do something to each item inside words, and so we are doing something for something in words. The thing we're looping over goes in this spot here. While we are repeating ourselves, while we are doing something to each item in this list, we need to give a name to the current item. We need some way to refer to it. Earlier on, we were referring to items inside a list using square brackets and numbers. But because here we're just going to be looping over the list, we don't care what number we're at. We are just going to be dealing with one item at a time as we're looping over the list. And so to make that work, we have to give each item as we come to it a name. We're only ever going to have one item in our hands at any one time. So only have to give one variable name. And the variable name we're going to use is word. It doesn't matter what you write here. You can give this variable any name you like. Like before, we had variables called mylist and distance in miles. In the same way, this is just a variable name we're creating. So the first time around the loop, this variable name word is going to be pointing at the first item in the list. Then the next time it loops around, this variable word is going to be referring to this item in the list. So the first time round, it's going to print word, so it's going to print hello. It is then going to repeat itself, and it's going to print Python. Let's check that that works. There we go. It prints out exactly the same thing as it did before, but what was previously 4 lines of code is now only 3 lines of code. Now that might seem like a small saving, but bear in mind that we could be looping over a list that had 1,000 items in which case this would still only be 3 lines of code. Whereas if we were having to print each item individually, it would be thousands of lines of code, and that is a lot of writing. The final thing I want to point out about loops, is that the colon at the end of the line in Python always designates that the next section of code should be indented. And that is why we have these spaces at the beginning of the line here. Python uses the fact that this is indented to know that these are the lines we want to repeat. If we write print ... no, in quotes, there we go. It is going to repeat, it's going to print this line and then this line, then repeat itself and do those 2 lines again. So if we run this, we see we get ... hello, ... Python. Likewise, we can print end, and it will do ... hello end ... Python end. I'll just clear that. If we don't want this end to be repeated, all we have to do is unindent it, which you do by pressing backspace. Because this is no longer indented, this line of code will not be repeated. So when we run this, we get ... hello, and then ... Python. Then because the loop's finished, because words has run out of words, it then exits the loop, unindents, and then runs this line of code just once. So have a go at the exercises on the loops chapter. Do the first exercise on there first, and then if you've got time, move on to the exercise at the bottom of the page. Don't go quite as far as enumerating, because I'll be covering that in just a moment. There's a question there from Sam. We use 0 and 1 in last exercise. Why can't you do that again? So you're saying, why can't we do print words 0. I'm going to delete those. And print words 1. There's no reason why you can't do that. And if we look, we'll see that those 2 things come out exactly the same. But if we have hi, it's Matt here, then we'd have to do 0, 1, and do a 2, and then a 3, and then a 4, and that's probably not even the right number. Hi, it's Matt, and I didn't miscount it, so they have to do a 5. And so then it's done the right thing. Hi, it's Matt here. But we've had to copy and paste. We have to repeat ourselves. It's very easy to accidentally do that and not notice that you've got a number repeated. Also, if you've got lots of items, you have to do lots of lines of code. This will always just be those 2 lines of code, regardless of how many items you have in the list. It's quite common with lists that as you're collecting your data, you don't know whether you have 99 or 101 items. You just know that you have a container with information in, and you want to do something to each of those numbers. Maybe you want to double them, maybe you want to print them, maybe you want to email everyone that's in that list because it's a list of email addresses. You don't care about where each item is, you just care that there's a whole bunch in there. So yes, it certainly is possible, but looping gives us the flexibility that we wouldn't otherwise have. Kunal asks, what if we want to print each item twice? Let's have a look. I'm going to simplify this back to where we were. So here we do this and it prints each item once. If we want to print it twice, we can just write print word twice inside it. If you want to do it 3 times, well, we could copy and paste it again. But as you can see, we're probably starting to get the point where we're repeating ourselves quite a lot. So as Gareth says in the chat, you can actually make a loop inside your loop. You could do another for repeat in. And the way that you repeat things a certain number of times is by using the range function, range 3, print word. And here, when we run this, we get it happening 3 times and 3 times. So then if we want to do it 100 times, we could just change that to 100. And it would print each word 100 times. Yes, so range is a special word. Or rather, it's a built-in function. In the same way that print is a built-in function, range is a built-in function. The job of the print function is to take the argument and display it on the screen. The job of the range function is to take the argument and to give us back a list containing that many numbers. Ronald, I'm glad you asked, because that's exactly the next little section, which I'm going to cover now, and then we're going to have a little break for a bit because we've been at this for nearly an hour and a half. So let's have a look at how to answer Ronald's question. So they're asking, what's a concise way for accessing the current index / iteration inside the loop? So here we are looping over for word in words. The thing that we're looping over is this list. And when you loop over a list, the thing you get given each time is each item in order. If you want to get each item and its position, there's another function called enumerate, which means give numbers to, which when we run it, we get back the index and the item. It gets given this back to us in this form with the brackets and the commas and stuff, which is useful, but it means that we can't access those two pieces of information separately from each other. So if we want to get access to the two things individually, we can take the fact that enumerate is giving us back a pair of things each time. And so instead of having one variable name here, we can have two variables separated by commas, where I is going to be assigned the first thing that's given back, 0 the first time, and word is going to be assigned the second thing that's given back, hello. So then now if we print item I is word, it'll print item 0 is hello, item 1 is Python. Kunal's question. So that's a question about documentation. How do I find suitable function for my tasks? There can be 100 built-in functions which I don't know about. So let's go to docs.python.org, exactly as Gareth's linked there. So the page that I was on before was a page called built-in functions. So you can go to the search, built-in functions, and then you can never find them. So what happens here is I go to Google and I search for Python built-ins, which is almost certainly what Gareth did. And there's a link here to built-in functions. And we have here a list of all the built-in functions, which include print and enumerate and range. And that gives you information about what's going on there. In general, the Python documentation will have information about every single thing you can do with Python the language. It's not always easy to navigate through here. So on the whole, the way I get there is by Googling for Python followed by the thing I want to search for. Like Python insert into list is what I searched for earlier. That will take me to the Python documentation. I end up in the right place. The thing to make sure you're doing on the Python documentation page is the link, there's a drop-down menu with different versions. Make sure you're not on the Python 2.7 page. You'll be able to recognize it because the 2.7 documentation is all blue and it's got a big banner at the top. So in that situation, click on the link here and click on the latest number up at the top. And that will take you to the current version's documentation. Ronald asking a question, do you take a bigger performance hit if enumerating a long list versus just adding a counter inside the for loop? So no, the way that enumerate works is that it only generates the indices as it needs them. It doesn't generate a big list in advance, it just keeps track along the way. So it's doing that counter inside the for loop thing for you automatically, which means you don't need to worry about setting it to 0 before the loop and anything like that. It just does all that stuff automatically. So there's no performance hit at all. It does it all dynamically on the fly. That said, if you're worrying about performance with a really, really long Python list, you're probably at the point where you want to start looking at more advanced Python tools. So there's a set of tools called numerical Python, sometimes abbreviated to NumPy or NumPy, that will have the tools in there for doing that kind of stuff nice and efficiently. And also in our Python Introduction to Data Analysis course, which Gary was just asking about, where you go through a package called Pandas, which provides tools for doing this stuff nice and efficiently as well. So once you're at the point of worrying about performance, it's worth looking outside the built-in Python lists at what other tools are out there. Ronald, your question, is it possible to have local dummy variables inside a loop? Yes, it absolutely is. So I'll just demonstrate that quickly here. Let's make a variable called my number equals 42, and then let's just print my number. And when we run that, we see it prints the thing out and it prints out the variable as well. So you can introduce variables inside the loop and then they just sort of live inside that scope. So before the break, we were covering loops. That's how we perform the same operation multiple times. So to look at the example we have up here, here we were doing this line of code, which we've only written once, but it's going to be performed multiple times. So you write a line of code once and it runs many times. The other kind of thing you want to do to your code sometimes is to write a line of code which may or may not be run at all, depending on the context and the situation around it. The way we do that in Python is by using what's called a conditional. So let's make a new file and let's call it if.py, because that is the question that we are asking. If. Let's make a variable. That's how we start almost all of our scripts. Number equals 128. Nice computery number. The way we ask questions of our data in Python is by using the if keyword. This works similarly to the for loop keyword that we had before. And you'll see it's done the same thing where it's gone the green and it's bolded up as well. After the if, we are going to write something here, followed by a colon. Similar to the for loop where we had our scaffolding of the for, here we have the word if, and we have a colon at the end of the line. The question that we ask can be a whole bunch of different things. So I'm going to give an example, and then I'm going to let you have a go at running that yourself, and then I'm going to be building it up bit by bit. One of the simplest questions you can ask is to compare the size of numbers. So let's say, is my number greater than 100? So this bit here is whatever we want it to be, as long as it's giving back something which is true or false. This means greater than, and if you have something on the left and the right that are numbers, it will compare them and give us back true or false, depending on whether they are bigger or not. If this thing returns true, if my number is bigger than 100, then it will run whatever code is indented in the block below, which in this case is going to be our trusty print statement. My number is large. So if my number is bigger than 100, it will run this line. If my number is smaller than 100, it won't run that line at all. Oh, no, that's not what I meant to do. That's what I meant to do. Python if.py. 128 is large. Copy that code into your own script, into a file called if.py. Do the same things I just did there and make sure it prints out the same output. Then try changing my number to be different things. Negative numbers, numbers that are near to 100, numbers that are small, numbers that are much bigger than 100. See what you get, have a little play, and make sure you understand what answers it's giving you back. So I had a go here and I set my number to be 999 and it likewise printed 999 is large. But if you make this smaller than 100, like 50, and we run it, nothing gets printed out. It just does nothing at all. So if we wanted to print out something if our number is less than 100, we need to use a different operation. Instead of saying, is it greater than 100? Let's change this to be less than, and let's say, is it small? So now when we run this, it says 50 is small. As well as, I'm just going to do some stuff down here. So greater than means greater than. This means less than. Greater than sign followed by an equal sign means greater than or equal. Hopefully you can guess that that means greater than or, no, sorry, doesn't mean that at all. It means less than or equal. If you want to check whether two numbers are exactly the same as each other, you use two equal signs next to each other. If you use a single equal sign, it will give you an error. If you want to compare numbers, you use two equal signs. Are they equal? And if you want to check that they are not equal, you can use exclamation mark equal sign. Are not equal. Are they? Let's be grammatical. So have a go now at tweaking your if statement to use a different sign. Update the little comment so that it does something that it prints something that makes sense. Just have a little play with a few different operators, as they're called there, and see and check that they make sense to you, and then we'll be moving on to the next little section. If everyone's happy with that, everyone's had a chance to play around with different signs and check that it all works for them, then I'll move on to the next little section. I'm going to delete that because it's not valid Python code and it will give us a big old syntax error if we try and run it. It was just a comment. So a question you might have thought of is, I wanted to do one thing when it's greater than 100, and we say it's large. And then if we wanted to print something when it's smaller than 100, we had to delete the code and change it and make it say something else. What we'd usually want to do is to do one line of code if this condition passes, or a separate line of code only in the situation where that line of code doesn't pass. And we can do that using a statement called an else. An else statement in Python always has to follow an if. By that I mean you can have an if statement with no else, but you can't have an else with no if. So you just write else and a colon, and here we write print my number, if I could spell, is small. And so now we can run if.py, it says 50 is small, we can say 990 is large. If we do 100 exactly, it tells us that 100 is small, because 100 is not greater than 100, it is equal to 100. Okay, so Olivia has a question about the indentation here. So the indentation here gets interesting. There is a consistency across Python with how indentation is treated, so it's worth taking some time to understand what's going on. The way the indentation gets applied is any line that's indented is always associated with a colon before, and that colon and the indentation associates this block of code with this statement here. So we could print hello as well. So these two lines of code are indented, so they're associated with the if passing. This block of code is indented after following this colon, and so it's associated with this else. The if and the else are at the same indentation level because the else kind of sits next to the if, it's not inside it. And as I introduce the next statement here, you'll hopefully see why we don't keep on indenting, because you'll see that things get a bit messy. Because we might want to here do one thing if it's greater than 100, another thing if it's less than 100, but a third thing if it's exactly equal to 100. And for that, there's a thing called an else if. So here we say, if this thing's true, do this thing. Otherwise, if this thing's true, which let's make this my number is equal to 100, print my number is 100. And if that one's not true either, then it finally goes to the else. The reason you want to do that, and let's just check that works. Here we say, oh, we've got a syntax error. Of course, that was for demonstration purposes. In Python, you don't write else if, you write elif. It's an abbreviation they introduced for whatever reason. Here it says 100 is 100 because it's taken this number, my number. It's not larger than 100. It is equal to 100, and so it's printed this, and then it stops checking. When you're going through a chain of ifs, elifs, and elses, it will check from top to bottom. The first one that matches will run that block of code, and then it will drop out and not check anymore. And the reason you don't want to keep on indenting these things is because you can have as many elifs as you want. You can obviously have 0 because we saw that already. But you could also have a second one which checks if it's 42. So 100 is 100. 42 is 42. And 13 is small. If each of these times we had to indent our code, we would end up disappearing off the right-hand side of the page by the time we checked all our different conditions. And that is why we don't have to indent each block as we get to it. So for the exercise here, I want you to take this block of code, or a similar block of code if you've got different else's and ifs, and put it all inside a loop. Remember before I showed that you can nest loops inside of other loops? You can also nest if statements inside of loops, and vice versa. So take these lines of code, nest them inside a loop, and loop over a list of numbers, and check each of those numbers in turn and print out whether they're large or small or whatever else you want to check up on. I'm going to do it alongside you all on the screen here so that you can see how it works. And then I'll check back with you in a few minutes and then we'll be ready to move on to the next section. So this is the exercise at the bottom of the conditionals chapter. Okay, so we've got one person's finished now. I'm going to go through the exercise answer with you all now to explain how it's done so we can move on to the next section. But with any of this stuff, I'll give you information at the end to do on how to get in contact with us afterwards. But we've got a quick question here from Olivia, asking about the difference between the numbers and range. So in my example here, I want to loop over the numbers 0 to 9, and so I've used the range function to give us access to them. The other way we could have done that is by doing 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Both of those are going to give us basically exactly the same answer, with the difference being that we've had to type a whole lot more for doing it explicitly. Secondly, if we wanted to loop over the numbers 0 to 10,000, it would grind our fingers to the bone having to type it all out. Whereas doing it using range, we just do that, and it's immediately going to give us access to them all. So that's one of the reasons to use range instead. But we start off with my numbers equals range 10, which as we saw before, give us the numbers from 0 up to 10, but not including 10. So that gives us the numbers 0 to 9. The if statements inside here are exactly the same type of thing as we were doing before. Is a number bigger than 5? Is it less than 5? Or is it neither of the two, in which case, well, it must be equal to 5, mathematically. The thing that we have done extra here is that we have indented all of this, as you can see. And we've done that because it is now inside a for loop. We are now going to be repeating this set of if statements multiple times. We are going to be doing it once for each of the items in my numbers, which is the numbers 0 to 9. Each time around that loop, we are going to have the variable num. So inside each loop, the variable num is going to be referring to first the number 0, then 1, then 2, then 3, etc, etc. And so it's that number which we are comparing in each of these situations and printing out. So when we run this code, we get, first of all, we get the first item from range 10, which is 0, which goes into the variable num, which gets compared to this. It is not greater than 5, so it goes to this one. It is less than 5, and so it prints out less than 5. Does the same thing for the rest of them until it gets to number 5, at which point it's not greater than, it's not less than, and so it does this block. Then it carries on through, and then all of the rest of the numbers are matched by the first block there. So this is to show that you can put if statements inside for loops, and it all just kind of works how you expect. In this block here, you can put some blank lines in here. You can look at this block of code, and even outside of the context of you knowing that you're inside a loop, this section of code still makes sense in itself, as long as you trust that there's a variable called num that you have access to. It doesn't matter to these lines of code that they're inside a loop. They are just doing the same if, else, elif, and else thing that they always do. In our case, however, we do want to make it clear that it's inside a loop because that's how we know that we're looping over the numbers. You'll use if statements a lot in your code. I find it quite uncommon to use elif. It's a corner case catching tool rather than everyday tool, but certainly I use a lot of if statements. I use a decent amount of else's, and I always use loads of for loops in my code. That is one of the most common things that I do in my code, is looping over stuff and repeating myself for each item inside a list. And Kunal asked, there are a lot of variations of if in Python, right? Yes, there's ifs and elifs and else's, and there's lots of different things you can put here. It gets quite complex to allow you to explain to the computer all of the different things that you might want to do. So I'm going to move on to the next section now. So after the loop section, I'm behind on the notes on the screen here. And after the conditional section, we move on to dictionaries. I'm going to make a new text file again. It's always good to make a new text file for each section of code that you're writing. And I'm going to call this one dict.py. Dict is the usual abbreviation for dictionaries in Python, and you'll see that cropping up a lot. So get used to dict meaning dictionary. And now I'm going to explain what a dictionary is. So a dictionary is similar to a list. Lists were containers which held multiple pieces of data. They held them in a certain order, and we could access them either by looping over the list or by asking for specific items in the square brackets, asking for item 3 or 0 or -2. A dictionary works in a similar way. It's a container which holds multiple pieces of data, but rather than holding them simply linearly all in a line and giving each of them a number to refer to it, we instead give each item in our dictionary a name or a key which we use to access it. You can think of it a bit like a physical dictionary where you have a bunch of words and their definitions. You look up the definition of a word by finding the word in there, and then the definition is associated with it. Let's look at an example now to see how it looks in code. So I'm going to make a dictionary which contains animal sounds, continuing our animal theme from earlier. So I'm going to make a dictionary called sounds, and inside this I'm going to make a dictionary. A dictionary is made using curly brackets. Now those are different to the square brackets, and they're different to the round brackets. Curly brackets in Python almost always mean I am making a dictionary, in the same way that square brackets by themselves meant I am making a list. So once again, inside the curly brackets, that's where we put our contents of our list. Each item in a dictionary is a pair of items in this case. So we have here cat and meow. Those two things together, separated by a colon, are a single item in the dictionary because each item in the dictionary is a key and the value. You can add multiple here, for example, dog and woof. Sorry, that should be a colon. So here we have one item, which is this pair of things, and another item, which is this pair of things. Each item in a dictionary is made up of two parts: the key, which goes before the colon, and the value, which goes after it. I tend to, when I write dictionaries out, spread them over multiple lines because I find it a little bit easier to read. When you've got this many symbols hanging around, it can get a bit messy to the eye. So one thing you can do with dictionaries, and in fact with many things in Python, is spread them over multiple lines. So I'm going to put a new line in there, a new line after that comma, and a new line before that closing bracket. So this is exactly the same thing, it works in the same way, but it makes the fact that this item and this item are separate a bit clearer. Oh, sorry. So I'm going to ask in the chat, I need more than 2 items for my list because 2 is a bit boring. What other animals and sounds shall I put in here? We had penguin earlier on. What sound does a penguin make? Because I don't know. Gareth? Apparently they go meep. And we also had fox. There we go. Thanks, Maddie. Now, what does the fox say? Screech. That sounds about right. I had one in the garden the other day and it made a very horrible noise. And we've got a duck. Duck. Going honk. And we have a sheep. And what noise does sheep make? Bah. Lots of A's. There we go. So, once we've got our dictionary full of items, each of these is an item, we have a key and a value associated with each. We get things out of the dictionary in the same way that we did with lists. So we're going to make a new variable cat sound, and we want to get from this dictionary the sound of a cat. So we go to sounds, we use square brackets, but this time inside the square brackets, we don't write the number of the position of where the thing we're looking for is. We put in the square brackets the key of the item we're looking up, for example, penguin, and it will give us back the associated value, which in this case would be meep. So if you put cat in there, it's going to give us back, hopefully, meow. Let's print it and check. Cat sound. Oh, no, wrong file. Python dict.py. Invalid syntax. I've missed a comma there. Very easy to do. Cat sound. I made a typo. Tell it's getting late when I'm making that many typos. It prints out meow. It's looked up the key we put in. It looks up in here. It's given us meow. If we change this to be just sound, because we're going to be tweaking what animal this is, change it to fox and print that, it makes a screech noise. So have a go at that yourself. Copy in that dictionary, try grabbing items out of it, and also see what happens if you ask for an item from a dictionary that isn't in there. For example, if you make a typo here, or you ask for an animal which isn't in there at all. Olivia asks, do you have to have a comma after the last key in the dictionary? No, you don't. That works just as well. The reason I tend to put a comma after the last item when each is on its own line is because when I add a new item, I only have to worry about this line here. I don't have to remember add a new item like fish, bubble, and then, oh, I missed the comma there, which is exactly what I did wrong earlier. So I tend to always put a comma at the end of the line to avoid me making that mistake. Also, when you come to use version control like Git later on, it makes your differences between files a little bit neater to read if you have a comma at the end of each line. But largely, it's a matter of style. I will sometimes use one or the other. Gary is asking, why does the dictionary use square brackets to search the items, not curly brackets? So this is where it gets a bit confusing with Python and the different kinds of brackets. Or at least it does seem confusing at first, but I'll try and explain the logic behind it. So the reason that we use different types of brackets for creating the different types of objects is to make it unambiguous when Python is reading the file what kind of object we're trying to create. And that is why right from the start, you have to choose when creating something, whether it's going to be square brackets to be a list, curly brackets to be a dictionary, or there are other types of brackets which get used as well. As for accessing stuff from lists, it's not ambiguous what we're asking for with the square brackets here, because each type of object can only be searched in one way. So if this were a list, then Python knows that square brackets is asking for it by number. This is a dictionary here, so Python knows that square brackets is asking for an item from it by its key. That allows Python to always use square brackets to mean, give me something out of this list. And the syntax would always look the same, so you can look at the line like this, and you don't really care whether sounds is a list or a dictionary or some other exotic type of data. All you care about at the reader of the code is that we know this is something which must contain stuff because we're asking for something from inside it, and we trust that the thing, in this case sounds, knows how to interpret it. The other reason is because there are lots and lots of different kinds of containers, beyond lists and dictionaries, which have their own syntax here. In more advanced Python tools, there are other tools which don't have their own individual way of creating with special brackets, but they are accessible using square brackets. And so by allowing square brackets to be the generic syntax for give me something from inside this thing, it makes the language nice and extensible. Now I'm going to move on to the next little section. Like we did with lists, we created our list statically, we've created our dictionary statically, it's fixed in the file. With lists, we could add items into it by using append, and we also saw the insert function when I was answering someone's question. Dictionaries have a similar ability. So I'm going to get rid of sounds fox. If we want to add a new item into a dictionary, we do it just by accessing it. So can someone in the chat give me another animal and a sound? Tiger. And what sound do tigers make? Grr. Okay, cool. That's scary. So you do it by accessing the item as if you're trying to get it out. But if it's not in there, because we've given it a value on the right-hand side, it's going to insert that into it. And that means we can now do sound equals sounds tiger, and this will print out grr. Ronald is asking, can you modify the name of the key without changing the value? So we can change the contents of a value by doing this same thing. We could have put, for example, duck there and maybe make this a scary duck. But if you want to change a key, it's a little bit trickier. So you would have to, for example, let's say we've called this, let's say we made a typo and we called Tigger by accident. We would have to make a new one, sounds tiger equals sounds Tigger. And then we'd have to delete sounds Tigger. So it's a two-step process. So we put in an incorrect name there. We've then renamed it, and we can access it by the correct name, and that should work. So have a go at that yourself. Try adding in a new entry into the dictionary. Make sure it makes sense when you're doing it. Try overwriting existing variables, and I'll come back in a minute or so to move on to the next section. I'm going to cover the last section on dictionaries here before we move on to the last chapter in the course today. We're doing well for time, I think. And it's following the same kind of pattern to what we did with lists. With lists, we looked at making them statically, getting items out of them, changing items inside them, and then we moved on to looping over them. And when we loop over a list, we repeat each line inside the loop body once for each item in the list, and it works in a very similar way with dictionaries. So let's put tiger inside here, because I don't want to leave any animals behind. So when we loop over a dictionary, let's find out what happens. The nice thing about Python looping and for loops is that they are very, very generic tools. You can loop over lots and lots of different types of things in Python, while the syntax you use basically stays the same. It doesn't matter whether you're looping over a list, or a string, or a dictionary, or as you'll see in the next section, a file. The words that you write on the page look very similar, and it's a general way of repeating yourselves depending on the kind of container that you want to loop over. So here we want to some kind of thing in sounds. And I'm saying thing because when we looped over a list, it was unambiguous what we'd get back. We had one item at a time. Here we've got two different things. We've got a key and a value, or potentially the whole thing all at once. And let's pretend we don't yet know which of those we are going to get back. And let's print thing and find out what thing is. So when we've looped over this dictionary, we've said we want to have whatever it is that looping over it gives us, and Python's decided that for us. And it looks like, looking at the output, that when we loop over a dictionary, we get back the keys from that dictionary. Cat, dog, penguin, fox, duck, sheep, fish, tiger. Those are the keys in our dictionary. It hasn't given us access to the values. So we now know that this isn't thing, this is a key. Again, the variable name doesn't matter, but it's good to use one that's descriptive. But better than that, actually our key isn't just a key, it's an animal. And suddenly this loop here is starting to read a little bit more like a human would understand it. For each animal in our sounds dictionary, print out the name of the animal. And that's what we get over here. If we want to get access to the values, there is a thing we can do where, like with the append function to a list, we do a dot values after the thing we're looping over, and that's going to give us back each of the values. So we now change this to sound and sound. Now it's giving us back each of the values one at a time. If you want to explicitly loop over the keys from the dictionary, like we had before, we can do that too by writing keys there and changing this back to animal. So if you have sounds by itself, it gives you back the keys. If you do keys explicitly, it gives you back exactly the same thing. Sometimes it's good to do it this way because it reminds you that it's giving you back the keys. The final thing that you sometimes want to do with dictionaries is not get back a list of just the keys or just the values. Sometimes you want to get back both of the things at once as a pair. Because as you can see in the output over here, the keys and the values have been disassociated from each other. There's no way to know which sound and which animal are related to each other. In order to get them coming out in pairs, there is a third thing that we can pass in here called items. Remember I said earlier that an item in a dictionary is this pair here, or this pair here, or this pair here? That terminology carries across to this function here. So when we ask for the items, it's going to give us back cat, meow, etc., etc. So let's have a look and let's call this thing again. And when we print this, we see it gives us back these pairs. Now these pairs work in a very similar way, well in fact exactly the same way as we saw with enumerate earlier. With enumerate, we solve the problem of it printing out it with the brackets and the quotes by putting two variable names in here. And we can do the same thing with items. So we can write, for example, for animal, because the first thing we're getting back here is the animal, comma, sound. And then our print statement, we can say animal goes sound. And when we run this, it writes cat goes meow, dog goes woof, etc., etc. This is a very common thing I do, to be able to loop through a dictionary and get access to everything. But each iteration of the loop, I'm only being given access to one of the items, so the key and the value at a time. But that's really useful to allow me to go through and do something to each of the things inside the dictionary. Some questions in the chat there. So Rosalia is asking, my list is printing in a different order. Is that an issue? No, it's not. So until Python 3 point something, 3.4 or 3.5, the order of a dictionary wasn't preserved. So the order you wrote it here could easily end up being different to the order it's printed out at the end. As of a recent version of Python, they've changed it so that it's always preserving the order. But in general, it's good to not rely on the order of a dictionary. Treat it as a bag you've thrown a bunch of items into, and each time you loop over it, you stick your hand in and grab them in a random order. Assume that's the case, even if they end up coming out in the order you put them in. That's the safest way. And Amanda asks, can I assign more than one value to a key? You can. So let's look at dog. So here we've got dog making a woof noise. If we wanted to assign a list of values to it, we could say woof and bark. And so now when we print it out, we get dog goes woof bark. Of course, this isn't a very nice way of printing it. So we might want to have an if statement in here, which has something like if animal is equal to dog, animal goes sound 0 and sound 1. Make that a little bit bigger. So here we have assigned dog to have 2 values, and so when looping over it, we check if we're on dog. If we are, then we print both of the sounds. Otherwise, we print the one sound. And we look at that, and we see dog goes woof and bark, and the rest are just carrying on. So here we're combining together dictionaries, loops, and if statements all together. So have a go at running those things yourself, looping over items, keys, and values. Check you're happy with it, and then I'm going to be moving on to the final section in the course today, and that is reading files. Just take a few minutes there, and then I will be moving on. Salim, yes, the something going something is a strange Englishism which is a bit weird to translate. So we could instead write animal makes this noise. And then it says penguin makes this noise, meep. Fox makes this noise, screech. If that's easier for you to read or something, then go ahead and change it to that, and that might make it a little bit easier to understand what's going on. Emma asks, can you make the code detect that the dog has 2 sounds? Yes, we can. There's a few ways we can do it. I'm going to try and not use a way that's too confusing for new learners of Python. But we could, for example, do if there's a thing you can do called isInstance in Python, which checks what kind of data something is. And we could say if isInstance sound list. Let's see if this works. It then does the correct thing for dog. So this is saying if sound is an instance of the list type, then do this. Otherwise, just print it out on the screen. That's one way to do it. There is, in general, lots of ways to do things in most programming languages, and part of the job is working out which one's right today. The last thing I want to cover here in the dictionary section is right at the bottom of the dictionaries chapter. There's a little list of things that you can loop over. And I just want to draw your attention to that because we're going to be building on this in the next section. But to reiterate, when you have a for loop, the thing that you put in this section between the in and the colon can be a list or a string or an enumerate function, or we saw range earlier, which isn't listed here, or dictionaries, or the keys of dictionaries, or the values of dictionaries, or the items from dictionaries. All of those things are possible, all with exactly the same syntax on this line here. The only thing you change is what you're looping over. Python has a very extensible and generic way of looping over things. So much so that we can loop over objects that aren't even part of the language itself. For example, files. So the last section we're going to do today is this last chapter here, files. So I'm going to make a new file, text file. I'm going to call it, maybe confusingly, file.py. And in here I'm going to also make a file. I'm going to make a second file, which I'm going to move down here. And I'm going to call this data.txt. And inside here I'm just going to write some, this is a file. So I made 2 files here, a Python file and a text file. And what we're going to do is write a program which can read this text file and display it on the screen. So the way we start this is by writing open and then the name of the file that we want to open. The file by default has to be in the directory that you're running your code from. In this case, it's data.txt. In order to handle the file being automatically opened and closed, we need to introduce a new thing called it's called a context manager, but they're sometimes called with statements. And that's because it starts with and then has asf. And what this is saying is open this file, make a new variable called f, which is going to be referring to this file. It's our handle, which we're going to use to, hold on to refer to this file. And the with part is saying, because we've got the colon here, everything inside the next block is dealing with it while the file is open. And as soon as we finish and unindent, the file will be automatically closed. The reason to keep track of whether files are open or closed is because A, you can only have so many files open at once, and B, in some operating systems, only one program can have a file open at once. So it's good to be careful and judicious about closing your files when you've finished dealing with them. And that's what this with statement handles for us automatically. So with the file being open, we can do something to it. And the most basic thing you can do to a file, as we saw, as I was alluding to before, is loop over it. So we can write for line in F, print line. We then run our script, what's it called, file.py, and it's printed out, hello, this is a file, almost exactly as we saw there. The thing that's different between the two is that here we have no blank lines, but here we've ended up with blank lines after every single time it's printed. The way to fix that, or the reason that's happening, is because every line in a file has the word HELLO, and then it actually has an invisible character at the end of every line called a new line or a carriage return, which tells it to go move on to the next line. Now that's fine, except that the print statement also always prints something and then does a new line for the next time. So we're getting a new line being printed from the file itself, and another new line coming from the print statement. So we end up with two new lines after every thing that we print. To fix that, there's a few ways of doing it. The easiest way is to tell the print statement not to print its own new line. So you can do that by passing a second argument to print, the end argument, and just give it an empty string. By default, end is /n, which means print a new line. If we tell it to do nothing after printing each line, it will then print our file correctly. I'm getting something funny happening there, so I am going to do, ignore me for a second. There we go. So we say, hello, this is, and then we say a file at the end. So it's printed it. It hasn't printed a new line after a file, and then it's printed my prompt straight away afterwards. So that looks a bit messy. So let's see if there's another way we can do this. So maybe instead of suppressing the new line that's coming from the print statement, we instead suppress the new line that's coming from the file. So the way we can do that is we can take line and we can assign it to be line, but there's a method you can call on all strings called strip. And what strip does is remove any spaces or new lines from the beginning and the end of the line. That will therefore get rid of the new lines that are coming from the file and leave us only with those coming from our script here. And that means we can move back to here and we can run Python file.py now after saving this one. And now it does the correct thing. So what we've done there, we've called the strip method on each line of our file, which has got rid of the extra new lines that are kind of hanging around. So have a go at doing that yourself, reading in a file. Doesn't matter what file you put here, as long as it's in the same directory as everything else. And make sure you're happy being able to read it in, stripping the new lines that come with the file, and then printing out each line. I'll just cover now the last thing I want to talk about in files, since we've only got a few minutes left of the session. And that is how files deal with data types. So I'm going to change my data.txt down here to have some numbers in. 42, 9013. If we now run this again, we get those numbers printed out. Now we know that we're looping over numbers. We want to be able to do something like print line times 2. Maybe we want to double each of these numbers to get 62, 18,000 and 26. So if you run this now, see what happens. We get something strange. Instead of doubling the numbers to be 84, it's doubled the string. That's very strange. The reason it's doing that is because it's reading everything from this data file as if it is text, even if it is a number. If we know that everything in here is a number, then what we need to do is, once we've stripped it, to also convert it to a number by using, for example, the integer function. This is going to take what was line with new lines, strip off the new lines so it's just the digits, then convert it to be an actual integer, so that then we can do mathematical operations on it. This is like the difference between 2 in quotes and 2 by itself. So now when we run this, it does the correct thing. So question there from Salim about art of knowing all the things that you need to do. As Gareth says, it just comes with practice. The more you do it, the more you learn stuff. I've been doing Python for 10 years or something now, so this stuff just becomes second nature the more you do this stuff. You shouldn't expect to be an expert at Python after a 3-hour session one afternoon. It takes time. But there's lots of people learning with you, and there's lots of people who can help. So that's the last thing in the file section. The very last summary section here has on it a big difficult exercise, which I'm leaving as a homework exercise for you if you'd like to carry on with this after the session. With that, I'm pretty much going to wrap up. Thank you very much for attending, and I'll hopefully see you all soon. Dictionaries and lists and things like that. We'll be working through some slightly more intermediate material as a follow-on from that course. Now, the first page of these notes here go through setting up Jupyter Lab. In the landing page, there was a link to some videos, which hopefully you've had time to go through to make sure everything's all set up. Otherwise, if you've been to our beginning Python courses, then you should all be ready to go anyway. But I'm going to go through that just in front of the room now to make sure everyone's up to speed. Give everyone a minute to catch up, and then we'll launch into the actual material. So the first page of the course notes here are mostly going through getting Jupyter Lab set up. So I'm going to scroll down as far as the setup, and then there'll be a little bit of demonstration. So I've switched tabs now to Jupyter Lab. This was launched through Anaconda, and I've set it up in the same way as I showed in that video. So I've got a text editor on the left-hand side, in which I've already written a short Python script. Hopefully everyone here is comfortable with that level of Python at the very least. On the right-hand side, I have a terminal. In that terminal, I can run, for example, Python, and then space, and then the name of the script, which in this case is script.py. Press enter, and it runs it and prints out what the script does. So throughout the course today, whenever we're doing exercises, I'll be asking you to do the exercises in a text editor and run them in the terminal. That's how you're going to be working on the exercises today. But in the course today, we're introducing a potentially new tool called the Python console, which I've opened up in a second tab on the right-hand side as well. So if I click on the Python console, this is where we can write and run Python code interactively. It works very similarly to a Jupyter Notebook, if you've used one of those, but we can write in here at the bottom, print, and then put something in the string, hello. I then run the cell with a shift enter. It prints the code and prints the response. So when going through the examples in the session today, I'll mostly be working in the Python console here because it lets me quickly iterate, but I might be using both modes at various times. So I'm just going to give you a minute now to make sure that you can A, write a Python script and run that Python script in the terminal, and B, that you can load a console and run some Python code in there as well. So as to your question, David, when you're writing code in the console, when you want to run it, you have to hold down Shift and press Enter. It might also be that Control Enter works. No, Control Enter doesn't work. So you have to hold down Shift and then press Enter, and that should run that bit of code. It looks like most people have managed to got things working now. So I'm going to just do a little bit about how the console works. So I imagine that most of you haven't come across the console before, so I'm just going to show you some of the features that it provides, which I think are quite useful. So I'm going to start off by making a list with some animals in it. So cat and dog. Normal Python list, something we've all seen before. Can I run that with Shift Enter? So L is now a list type. So if I want to do something to this list, we learnt about in the beginning Python course that we can call list.append on lists to add stuff to the end of them. So if we do L dot, but if we pretend now that we don't know what functions are available on the list, if you press the tab key just once, just press the tab key on the keyboard, then you get popping up a list of all the functions that can be completed. So you see there's the append function, that is the one that we want to do in this context, to add something to the end, as well as clear, copy, count, etc, etc. This works with more than just lists. This will work with any data type in Python. So you can always use this as a quick way of finding out what you can do with a particular piece of information. In our case, we want the append function, so either click on it or press enter. Then let's pretend that we don't know how to use the append function. We don't know what arguments it takes, and we don't know necessarily exactly what it does to the list. The Python console provides a way of finding help directly inside the console without having to go away and Google. And to do that, if you follow the name of the thing you want to find out about with a question mark, and then run that cell, and I run that cell with Shift-Enter, you'll see it prints out directly in line a bit of information and context about what that function does. It does use some somewhat technical jargon, and for example, it tells you what the append function does by using the word append, which is a classic mistake. But it tells you that it's a function which takes one argument. The slash there's a behind the scenes thing, which means doesn't take any more arguments. But it tells us that whatever object we pass in, it appends that object to the end of the list. And that's a useful thing to know exactly what it does. It adds it to the end of the list, rather than the beginning or somewhere in the middle. That means we can go ahead and use it. So if you press the up key on the keyboard, we can then, that brings up the previously run command. You can keep on pressing up and you can cycle through. Up and down cycles through the recently run commands. Delete the question mark, call it like a function, and pass in something like horse. If we now run that with Shift-Enter, the list has been affected, and it's hopefully added horse to the end. If we want to have a look at what is inside the list now, of course we can write printl, as we've seen previously, and we can do with normal Python. But if you just want to have a quick inspect of what an object looks like, you can just type the name of the variable, nothing else, and then run the cell with Shift-Enter, and it will display on the screen the contents of that variable. So it will show us what's inside it. So if you have a little go at that yourself now, using the question mark, making sure you can display variable names just by writing the name of the variable directly, and see if you can get tab completion working. So we'll move on to the next section of the notes. I'm going to switch back over to the notes. At the bottom of every page, there is a next button. If we click on that, we end up on the next chapter. But let's go through string formatting and see what Python can do to help us. So if we go over to the console here, and let's have a look at some features. So these are features which were added in relatively recent versions of Python. There's always been ways of telling Python exactly how you want your strings to be formatted, and including variables in your strings as well. But they've added several over the years, and so I'm going to be showing you today the most up-to-date and most recent way of doing it. But first we're going to start with plain old print functions. So let's make a variable, something called mynum, and let's make it the number 42. We can, of course, print 42, and that shows up correctly. It does the number 42. No, sorry, I meant to say we can print mynum, and we run that, and it prints 42. So it's accessing the variable as we expect. We can also, with print functions, put in multiple arguments. So we can say something like mynum is, and there's a second argument, pass in the variable. And that prints out the first argument you pass in, automatically puts in a space, and then prints out the second argument you put in. So this works perfectly well. There's nothing wrong with doing Python coding this way. The potential issues are that it's automatically put the space in, and so maybe you don't want it to put the space in. You want to format things a little bit more neatly. And the second thing is, if you get lots of variables and lots of things going on, this can end up being quite a long string, and it's hard to see by reading the code what your output is going to look like. And so Python introduced a way of including your variables directly inside the strings, so you can see how it's going to be displayed at the end without having to construct it out of separate pieces. So to do that, we use a print function, and we write a string as we ever did. But to enable this special mode, you have to write an F just before the opening quotes. So you write an F and then the pair of quotes, and then inside the quotes we can use the special mode. So we write mynum is, but then instead of doing a comma and then passing a second argument, we can, directly inside this string, use curly brackets. Now previously we've seen that curly brackets are used for making dictionaries. This is a completely different use of curly brackets. It's a common problem in programming that there's only so many different types of brackets that they do end up being used for different purposes. But But inside those curly brackets, we can just directly write the name of the variable that we want to use. So we just write my_num inside those curly brackets. And when we run that, it's going to write this and the space, and it sees the curly brackets and it's going to replace those with the value of the variable that's inside them. So run that with Shift Enter, and we get the same thing printed out. But here we've constructed one string which represents what we want the final product to look like, but we put placeholders in for where we want our variables to be replaced. You can do more complicated things, so we can write answer equals 42 and pi equals 3.14159 probably. Two variables there. And I can then print them out in an F string, all in one F string. So I write print, open and closing quotes, again putting the F in front of the string. And inside here we can write the answer is curly brackets answer, the name of the variable. And then outside again, and pi is curly brackets, the name of the variable. And so it's going to replace this with the variable answer, this with the variable pi, and we'll print out the answer is 42 and pi is 3.14159. You can put more complicated things inside the curly brackets. You don't have to just put a plain variable name. So I'm just going to copy and paste a dictionary in here. So here we have a dictionary which has one key, which is answer, and a value 42, and one key, which is pi, and the value is 3 point whatever. If we want to print that using an F string, we can do our F quote quote thing again, and we can copy our thing from before. But this time inside the curly brackets, we want to get the value out of the dictionary. So the dictionary is called myDict. We use square brackets, and then we ask for the key from the dictionary. And we do the same thing here. myDict, square brackets to get the key, and we ask for the string pi. You'll notice here that I've used single quotes to get the string for the keys, to get the keys from the dictionary, and that's because I've used double quotes for the outside. So you have to make sure you don't use a double quote if you've made your overall string using double quotes. Otherwise, it's going to think you're closing the string and it will get confused. But when we run this, we see we get the same thing printed out. So just spend a minute or so having a go with that, and then I'm going to set you the first exercise to make sure that the first exercise goes smoothly. And that's because we're going to use the first exercise throughout the course today, build up on it slowly, so we want to make sure that everyone's set in the first place. But first, have a go at doing this F string formatting and make sure that it's working for you. So if you go to the bottom of the string formatting chapter, and I'll do the same on my screen, you'll see a big yellow box with a big long looking exercise in it. So inside here there's a big chunk of code which we are going to be working on and improving as we're going through the course today. We're going to be using it as the primary bit of code to do the exercises on, to learn and play around with the techniques that we're learning about. Luckily, this first exercise is nothing more than take this bit of code and run it. So I'm going to do the same thing as you will do. I'm going to copy this code. I'm going to move over my text editor. I'm going to make a new file, a new text file, put it over here. And I can close scripts.py. I'm going to paste all that code into that text file. I'm then going to rename it to encode.py. Because what this is doing, it is going to take a string and it's going to encode it into Morse code. Now the layout on the screen looks a little bit funky because of the line wrapping. But this up here is a dictionary which tells us for each English letter how to convert it to Morse code. So the first exercise is to take this code, paste it into a file, call it encode.py, and to then, in the terminal, not in the console, but in the terminal, to run it using Python, or if you've been told to, Python 3, encode.py. And you should get printed out incoming message, SOS, etc., and then Morse encoded dots and dashes. So to take a minute now to do that same thing, copy that from the example in the notes, paste it into a file called encode.py, and make sure you can run it in the terminal. Once that's all there, then we can move on and start learning about the first of our new techniques for this course. I'm seeing a few questions in chat. So the first one from Bryony, your syntax error. If it's saying that F strings are an invalid syntax, then there's a chance that it's because you're running on Python 2. So if you're getting that, when you run your code in the terminal, instead of writing the word Python, run the word Python followed by a 3, then a space, and the name of the script. And that will hopefully give you something that's working. F strings were only introduced in a recent version of Python. So functions are the first in the journey that we're going to be taking today. The general theme of the workshop today is learning about how you can take your scripts that you've been writing so far and package them up, make them reusable, make it so you can share them, and make it so that it's harder to make mistakes when writing code and when people are using your code as well. That's the general journey we're taking, and functions are the first step along that route. So functions allow us to reuse code. That's their primary purpose. One of the biggest sources of mistakes in programming is when you copy and paste some code and you make some kind of mistake when you're tweaking your pasted version, and it makes a mistake and then your code gets something wrong and it's really hard to spot. Functions are one of the ways that you can avoid that problem entirely and make it so that you can have a single unit of code which can be used in lots and lots of different contexts throughout your code base. So I am going to go back to my console over here on the right, and we're going to have a look at how we can learn about functions. So I'm going to start off with an example not using functions, and then go through the route of turning it into something which can be reused. So let's start off with writing a little bit of code which is going to add together the contents of two lists. So we make a variable A, which has got some numbers in it, 1, 2, 3, and 4, and a variable B, which has got some other numbers in it, uninventively 5, 6, 7, and 8. When we run that, we've got our two variables ready to go. Then we're going to write our bit of code which is going to add those two lists together. And by add the lists together, I mean add the first two elements, i.e. add 1 and 5, put that into a new list. Then add 2 and 6 together and put that into a list, add 3 and 7, put it into the list, and then add 4 and 8. So we're going to be adding the lists together pairwise. In order to have something to put our result into, we have to start off by defining an empty list, which I am going to call C. Then we're going to write a loop which loops over A and B and adds them together and puts the result into C. So we write a for loop, and I'm going to write A element, B element. So A element will represent 1, 2, 3, and 4. B element will represent 5, 6, 7, and 8. For those two in, and I'm going to use a function called zip here, which you can pass multiple lists to, and it allows you to loop over both lists at the same time. So we pass A and B into the zip function. This is going to loop over the two lists simultaneously. The first time around the loop, it will give us the first item from each. Next time around the loop, it will give us the second item from each, and so on and so on. We then append our result into C, and we compute our result by adding together ALM plus BLM, if I can spell. We run this code here, and it's going to go ahead and do the calculation. Finally, we print C to have a look at what's inside it, and we see that C contains the correct result. We're going to be using this bit of code in a few examples today, so make sure you understand what's going on here. But with that, we're going to have a look at how we can turn this into something which is reusable. When you're writing code, whether it's a small script or something on a much larger scale, doing a large piece of scientific analysis perhaps, almost all code can effectively be broken down into three main sections. The first section is the bit where you read in your data and prepare your inputs. This is what we've simulated here by defining these two lists. The second chunk, and often the largest chunk of your script, will be the part where you do some kind of analysis to your data. Here we're simulating our data analysis by just adding together the two elements. This is where you might run some kind of simulation or a model or do some kind of numerical analysis to your data. The third section that's present in most code bases is then doing something with the output of that simulation. This is often something like save it to a file. It's often a very short part of your code. But thinking about your code in these three sections often helps you think about the flow of data and work out how you can construct a pipeline to analyze it in the most effective way. Because you'll often find yourself doing similar analyses each time, you'll often in 1 week be doing analysis which uses a particular function, and then later on you'll be using that same bit of functionality in a different analysis. It's useful to be able to package up the middle step into small pieces which can be reused in multiple places. And that's what functions allow us to do. So we're going to look at this middle part of our analysis here, and we're going to wrap that up into something which can be reused. And so instead of us having to use 3 lines of code every time to do that functionality, we can instead have a single line of code we run to call the function which implements it. So we start a function definition with the def keyword, which stands for define, because we are defining a function. We then give the function a name. And now this is the name we are going to use when we call the function. In the same way as we call the print function, somewhere there is a bit of code that says def print. Here we are defining an add arrays function. Then we need to tell it what arguments it should expect to receive. And we do that by using round brackets. Similar syntax to use when calling a function, but here we are just defining it. And we say that this function, when it's passed the arguments, is going to refer to them as x and y. So this function, when called, should be given 2 arguments. We then describe the body of the function. Notice that when I press enter after the colon at the end, it automatically indented. Like with for loops and if statements and so on, indented code means it's part of the thing that's above. So all of this code is part of the function. I'm then going to effectively rewrite this bit of code here, but inside the function. I'll use different variable names to make sure that we don't get confused. So I'll make a variable called z, which is going to be our accumulator. We write for x elem y elem in zip x y z dot append x elem plus y elem. Okay. And I made a typo there, append. And then last time that was all we had to do because the C variable was left in the same level as everything else. So after we'd done our code, we could simply print C. This time, because we're inside a function, we've got our own little set of variables which are internal and private to that function. So in order for anything to get out of the function, to escape to the outside world, we have to explicitly return anything that we want the outside world to get access to. The thing that we want to return from this calculation is the variable z. And so to return it to the person who called the function, we use the return keyword, followed by a space, followed by the name of the variable. So the way we read this is we are defining a function called addArrays, which takes 2 arguments. Inside the function we are making a list, adding stuff to it based on some kind of calculation, and finally returning that new variable which we've just defined. If we run this cell, nothing has yet happened. We haven't executed the code inside. All we've done is define the existence of a function. But that means that we can now call this function in the same way as we do with print functions, sorry. We call it by using the name of the function that we just gave it, addArrays, and we pass it 2 arguments because that's what we defined it to want. It expects lists, and so we're going to give it the name of 2 lists, A and B. Notice that the lists in this top scope are called A and B, but inside the function they're called X and Y. That's perfectly fine. They don't have to have the same name at all, and in fact it's often better if they don't have the same name to avoid confusion. In the outside world, we refer to them as A and B. The function knows them as X and Y. They're the same data, but they have different names in the different contexts. If we run this function, call it passing in A and B, and run that cell, I made a mistake. That should be append those added together, not add them as two arguments. Now, if we run this function, we get printed out the correctly added data. So we've got our 6, 8, 10, and 12, which is the correctly added together A and B lists. So Amy's asking, with zip, can you multiply, divide, etc. A and B? Absolutely. So if we look at our code here where we're doing our zip function, all that zip is doing is providing us with the elements from those two lists. So the elements of X and the elements of Y are going into these two variables. Here we are deciding that we want to add them together, but we could just as well replace that plus sign with a multiply or a divide or absolutely anything else you'd want to do with those two variables in order to process the data as you see fit. So if there's no more questions, we'll move on to the next exercise. So going to the notes at the bottom of the functions section, it's a chance for you to have a go at writing some functions for yourself. So the first exercise here is to take that code from that last section, which I'll just show on the screen, and to turn all the code from here to here into a function. So to move that section of code inside a function by defining a function, defining the arguments. In this case, it will take one argument, which will be the message to be translated, and then to call that function and check that it's giving you the same result. Once you've managed to do that, there is a second chunk of code, which you can start by copying and pasting into a file called decode.py. And then you want to do the same thing to that chunk of code. Copy everything from the empty list creation to the join and put that into a function as well. In the first exercise of the two, your function should be called encode. And in the second exercise, your function should be called decode. I'm going to give you a few minutes to do this. And if at any point you want a bit of help, either ask in the chat, but also note that every exercise has an answer link afterwards. So do feel free to have a look at the answer to see if you can learn anything from it or if you want a little bit of clarification. Lucas is asking whether it matters where you define the function. For example, in MATLAB, they have to be defined at the end of a script. In Python, you can define a function anywhere at all. As long as you've defined it before you call it, everything's going to work out absolutely fine. There's a general convention to define your functions at the top, but as long as they're defined before they're called, it will work just fine. And Luca is asking, when you define a function, does it remain in Python when you run it another time? No, a function defined will only remain as long as that script is being run. We'll see in the next section how you can write functions and have them used in multiple scripts, so you're probably predicting the future a little bit there. But on the whole, you define a function, it exists in that script, and you can use it for the rest of that one script. I'm going to go through turning encode.py into a function on the screen now in front of everyone. So whether you finish this section or whether you're still working on it, if you want to watch along to see how I'm doing it, feel free. Otherwise, if you're still working on the exercises and you just want to concentrate on that, feel free to carry on for a little bit doing that. So if we look at encode.py, the bits of code that we want to turn into something reproducible are the bits that actually do the conversion. These lines at the top of the file are our data reading in. They're setting the initial inputs to the whole thing. Both some data that's used for the conversion, as well as the message that we want to convert. These lines of code here are the bit that's actually doing the conversion. They start by making a list that we're accumulating into. They loop over the message and convert each letter in turn into the Morse code equivalent. And finally, once all of those converted letters have been put into the Morse list, we join together all of those Morse letters using spaces and put it into this variable Morse_message. So this is the section of code that we want to turn into something reproducible. This is the thing that we might want to call in different contexts. We don't always want to only call it on this particular message. We might want to call it on other messages. So we want to turn it into something reusable. We start off by defining a function. Define encode. Choosing a name for a function can be a little bit tricky sometimes. The main bit of advice I would give you is keep it short and use something which is generally an action or a verb. When you call a function, you want it to perform some kind of action, and so you should name your function in a verb sense. So this function is going to encode something. It's going to take an argument. The argument is going to be called message, and we end it with a colon. All of the code inside, we then want to indent, because that is all now part of that function. At the end, what we need to do is return Morse message. So the input comes in here, gets looped over, and then the output is put into Morse. We convert Morse into Morse message using the join, and then we return our final output. Now that we have our function, we still need to call the function. If I ran this code now, we would get an error saying, I don't know what Morse message is. So we need to make sure we call the function. I'm going to scroll down a little bit. And we call the function by using the name of it in code, call it like a function, and pass in the argument as message. The result of that function, which is what's returned here, needs to be put into a variable. And so let's call that Morse message equals. We can now save that and run it, and we get exactly the same output that we got before. The one thing I'd like to point out, which I alluded to before with our A's and B's and X's and Y's, is that this variable here is called message, but we're also calling the variable inside our function message. That's just because that's how the code looked before we functionified it, but there's no reason they have to have the same name. To make that clear, I'm going to change our internal variable names inside our function into something else. So I'm going to just call that, I'm going to call this M, and I'm going to call this M. So the message that we want to convert is called M, and that's the variable name we pass to the function. Inside the function, it refers to it as message, and finally returns Morse message. Also, these two variables don't have to have the same name. So to make that clear, I'm going to call our outside of the function variable Morse underscore M, and do the same thing with both of these. So outside of the function, we just have M and Morse M. Inside of the function, that's where we've got our long variable names. There's nothing implicitly wrong with using the same names outside and inside, but I wanted to show you that they don't have to be the same. And to demonstrate it, I will then run that bit of code. The process for the decode function works in exactly the same way. There's a bit of setup at the top, which is defining our variables. Then the bit that does the decode works like this. We've turned it into a function by indenting it, called it in code, finally called it, and printed it out. I imagine that some of you attending the course today might have done functions before. It's always difficult to know what the introductory level of everyone's knowledge is, but certainly by the end of the course today, we want to make sure that everyone's up to the same level with all the topics that we're covering. So I want to try and make sure we're not leaving anyone behind. So now we've got our encode and our decode files, and I'll show that Python decode.py works as well. It prints out SOS, we have hit an iceberg and need help quickly. We are ready to move on to the next section. So looking at this code so far, we've got some information that is being duplicated between these two files. So first of all, there's this letter to Morse dictionary at the top, which is in decode.py, but it's also in encode.py. So this is something which is central and core to the process that we're doing. It's some kind of static data that's being used as part of our algorithm to do the calculation that we're asking for. But there's other text or there's other code inside this file which is specific to the problem at hand. In this case, it's the message that we're translating. You can imagine this being a stand-in for the data that I want to analyze today, or the database that I'm getting data from that I'm looking at today. So there's some things in this file here which are usable in all contexts, no matter what kind of message I want to convert to or from Morse code. and there's some code inside these files which is specific to the task at hand that I'm doing today. And so the first thing to think about when you've got code like this is to start thinking about which parts of your code are today's job and which part of your code are going to be useful in the future when you're working on a similar task a week, 6 months, 5 years down the line. Think about which parts of your code are generalizable and which part of your code are specific to your job today. Once you've got in your head how various parts of your code base fall into one category or another, you can start making it so those parts of your code which are generally usable can be extracted out and put into something which can be used in multiple different scripts without having to copy and paste them. And this is how we're going to carry on our journey towards making our code more reusable and harder to make mistakes with. The first step was we've got some lines of code, and so we turn it into a function so that we have a defined interface of what goes in and what comes out. And so we no longer have to care about what's inside the function. We just call it and we expect and assume that the internal is going to work correctly. The next step along that path is to take the parts of your code which are reusable and to put them somewhere where all your scripts can find them. And that is a feature of Python called modules. And so to demonstrate it, I'm going to show you how we can do it with the add arrays example that we were playing with before. I'm going to make this a little bit bigger here. So I'm going to make a file called arrays.py. And inside that, I'm going to put that same function that I defined over there on the right-hand side. So this is a normal Python file. It is as you've written any other time. There's nothing special about it, but this is going to turn into a module as we work through this little section here. To turn a Python script into a module in Python requires no work whatsoever. We have our arrays.py, which has inside it a function. That means we can go to our console and we can write import arrays. You might have seen import used when you're working with, for example, NumPy or pandas or other third-party modules that you might have used before in Python. But this allows you to write your own modules, which you can put in functionality which you want to use in different contexts yourself. When we write import arrays, it's going to first of all look in the current directory for a file called arrays.py. And because we've just created one, it's going to find this file and it's going to import this module. We run this with Shift Enter. We can then do arrays dot, because dot is how in Python you get access to something that's inside something else. We have the arrays module, which is this whole file on the left-hand side. And from that module, we want to import the add arrays function. Now, if your tab completion is working, you should, after typing arrays dot, be able to just press tab, and it will show up there arrays.addArrays, and it's a function. We can then pass in A and B and run it, and it gives us out our answer. Now, this addArrays function is the one coming from the module arrays, which is the one that's defined over here. And that means as long as this file is in our directory, we can restart our computer, we can change and restart the console, but as long as we write import arrays, we should get access to it. If you're having any issues with this, and I'll give you a chance to have a go with this yourself in just a moment, the first thing to check is that you've saved your arrays.py file. Up here you should see a black X next to the file name in the text editor. If you see a little black circle next to the file name, make sure you've saved the file by going to File, Save, which is Control-S or Command-S. If you have done that, then the next thing to try in the console is if you right-click in the console and select Restart Kernel, that will clear everything out after pressing the big red Restart button. You have to scroll down sometimes, at which point we can import arrays.py. again, define our A and B. And then we can call arrays.add arrays A, B. So if you're having issues, try right-click, restart kernel, run those lines of code again, and see if that works. I'm going to give you a minute now to have a go at that yourself. Then I'll carry on with the next little section. So Katie's getting an error, module not found error, as is Sophia. So the first thing to check there is that, as I said, when you do import arrays, it's going to look for a file called arrays.py in the current directory. So inside the box here, try running %ls and then press enter, and you should see the same list of files here printed in the console as you do on the left hand side in the file browser. If you see a different list of files, then you will have to make sure that you're in the same directory between the two places. So check that you're seeing the same list of files first, and if you're not, then let us know. Good, I'm glad that fixed your problem, Katie. It does get a bit confusing, and Jupyter Lab isn't always very good at keeping everything in sync. So that's always worth checking that you're in the right directory in all of the different places that need to be kept in sync. And Sophia, if you're not in the right directory, so for example, I'm going to put myself in the wrong directory. So on my computer, my code is sitting in home mat temp/python. I've put myself into the wrong directory. There we go, that's working. But if you want to move, then %cd space the name of the directory you want to move into, which is Python. CD stands for change directory. Run that, and then %ls should work. Kunal points out that if you put in different length arrays, then the resultant array has the length of the shortest. That's a very good point, and later on in the course today we'll be learning how we can check for errors and raise errors in those situations. But to demonstrate what you're talking about for everyone else, if I make A and B different lengths, and then run the function, we see that 4 never gets added to anything. Now there's two reasons for why that happens. Firstly is that there's no definition of what 4 added to nothing would be, and so it makes sense that it's not able to guess it. But the real root cause for it is that the zip function only loops over the arguments that passed in as long as they all have elements left. As soon as one of the arguments passed to zip runs out, the whole thing stops. That's something to be aware of when using zip. Bryony, you're seeing name error, name arrays is not defined. Make sure that you have run import arrays before you try and call the function. So you have to import arrays. You have to do that every time you restart the console, every time you do a new script, in order to make sure that arrays has a folder called my code. You could run something like mycode.arrays, and it would look inside that folder for that module. Otherwise, when you've got much larger collections of code, there are places you can put them centrally on your computer where it will always be able to find them regardless of which directory you're in. The next thing I want you to do is the exercise at the bottom of the modules page. So in this exercise, we're going to take the code from our encode.py and our decode.py, and we're going to extract the common core elements and move them into a file called morse.py. Then we're going to edit our encode and decode to import Morse and call the functions that are defined inside the Morse module. You can test it in the Python console if you want to, but if you do, you will have to do the right-click restart kernel trick. Otherwise, it's not going to import any changes that you make to your modules. But spend some time on that. Make sure you're able to convert your Morse code stuff into one module called Morse, and then import it in the other two files. I'll go through the answer to that exercise now with you all, how we can turn our Morse code functions into modules. So I'm going to close arrays.py. I'm going to make a new file over here. And I'm going to call this file, rename morse.py. So encode and decode are going to represent our tasks that we want to do today. We're going to pretend that we're a Morse code operator. We've received a message and we want to turn it into Morse code. And this script here should just do the task at hand. It should define an English message and then it should work out what the Morse code message is. Likewise, decode.py is just going to define a Morse code message. It's then going to call the decode function to get back the English message. All of the stuff that does the conversions, we're going to move into morse.py. The first thing we want to move in is our two functions. So we take decode, I'm going to cut it with Control X and paste it into morse.py. And I'm going to do the same thing with encode. And paste it into morse.py. So we've got our two functions in here. But if you look at the encode function, for example, it's taking in one argument, which this function is going to refer to as message. So inside this function, using message as a variable name is valid. We can access that. We define the Morse variable. We loop through message to make a new variable called letter. This is all fine. This is all consistent. On line 6 here, we try and access the letter to Morse dictionary. And from the point of view of this function as it's written, it doesn't know what the letter to Morse dictionary is because it's not inside this module. And so we need to make sure we also move in any data that these functions need into the module as well. And so that is the letter to Morse dictionary, as well as this bit of code which calculates what the Morse to letter dictionary is. These 4 lines of code here invert the dictionary, turn keys into values and values into keys. So I'm going to take these two variable definitions here, I'm going to cut them, and I'm going to paste them into our module. I'm going to save that file, and I'm going to get rid of it out of here because we don't need it in here anymore, because it's not used anywhere in here. And you see that has massively simplified the encode and decode files. They are just dealing with a task at hand, defining a message, decoding the message, and printing the decoded message. All of the complicated stuff is locked away inside morse.py, which the users, encode and decode.py, don't have to care about. They don't have to understand what's inside here. They just have to trust that calling those functions is going to work correctly. We can do a quick test of this by going over to our console, doing import morse, morse.encode, and let's encode SOS because I know what the answer should be. Gives us back ... .. So this function here is doing the right thing. We've got it from the Morse module, which is morse.py, called the function, it's given us the response. In order to do the same thing to our encode and decode files, there's one other change we have to make, and that is we have to explicitly import our module that we've just created. Imports in scripts always go at the top of the file by convention. So import Morse. And now encode as a bare name doesn't have any meaning by itself. It is now inside the Morse module, and so we have to write morse.encode. Importing a module doesn't automatically make everything inside it globally available. It keeps it inside what's called a namespace, named after the name of the module, which we access inside using the dot syntax. This means if we go to our terminal down here and we now run python encode.py, it's printing the right thing. We can make the same change to decode. Import morse, morse.decode. Printing out correctly. And so now still our job we're working on today's script is nice and short and to the point. We define our data, we process our data, and we print the result. Likewise with encode.py, define our data, do something with our data, and then print the result. The complicated stuff's locked away in the module, morse.py, and once we've written it and it works, we don't have to worry about it again. We can just import it and use it. We saw before how moving our code into functions allowed us to define the interface that they had. We would say this function should have these inputs and it should have these outputs. We also then saw how moving them into modules allows us to reuse those chunks of code in different contexts, in one file or in another or in the console. The last thing I wanted to show about what modules and functions provide for us is the ease with which we can test that our code is working how we expect. If I make a new file up here, I'm going to make a text file called test_morse.py. I've got a module called morse.py, and alongside that I'm going to make a second file called test_morse.py. So it's the same name, just with test in front. This is a convention I like using for every module that I write, to write a file alongside it with the same name but with test underscore at the beginning, in which I put a little bit of code which I can run to check that the module is doing what I expect. So in order for that to work, we have to start by importing Morse. And because our code that we've written is an encoder and decoder, that allows us to test what's called a round trip. We encode a string, decode it again, and check that we get back what we started with. So let's make a message, hello everyone. We then make a new variable code, which is created by doing morse.encode message. I then take the result of that and pass it to morse.decode straight away without doing anything to it, and assign that to decoded. The last thing I do is then print out, checking that message is the same thing as decoded. If message, which is our starting thing, once it's been encoded and decoded, is the same as the result, then we know everything's working well. And so I can run this script anytime I like with Python test morse.py, and as long as it prints out true, I know that everything's working. And that allows me to go to my morse.py, change stuff around, fix bugs, try and re-implement it in a different way. And as long as my test is returning true, I have decent confidence that the code is still working and that I haven't broken anything. This is something I highly recommend getting the habit of doing. This is the first step towards testing your code, but there are much more flexible, powerful, and useful techniques that you can use. And we cover those in our other course, Best Practices in Software Engineering. So do check out that course if you're interested in seeing how you can do more with testing. But for now, in this course today, this gets us most of the way there towards checking that our code is working how we expect. We're now going to move on to the largest chunk of the course today, if I go to the notes, and that is classes and objects. Now, classes and objects are something that a lot of people struggle with when they first start learning Python. It does take a bit of a conceptual shift as you're going through, but I'm hoping that I can take you on the journey today to show you how they can be useful and how you can use them in your own code. They fit in the same kind of story that we've been telling so far. We started with functions, which allow us to package up chunks of functionality and give that a name and make it so we can reuse it in different places. We then packaged up those functions and put them into modules, which allowed us to use that function in different scripts or in the console, however we saw fit. The next step along that journey is to learn how we can package up not just bits of functionality, but combine together data and functionality all into one blob, which we can reuse in whatever context we see fit. And the way that Python and most programming languages provide that is using a technique or a feature called classes. Through the example here, we're going to be writing some code which represents a dog. And so I'm going to go ahead and start writing some code. I'm going to do it in the console because we're going to be interacting with it. I'm going to restart the kernel just to clear everything out. And I'm going to clear the console cells just so that it's a nice clean slate. So let's make a variable called our dog. Now, the dogs that we're representing inside this code here are going to have a couple of attributes to them. And of the functionality that we've learnt so far, either this course or previous courses, the obvious thing that we'd reach for would be a dictionary, a thing that we can use to bundle together a bunch of disparate pieces of information. So let's go ahead and make a dictionary. The key is going to be name, and I'm going to get some audience participation here and ask in the chat if anyone has an idea of what we should call our dog. I'll go with Bruno. Bruno. The other bit of information we're going to store about our dog is its colour. Now, what colour is Bruno? I guess brown would be the obvious answer, but anyone got any other ideas? Yeah, let's go with brown. That's fine. And I'll do lowercase b. So, this is a dictionary which defines our dog. Its name is Bruno, and it's a brown dog. Now, this is a perfectly reasonable way to represent data. As you're developing code with Python, you're bound to very often reach for dictionaries as your way of bundling together disparate pieces of information which are related in some way, and where you want them to have names which you can assign and use to relate to different parts of that object. Because once we've got our dog, we can obviously do something like our dog square brackets name, and it prints out Bruno, so we can get the data back out again. Let's imagine, however, that we've got a function def called describe, which is going to read in this dictionary and print out a message which summarizes the core essence of this dog. So it takes one argument, which we're going to call dog, and inside the function, all it's going to do is return a string. In fact, it's actually going to return an f string, as we saw before, which says dog, no, I need the curly brackets, name is dog colour. So it's going to print the name of the dog, the word is, and then the colour of the dog, depending on the argument that we pass in. We've now got our function defined and usable, so we can now call it describe our dog. Dog. Bruno's brown. Good. That's all working fine. The issue comes about when you realise that this function here is making assumptions about the type of data that's passed in. A cursory glance of this, or a comment describing this function, might say, this function describe accepts a dictionary describing the dog, and it will print out information about the dog. That's a one-sentence summary of what this function does. But actually it's more than that. It requires that the dictionary has the key name, and it requires that it has the key colour. If you pass in a dictionary which doesn't have one of those two, then it's not going to work. It's going to raise an error of some kind. And so when we're describing how this function works, we would have to tell any users of the function, you have to pass in a dictionary which describes a dog, and that dictionary must have the keys name and colour. And if they make a mistake with that, they're going to get errors, and they're not necessarily going to understand why. One of the important things that you can do as you're developing code is make it so that any functions you write have a well-defined interface, which makes it hard for people to use them wrong. If you write a bit of code which people easily misuse, then it's not going to get very widely shared and people aren't going to want to use it. They're going to want rigid rules which allow them to avoid mistakes as much as possible. And so the main way that we can take something which is a dictionary and create some kind of data type which has a rigidly defined set of parameters or attributes on it is using a class. At its core, a class is a data type which has a strict list of parameters which must always be there, and you can rely on them being there. So let's see how we can take our definition of a dog and turn it into a class. Like with functions, which we start by writing def, we define a class using the class keyword. We then give the class a name. The convention in Python with classes is that you give the name of the class a capital letter at the beginning, as opposed to variable names, which use lowercase and underscores. This helps someone reading your code to easily see what are classes and what are variable names. We then follow that with a colon, and then we are writing the code inside the class in much the same way as we do with functions or if statements or for loops or anything else. The main things that sit inside classes are functions. And so we're going to define a function now which is going to describe what a dog looks like. So we do that with def. Now the special function that we have to create to define what a class looks like is called underscore underscore init. There are 2 underscores before and 2 underscores afterwards. This is a special function which is called in order to initialize the class. It's going to set it all up so that we know it has the parameters and the attributes that we expect. It takes arguments because it's a function. All class functions always have to take an argument called self at the beginning of their list, followed by any arguments that we want it to accept, which in our case are going to be name and color. And it's a function, so we end it with a colon. I'll come back to explain how init and self relate to each other in a little while, but for now we're going to make this dog class, use it, and see how it works. Inside this function, we are going to set some variables, and we are going to set those variables. We're not going to return them at the end, but we are instead going to attach them to this variable self. This variable self is representing the dog in question at the moment, the dog that we care about, the dog that we are currently initializing. And so if you do self.name, we are talking about the variable name that's attached to the object self. We assign that the argument that was passed in name. We do the same thing with color, self.color equals color. At this point we have finished defining and describing our class. That's all you need for a class that has 2 attributes on it. So we run that cell with Shift Enter, and it gives us back no error. So it's worked. That class now exists. In order to make an instance of that class, we call it like it's a function. We need the name of the class followed by brackets. The arguments that we put inside the brackets are the arguments that are going to be passed into the initialize function, not including self, because self gets handled automatically. It's the other arguments that get passed in. So we can pass in Bruno and Brown. We want to assign this to a variable, so let's call it our dog again. We run that, and that has created an instance of the class dog, which we are now calling our dog. Dog with a capital D is a class. This code here defines a class. This variable here, which was created from the class, is what's called an object or an instance. Now that we've created this thing, we can go ahead and use it. We can say our dog.name, run that, and it tells us that our dog is indeed called Bruno. So we're accessing attributes on our dog with a dot syntax followed by the name of the parameter that we care about. And that is in contrast, if I scroll up a moment, to our dictionary style where we gave the name of our variable followed by the square brackets syntax. So if you've got a dictionary, use the square bracket syntax. But because we're now inside using a class, we can use the dot syntax. We can obviously do the same thing with dot color, and we get out brown. This means we can now adapt our describe function so that instead of taking a dictionary and assuming that there's a dictionary being passed in, we can have it so that it assumes a dog object is being passed in. So here instead of instead of dog square brackets name, we do dog.name, and instead of dog square brackets color, we do square brackets color. We can now call the describe function on our dog, and it prints out Bruno is brown. So take a minute now yourself to write this code, copy it in. It's all written in the notes, so feel free to copy and paste it from there or use that as a reference. Spend a minute writing that code, running it, making sure you can make instances of your dog. You can get the attributes out again and adapt the describe function so that you can pass in a dog object using the dot syntax, get the attributes out and describe the dog and have it all work correctly. One way of thinking about a class in Python, and in fact in most programming languages, is that it can be seen as a template with which you can create objects. So the code here doesn't represent one single dog, it represents all possible dogs we might want to create. So here we created one instance of the dog class, we called it Bruno, and we called the variable name our dog, but we can create more. We can create an other dog, and there's been some great examples of dog names in chat, and let's go with Achilles. And what colour is Achilles? Achilles is blue, a very unusual colour for a dog. It's probably been mistreated. There we go. And I'll just run that our dog Bruno line again, so they're next to each other. So here we've called the dog class 2 different times. Each time we've called it, we've created a different object. And so the way that works when you're inside your class is that when we called our dog, and we call dog Bruno brown, dog is then going to look at the dog class. Because we're calling it with the brackets, it's going to create an instance of that class, which is going to need to be initialized. And so Python will automatically call this magic function underscore underscore init, sometimes called dunder init for double underscore init. And it's going to pass in the 2 arguments that we passed in here as name and color. The self object here is referring to the same thing as what's going to get passed out at the end. So self here refers to the same thing as our dog. And so when we do self.name, we are effectively doing our dog.name equals, which is why our dog.color, our dog.name give the right thing. When we call this class a second time, when we did other dog, this time in the function, name and color are obviously different because we're passing in different arguments, but self is also pointing at a different object. Self this other time is pointing at the same thing as other dog. And so self is the special argument in any class function which gives you access to the object that you're currently talking about. And so because self allows us to talk about various different things about the class, we can use it both to put data into the class, we can also use it to get data out. And so now let's see how we can extend our class here by adding some functionality to it. I said at the beginning that classes combine data and functionality. So far our class is all data. It just defines some data which is held by the class. We want to give our class some functionality as well. And to that end, I come back to our describe function. At the beginning, I was lamenting the fact that you have to remember not only that the first describe function, if I scroll up, took a dictionary and you had to remember to pass in the right dictionary, you had to also make sure the dictionary had the name and the color attributes or keys inside it. We improved that a bit by saying that our describe function here is going to enforce that as long as you pass in a dog object, it will always have name and color, because both of those variables are always defined inside the init function. But we still have the possibility that we could pass something completely wrong to dog. We could do describe hello, and when we try and run that, of course we get an error because describe function doesn't understand how to describe a string. It only understands if it's passed a dog object. And so what we want to do is make it so that our function can only ever be called on a dog object, and it can't be used outside of that context. And so I'm going to bring up our definition of dog again and run it so that it's on the screen. I'm going to go back up to our definition of our class, and I'm going to show you how you can take this function that's currently freestanding and move it so that it's a function inside the class. I'm going to copy the code because it's going to be only a short few steps. We move it so that it is alongside the init function. We paste this code here and make sure that it's indented so that it's at the same level as init and the internal indentation is all the same. The next thing we need to do is, like we had with the init function, the first argument was self. Here, the first argument of describe is going to be self. And as self here was referring to an object of the class dog, likewise, self here can refer to an object of the class dog in the same way that the dog variable in our freestanding function did. That means we can simply rename this variable to be self, rename this variable to be self, and rename this variable to be self, and that's all we have to do. We have now moved the describe function inside the class to be a class function. Class functions are sometimes also called class methods. Those two bits of terminology are somewhat interchangeable in Python. Now when we define this class, it has got two functions on it. I can make our Bruno dog again. We have to recreate our dog because it was still referring to the old version of the class. And that means that we can now do our dog dot, and instead of doing dot name or dot color, we can now do dot describe. Notice that we don't put anything in the brackets of describe, and that because in the same way as self in the init function was automatically put in there, in the describe function, likewise, it's automatically passed in, where the argument that's passed in as the first parameter to describe is taken from the thing in front of the dot. So writing our dog.describe will call this function with our dog passed in as self. And that means inside the function, self.name is doing our dog.name, and self.color is doing our dog.color when we call this function here. So that means if we run this code, it gives us back the description of our dog. And there is now no way to call this describe function on anything that's not an dog type. If we try and make a list and do l.describe, that's not going to work because the describe function isn't defined on the list type. It's only defined on the dog type, and this will give an error. So I'm going to ask you to take a moment just now and do this same exercise with your dog class. Take the describe function, move it inside the class so it becomes a class function or a class method. Redefine your dog. Of course, you can give it any name and color that you wish. And check that calling our dog.describe does the right thing and prints something out. Take a minute or so now to do that, and then we'll be moving on. Harry, you're seeing a strange output of bound method dog describe and then a whole lot of hexadecimal, and I bet I can reproduce that. So I imagine what you've done is type something like our dog.describe and then haven't passed the brackets afterwards. So if I run that, I get a very similar thing. And this points to an interesting feature of Python, which we cover in more detail in our parallel Python course, and that is functions exist as objects in their own right. If you don't put the brackets afterwards, it tells you that thing you just told me about, that's a function, or as it calls it, a method that's been bound to the class. And so if we put the brackets afterwards, it does the right thing. So far, our dog is a little bit sad, really. It has a name and a colour, but it doesn't have any functionality. It can't do anything. It's entirely static. We create it, we give it a name and a colour, and then it exists in that form, changeless for eternity, or at least until we turn off our computer. We want to have the ability to represent data inside our classes which can potentially change over time. Something which is going to represent the state at one point in your program You call some functions and it keeps track of things, and it has a different state at another point in your program. So we're going to make a new parameter or new attribute of our class, which, unlike these two arguments here, we're taken from the argument list, you can just make static data which is attached to your class. So we can make a new variable, self.energy. This is going to represent how much energy our dog has. Now, if anyone has had a dog, you'll know that they have a lot of energy, but we're going to pretend that initially our dog is always created with an initial energy of 1 and some kind of units undefined. So this parameter here, this attribute, isn't being defined based on an argument being passed in, it's just statically defined to any new dog that's created to always have an energy of 1. So if I create that and I make our Bruno dog again, in fact let's make a different dog because we've had some good examples in chat. We had one earlier called Corona, and I'm going to make Corona gold. So now our underscore dog dot energy is number 1. It's got an energy of 1, so we've got some information about it. So that's all very well. We can, change the energy to be 100, and then it's got an energy of 100. But it's nice to, instead of having to dive into a class directly and change its parameters, to instead have functions which do the actions which we want this class to perform and keep track of the internal state for us. So we're going to be adding some more functions to our class which allow us to exercise our dog. So the exercise function is going to reduce the amount of energy that our dog has. So we go back to our class here, and we're going to add another function, def exercise. Again, it takes the self parameter, self argument. It's very easy when you're writing functions into classes to accidentally forget the self, but you'll quickly notice it when you try and use the code. And the exercise function or method is going to print out a message telling us that you take self.name for a walk. And then it's going to do self.energy. Notice that self here is the argument that's passed in, so it's going to be referring to the same thing as this. Minus equals, that's how you decrement or decrease a number by a certain amount, 1. So this function will print out something and then reduce the energy by 1. So if we make our dog Corona again, we print out the energy. Our dog dot exercise. It prints out the message. We took Corona for a walk. If we look at the energy a second time, we see the energy is now 0. If we make a second dog, to draw home the point that each dog object is an independent thing, if we make our Bruno again, other dog, other dog dot energy has not changed. So each dog has got its own internal energy attribute which it's keeping track of. So have a go at implementing the exercise function now, as well as adding in the energy parameter. Once you've done that, have a go at making a fourth function on the class called feed, which is going to feed the dog and increase the energy by 1. I have on the screen here the example of the feed function. So the feed function works exactly the same as the exercise function. It prints out a message saying that the dog eats the food, and then it does self.energy plus equals 1 to increase the energy. So if we define that class, redefine our dog, we can now do other dog dot feed, and it eats the food. We can do it again, and it eats the food again, so that if we look at other dog dot energy. The energy is now 3. So it's a dog with an infinite appetite, which will accrue an infinite amount of energy. But such is life when you're simulating things on the computer. There's some text on this chapter here, which is explaining how this stuff all works. So do have a look at this text later on. All these course notes will stay up permanently. So do have a look through the text here if there's anything you're not clear about. But have a look at the exercise at the bottom here, which is to edit the morse.py script, which is our script which is holding our library code, our functions and our static data, and to create 2 classes. One class called English message, which has the encode function moved inside it, and another class called Morse message, which will have the decode function moved inside it. And then to change test.morse.py or make a new file called test.morse.py, which imports those 2 classes, makes a string and an English message from that string. So this is calling our first class. Calls the encode function on it to get back the encoded text string. Then to take that encoded string and to make a Morse message from it, and to call the decode function on that, and to check that we get our answer back at the end. Have a look at this exercise and see if you can create a class for the encode function called English message and a class for the decode function called Morse message. Again, there is an answer at the bottom of the section, so do feel free to have a look at that answer in case my description of the question isn't good enough, or if you want any help along the way. And likewise, feel free to post in the chat if you have any questions. I'll give you a few minutes for this one because it's a little bit trickier. As to your question there, Emma, about it not changing the energy, I'm going to show you on the exercise here what you've done. So you've written return that string in the same way as you did in the describe function. And that means as soon as the exercise function gets called, it's going to return that string and the function is going to end, which means it's never going to get to this second line here. Instead, change it so that you write print as a function so that it prints that, outputs it, and then carries on to the next line. And that should then work. Gunar's asking, what if I don't put init in a class? So in the example here, if I didn't have an init function at all, it would still work. It would mean that you can only call your function or create an object of your function without any arguments at all, which means that none of the parameters or the attributes of it which are assumed to be there will be created. You will effectively create an empty class which has no data, which only has functions. It's a perfectly valid thing to do if you want to bundle up a few of your functions under some kind of namespace. But on the whole, you usually want to have some data in your class as well as functions to act on that data. I'll go through the answer to that exercise on the screen now, so you can all see how I can convert a function and some associated data into a class which is encapsulating both of those things. The easiest place to start is with the function here, and we write class English message. This class is going to represent a normal string, an English string, which is going to have an encode function on it, which is going to return to us the Morse encoded string. We want to indent this, and we'll come back to the rest of what we do to that in a moment. We have to make an init function, and the init function, like all functions, takes self, and that is and message. So we're going to make one class which represents a message, and that message is going to be wrapped up and saved into the class with self.message equals message. The other thing that we want to save into our class, because we want to use it inside our function, is the letter to Morse dictionary. So I'm just going to copy, in fact I'm actually going to cut it, and paste it into here, make sure everything's indented nicely, and write self.letter to Morse. So this is saying that our class is going to be initialized, or an object of our class will be initialized with an attribute message, which comes in from what's passed in as an argument to the constructor, as well as an attribute which is storing our conversion dictionary. That means in our function down here, where we are going to be converting our message, it has to take the self argument, Now message isn't going to be passed as an argument to self, and that's because we don't need to anymore, because we can access message through self as self.message. And so here, instead of writing message, we want to write self.message. And here, instead of writing letter to Morse, we want to talk about this letter to Morse up here. So we write self.letter to Morse. And I think that is all the changes we have to make. So I'm going to save that file. I did, when you weren't looking, make the same change to the Morse message class, which has got a self.message, a self.morse to letter attribute, and then the same decode function, which had the same stuff done to it. That means that we can come over to our test Morse file, which imports English message and Morse message. It's going to call the English message class and pass in a string. That is going to call this init function with message as the string, which will then be saved as self.message. It calls the message.encode function, where message is the object of that class we just created, which is going to call this function here, do the same stuff as we've been doing so far, and return our message out at the end. That goes into code string. We can then stick that back into the Morse message class and do the same thing in reverse, where we call it, make a Morse message object, call code.decode, and then compare the two. So now hopefully when I run this over here, I will get out true printed. So that means we now know that everything is working. We could also do from Morse import English message, English message. We'll do our SOS again. Let's call it M. And we can do m.encode, and we get back our Morse code. This means we can't accidentally call encode on something which is a Morse code message, and vice versa. It makes sure the type is holding both the data and the things that we can do to it. No one's piping up in chat to say they're having any problems or have any questions. I will say that classes in Python and in any language are often one of the biggest increases in complexity you come across when learning the language. Hopefully I've done a good enough job of explaining how they're used, how you can construct them, and what their purpose is, but they do sometimes take a little bit of experience and practice to get the full value out of them. Kunal is asking why I wrote from Morse import English message there. So I could have written, exactly as I did before, import Morse, and then done Morse.English message, SOS. That gives us back an object of that class. But by writing from Morse import English message, I've extracted out just the one thing that I care about from the module, and so I get access to the class name just by itself without having to write Morse in front of it. So the last section that we'll cover today, actually no, before we do the last section today, a thing about naming. I did mention this earlier, but classes often have these capital letter names like Morse translator or dog. Whereas variable names and function names use this snake case. It looks like a snake because it goes on the ground and it's got sort of up and downs to it. So snake case in Python is used for variables and functions and modules, in fact. Whereas camel case, and it's so called because it's got these humps, is used for classes. If you stick to this convention, then other people reading your code are going to understand what's going on. So the last thing I'm going to cover today is on the next section of the notes, and that's handling errors. So going back to our console, let's have a look at what these dog classes can do. So let's create our dog again so we know what state it's in. And let's make a other dog equals dog Bruno Brown. So we've got our dog defined. Our dog can do things. We saw before, we can perform actions on the dog. We can call these functions and we can do other dog dot exercise. that works fine. And we can do other dog.exercise, and we can exercise it, and then we can do other dog.exercise, and it keeps on walking, and it keeps on working, and everything seems like it's all working well. And that is until we ask the dog how it's doing, and we look at the energy of the dog, and we see that somehow its energy has ended up negative. Now, under very few definitions, is a dog with negative energy doing very well. And this is because we've allowed our exercise function to arbitrarily keep on reducing the energy attribute by 1 every time we call it, without any checking that it has energy to go for a walk. And so let's look at what tools we have at our disposal in order to make sure this stuff is being checked as we're going through. So the main tool that we've had at our disposal so far for checking stuff is an if statement. So let's go ahead and use the tool we already know and see how far that can get us. So we only want to exercise if self.energy is greater than or equal to 1. If it's 0, then the dog can't go for a walk because it's going to end up with negative energy by the end of the walk. We are going to allow the dog's energy to get to 0. That just means it's very tired. So if the energy is greater than 1, we allow it to happen. And so if we run this code to find our dog and make our dog, and then exercise it, we get the message printed. If we try and exercise it a second time, we see that no message gets printed. We can exercise it as many times as we want. But if we go back and check what the energy is, the energy has stopped at 0. It's never gone below 0 because we are checking as we go along that the state of the system that we're looking at is in some kind of sensible situation. Of course, it's very easy to miss that this one printed something and this one didn't. And so we really want to, when we're printing these things out, to print something else in the situation where the dog is out of energy. So let's write else, and I'll copy and paste this. The dog is tired, it doesn't want a walk. So if we now run that class and define it, make our dog, and try and exercise it, it works once because we reset the energy to 1 in our initializer. If we try and do it a second time, it tells us that it's unhappy. That's good. We've now got something printed in the good state and something being printed in the bad state. But when you're writing code which is going to be used by other people, it's still very possible to ignore this line accidentally. If, for example, we do this same line of code multiple times because we think that everything's working fine, and then we do afterwards other dog.describe, because we've seen here that we've run this 3 times, we're going to expect that the energy is going to be 3 lower than it was. Now let's look at energy. But actually, it's silently failing, and it's allowing these more exercises to carry on. It's allowing us to keep on trying to walk our dog without us being told explicitly and forcing us to make a decision to notice that it is in fact tired. And so the way that you can raise an error in Python which the person calling your function can't ignore is with a thing called exceptions. And so we can raise an exception in our code. I'm going to make this a bit bigger. By instead of just printing out this message, by writing the word, and I'll make this wider here as well, so that everything fits on the screen, the raise keyword, followed by the type of error that this is. Runtime error. In the notes here, there's a link to the documentation which lists all the different kinds of errors you can raise. In this situation, it's an error which has occurred while the program's running, and so raising a runtime error makes sense. It's up to you to decide what kind of error makes sense for your situation. So now when we exercise that code and we make our dog, and if we try and exercise it too many times, we get an error raised, a deliberate error which tells us that a runtime error was raised and the dog is tired. If we look at where the lines of code raise the error, we see that it's telling us in the exercise function on line 15, we raise the error, but that was called from these lines of code here, which are these lines of code here, and you see it's stopped on line 2. It's tried to exercise it this second time, hasn't been able to, and so these other 2 lines of code here will never ever run. It's forcing us to make the decision about how we deal with this problem. Now, there's a few ways that you can deal with an error that's being raised like this, but one of the most common is using what's called a try except state. A try except block is going to try and run some code, but if an exception or error is raised, it's going to allow us to run a different bit of code to kind of deal with the error that we're seeing. So we write try, and then we put this code in here. So I'm going to try and do this, except if there's a runtime error raised, in which case we are going to print something out. And see, now when we run this, it says something went wrong. So this code was attempted to be run, a runtime error was raised, and so this message gets printed out. That's good, we were able to catch the error and deal with the situation, but we've lost the information about why it failed. And so what we can do in this situation is take the error that was raised, capture it, and give it a name by writing as E. Then if we turn this into an F string, we can put E as a parameter inside the F string. So now when we run this, we get something went wrong with trying to access the dog, and then the contents of that error printed out. So printing a logging message when you've got an exception raised is a useful thing to do, but in some situations you can actually deal with the error and fix it in that situation. So for example, we have our try block still, but here inside the exception handler, this except state here, if the dog has run out of energy, we can try and feed it. And if we feed it, then we will be able to exercise it. So we've tried to do these lines. If any of them fail due to the lack of energy, then we end up in this block, at which point we can feed it and try and exercise it once more. So when we run this, we see that one of these lines failed, presumably the first, because we never saw an exercise line be printed. It's gone to this section here, where it has fed the dog, and then it's able to successfully take it for a walk without any further exceptions being raised. So for your homework after this session is to take the ideas that we had here with catching errors and raising them and apply them to the encode and decode code that we have inside our Morse code translator. If you try and translate code in Morse code which contains exclamation marks or @ signs or pound signs, anything like that, it's going to fail. So the exercise at the bottom of the handling errors chapter, I'll leave as homework for you, and it's to take this same idea of try excepts to catch the errors as they're raised and to practice applying the try except statement to them to make sure you get a sensible error message printed out. On the very last page on the notes, there's a link to our summary, which goes through what we learned today, as well as some links to the notes for some of our future courses. So do feel free to have a look at the notes for those and sign up for any of those courses if we're running them in the future. With that, I'll just say again, thank you all very much for being here today. Really great session, and I look forward to seeing hopefully all of you in one of our future courses. Bye-bye. We're mostly going to be learning about machine learning techniques today, or at least some things which fall under the umbrella of machine learning. Now, machine learning is a slightly overloaded term. I'm going to try to, throughout the course today, explain what machine learning is, how it fits in the context of wider topics such as AI, and how some of the techniques specifically we're using can be used, and why machine learning is more appropriate description for them than just statistics. Machine learning covers a whole host of tools. You might have heard of neural networks and deep learning and things like that. Those are techniques which use machine learning to discover information about data. At the very other end of the scale, perhaps the simplest form of machine learning that I can think of is the linear fit or linear regression. So that is just taking an X and a Y axis, a scatter plot, and plotting a line of best fit through your data. that is going to use machine learning techniques when you do it on a computer in order to get the information. And that really gets to the crux of what machine learning means. It is simply a statistical technique you apply to your data, but because you're doing it on a computer, you are using a machine. And so the machine is the thing that is doing the learning, rather than you sitting there with a pencil and paper and doing it by hand. So we're going to start off by launching into doing some data. So I'm going to do a little example here, and I'll pause every now and again to let you follow along and catch up. Otherwise, if you feel happy to, feel free to type as I talk. Almost everything I type is going to be coming out of the pages of the notes. So we're going to start by loading up pandas. So from pandas import read CSV, because we are going to be downloading a file. I'm going to copy and paste this because no one wants to watch me type out a big long URL. We are loading a CSV file. It's downloaded it. Let's have a little look at the top of that file. It is a CSV file, which if you had a look at it, you'd see it's 2 columns of text separated by commas. Therefore, it's been read into pandas as a data frame, which is a table which has 2 columns. The first column is labeled X, the second column is labeled Y. We also have a row index for each of the rows. Largely, we're going to be ignoring row indices in the data today. We are just going to be selecting columns from our tables of data. This table, as I said, has got 2 columns, X and Y. And I'm going to start by trying to clarify some terminology, because the sooner you get the terminology understood, the more easily you're going to pick up more advanced terminologies and concepts as we go through. And so the first thing I want to point out is the use of X and Y in machine learning. They have the same meaning as your traditional X and Y on your scatter plot, where X goes along the bottom axis and Y goes on the upwards axis. They're usually drawn that way because X are your independent variables, the things you've measured, and Y is your dependent variable, the thing that you are trying to find out about. And the same thing happens when you're doing stuff in machine learning. It is usually the case that you collect your X data and you want to use X to predict what Y is going to be. In this table here, we have one single column of X. Though it's possible, and we'll see this in the course today, you can have as many columns of X as you want, X1, X2, X3, etc. It's usual that you only have one column Y, though in principle it's possible to have more complex data there. So at its root, what we're going to be doing with machine learning today is using X to predict what Y is. And that's exactly what we're going to do with our scatter plot here. But let's have a little look at what our data looks like. So first thing to find out is how many pieces of data we have. It's telling us the X and the Y columns both have 50 rows in. So we've got 50 data points. Once you've got a vague sense of the shape of your data, the very next thing I tend to do, and we'll be seeing more and more in this course why that's a useful thing to have, is I'm going to look at what the data looks like when plotted. So let's do data.plot.scatter X and Y. And we get here a scatter plot. You see our data is looking relatively linear, starting in the bottom left, going up the top right, but there's a bit of scatter to it. What we want to do is, for a given value of X, predict more or less what the value of Y is. This is what a linear fit does. So I'll just give you 20 seconds or so to copy those lines of code into your notebooks, check you get a plot that looks the same as what I'm seeing, and then we can step on and start actually using some machine learning on this data. So hopefully that's all working for you. You've managed to load in the data, get the scatter plot going. So as with all data analysis tasks, we've started with our data. We've looked at the shape of it, we've looked at how it looks when plotted. We've guessed what the approximate relationship between the parameters are. We've guessed that between X and Y there's going to be a linear relationship of some kind. Once you've decided how you want to represent the relationship between your X and the Y, the next thing is to go and find some piece of code which is actually going to be able to extract the underlying parameters of that relationship for you without having to do a whole load of maths by yourself, by hand. In the course today, we're going to be using a package called scikit-learn. There's also another package called stats models. Both of these are linked in the notes. So if you have more complicated statistical things you want to look at, then stats models might be a place to look. But for most machine learning tasks, scikit-learn is going to give you a nice, easy to use interface to extract most of the information that you need. So let's start by extracting our model we want to use. So we're going to go from sklearn. Now we are looking at linear models here because we think there's a linear relationship between the two of them. So there is a linear model package inside the scikit-learn package. And from there, and I found this out by Googling and looking at the documentation, there is a package called linear regression. So every model that scikit-learn implements is implemented as a class. You import the class that you want to use. You then make an instance of that class. Now, at the point you make an instance of that class, it's effectively making an empty model which knows how to learn from your data, but hasn't yet learnt anything from your data. So we do something like linear regression. Linear regression is a class, and so we can call it with a pair of brackets like a constructor, and we assign that to a variable. This model object is now our model, which is ready to learn from our data, but is currently got random or empty attributes inside it. When we show our data to this model, it is going to go away and tune the various parameters that describe how the relationship works. In the case of a linear regression, the two parameters that are going to be tuned are going to be the gradient and the y-intercept in principle. More complicated models will have more parameters inside them that are going to be learnt as the model looks at your data. There are also things that you can tune on a model which you set once up front, which aren't learnt from the data, but you as a data scientist, which you were all becoming throughout the course of this course this afternoon, you want to set in advance. Now the things that it learns during the process are called parameters. The things that you set up front are called hyperparameters. And there's a hyperparameter that we might want to set on our model here, which is to tell it that we do indeed want to fit the y-intercept. Some linear regression models fix the y-intercept to 0, so we want to make sure that the y-intercept is going to be fitted as part of learning about the data. So we pass in another parameter, fit intercept equals true. And then we run that cell. So if you could all run those two lines of code now, make sure that scikit-learn is working, is installed, it's able to run at least that much, then I'll step on to actually fitting the data. We've now got our model. It's sitting there ready to learn. It's like a student who's just turned up at the beginning of class, doesn't know anything yet, but knows how to learn, but just needs to be given the information to extract the things that they really, really care about. Hopefully that's how you all feel, and you will learn something throughout this course. So in order to allow the model to extract the parameters of interest, which as I said are going to be the gradient and the y-intercept of the straight line, we have to show it some data. Now all models in scikit-learn have a nice consistent interface to them, and that's you type the name of the object that represents the model you've created, and you call the fit function on it. All models in scikit-learn have this fit function. As to the arguments that the fit function accepts, again, there's a good amount of consistency here, but it's important to understand the type of data that it expects you to pass in here. For a model like this, where we're showing it some data that we want it to learn from, and some more data we want it to learn to, i.e. the x and the y, the fit function is going to take two arguments, effectively x and y. But we can't just write x and y, we have to actually give it the data, which from above we've stored in our data object. The fit function expects the x argument to be a two-dimensional object. That is, we can't just pass it a single list of numbers, we have to pass it a table of numbers. Now we're going to get our data from our data table, which we had above, and we would, in principle, want to grab our x column from that table. The only reason we can't do that directly is that the x column from our table is only a single column, and with pandas particularly, if you extract a single column out of a table, it gives you back a one-dimensional object, basically a list of all the numbers. We want to tell pandas that we want to get a two-dimensional data frame out of our larger data frame, and so we have to tell it we want to get a data frame which is made up from the columns x. Now, in principle, if there were multiple, we would do x, x1, x2, etc. But in our case here, because our data only has one single x parameter, we just ask for a single x. And that is why we have these slightly strange looking double square brackets when we call the x parameter. That is to make sure that our x parameter being passed in is two-dimensional. It should be a table of data. One row for every sample, one column for every feature or x value. The second argument that the fit function takes is, unsurprisingly, the y data. Now, in this case, it is okay with the y data being a one-dimensional list because there is only usually one column of y data. For each sample, i.e. for each row, and I'll just scroll up, it is going to use all of the x's to work out what the y is. And then the next sample is going to find the relationship between all those x's and the y. So we're passing in our x data as a two-dimensional table and our y data as a one-dimensional list. At this point, we can go ahead and run that cell. And in that split second, it has gone and done the machine learning. It is computed some algorithm. I think it uses ordinary least squareds to calculate what the line of best fit through the data is. And it has now saved the results of that into this model object. So by calling the fit function, you have performed the machine learning step. Because we only got 50 data points and a one x value and one y value, it only takes a fraction of a second. With more complicated models, it could potentially take hours to run this single line of code if you were doing something a lot more complicated. If you could all run that line of code as well now, make sure that's working for you, and then I'll step on to the next section. The learnt parameters are now inside this model object, and this might be a case of you've got to trust me, they honestly are inside there, but you absolutely should not just blindly trust me. You should be asking the question, how can I get access to those parameters? It's all very well it having learnt about the data if we can't then extract out the stuff that it's learnt. The number one way that you get access to the data from the model is by calling the predict function. So the predict function, after the model has been fit, can then be passed in to x data and will make a prediction of what the corresponding y data should be based on the model that it's been able to create. Given that we've got a straight line, we will be able to plot a straight line of what our predictions look like simply by grabbing the upper and the lower points that we care about and then drawing a straight line between those 2 points. So let's grab our 2 points that we care about, our upper and lower bounds on the range that we're looking at. So we can get the lower bound with data, from the x column dot min. That's going to be the smallest x value, and then data from the x column dot max. Let's stick that inside a list. It's a 2-item list. And then for sake of getting things in the right shape, we want to turn this into a table of data. So I'm going to do the similar thing to what I did before, frame, where I make the x data into a data frame. I'm going to call that x fit. Because I'm now using the data frame, I've got to from pandas import data frame. The reason I've done this data frame thing here is because we're creating x data again. And the same as with the fit function, our x data had to be in a 2-dimensional table. Likewise, with the predict function, our data has got to be inside a 2-dimensional table. We can then pass that to our predict function. It's going to make a prediction once for the minimum value, give us back what the corresponding y value is, and then it's going to do it again for the max value and give us back the corresponding y value. So this will give us back 2 pieces of data, which we are going to save into y predicted. Best way to visualize things is to plot them. So let's do data.plot.scatter, exactly the same as we did before, x and y, So we're plotting our overall data there. Save that plot so that we can plot the other data on the same pair of axes. And on this second pair of axes, over the top of the scatter plot of our data points, we are going to plot a straight line with the x values x fit and the y values y predicted. I'm also going to set the line style to be a dotted line. That's how you do that in Matplotlib. So now if we run this, we get our original data as we had it before, but we also get plotted a dotted line showing what the model has made a prediction of. This dotted line has been created by predicting a point down here on the bottom left and predicting another point over there on the top right, and it's drawn a straight line through the two of them on this line here. So visually, it looks like it's doing a good job of predicting what our data is. The question is, a visual representation of our data is only so useful. Often we want to be able to extract numerical values from our data. In order to do that, the data has been saved onto this model object, and so we can extract that out. So I'm going to make another cell here and have a look at some of these pieces of data. So the coefficients, which is going to be the gradient of the line, are saved in an array on the model object, which is in this case got the value, so one element array with a value of 1.977. The reason the coefficients are returned as an array is to have a consistent interface in case we were fitting over a polynomial of some kind, in which case there will be multiple coefficients here. So since we've only got one, we'll just ask for the 0th coefficient. And we can also have a look at the intercept. You'll notice that both of these attributes have got an underscore at the end. That's a scikit-learn convention used to represent attributes which only exist after the fit has been performed. So if you ask for these and you hadn't yet run fit, you get an error. The underscore tells you that this is a learnt attribute, or learnt parameter, I should say. Have a look at what the intercept is. No, I did that wrong. Have a look at what the intercept is, and it says it's minus 4.903, etc., etc. Now I expect on your computer you've got exactly the same numbers as these, and that's because this is a relatively deterministic algorithm. There isn't much randomness going on, and so since we've started with the same set of data, we run basically the same version of the fitting package, we end up with exactly the same number at the end. If you were on a different version of scikit-learn, maybe even on a different version of Python, you might end up getting slightly different results here, but they should always be the same to a certain number of decimal places. So this is telling us that we've got a line that is being represented more or less by the equation y equal to 1.977 times x minus 4.9. Look at minus 4.9, we see on the plot above that it does probably hit the y-axis at minus 5-ish, and the gradient is about a gradient of 2. So these numbers are fitting with our expectations. As it happens, this data was created from a gradient of 2 and a y-intercept of minus 5, so the slight difference here is down to the randomness that I introduced into the data. So have a go with doing that yourself. Run the same model above and try fitting it all out. The exercise that I'm showing you here is at the bottom of the fitting data chapter. All of our exercises are in these yellow boxes. So have a go at fitting that data, making sure you get the same thing above. Once you've got that working, have a go at doing the same process on a different data set. So scikit-learn comes with a bunch of example data sets, which you get through sklearn.datasets. There's one which represents diabetes patients. So try doing a line of best fit between the BMI column and the target column inside there to see if there's see what the relationship between those two parameters is. I'll give you a few minutes to have a go with that, and then we'll carry on to the next section. I'm going to go through the answer to the diabetes example now on the screen so that everyone has an example of how it's working. As with all of the exercise today, there is an answer linked in the notes, so you can always check that if you're struggling, but sometimes talking it through is a better way to learn. So down here, I'm going to make a few cells, and I'm going to paste in the bit of code that was basically given to you. Here we're calling the load diabetes function. It's giving us the data. The title, the column headings are coming from the function's feature names attribute. And we also take the target column. This represents the Y that we were talking about before, and we put that into the target column. When we look at that, we get some data that looks like this. So we've got age, sex, BMI. That's the column that we're interested in for doing our linear regression. A bunch more parameters, which are documented, but I don't know what they mean, and a target column. So the question we're asking here is, what is the relationship between the BMI column and the target column? So the first thing to do there, really, is to do a fit. Now we do that using AX equals diabetes.plot.scatter BMI and target. Have a look at that and we see there's definitely a loose relationship between the two of them. It's a very wide distribution, but there's definitely some kind of relationship there. But we want to be able to extract out a numerical value which represents the two of them. So let's do that same thing we did before. Model equals linear regression. We want to make sure we're fitting the y-intercept. And then we fit our model with model.fit. Here again, we need to make sure that our x values being passed in are two-dimensional. So we do diabetes square brackets, and then we want to do a second pair of square brackets and ask for the BMI columns. As our y value, as our target we're aiming for, is our y-axis, which is going to be diabetes target. If we run that, it's going to fit the model, but we want to also plot our model. So I'm just going to copy and paste these two lines of code. They're exactly the same things we did before. We get the minimum value from the BMI column and the maximum value. We make a prediction for each, and then we are going to plot that prediction onto the same axis. Line style equals dotted line, and this time let's make the line red, make it a bit more interesting. And there we go, it's made an estimate of the relationship between those two things, and it's plotting the line. So you see here, no matter what data you've got, as long as you've got an input column and an output column, you can always extract the two of them. Sure, there's a question in the chat there, Abada, asking, can you explain why the X data should be in a 2D array? So the reason for that, and I'll get onto this in a bit more detail in the next section, is that in general, your data is going to have multiple measurements you made, and then you want to make one eventual prediction. So the example I use in the next chapter is that you're maybe trying to come up with a model which is able to predict the price of a house. And so you might want to work out what the price of a house is based on the number of rooms in the house, the size of the garden, and how many schools there are nearby. So you've got three things of interest that you've measured, and based on those three things, you want to be able to predict what the house price is. And so because in principle, your thing you're learning from can have 2, 3, 4, 1,000 different columns or features that you're looking at, the fit function in scikit-learn will always assume that your X data is going to be a set of columns. It's going to be a two-dimensional array. It's going to have a row for each sample. In this case of the diabetes, each sample is a person. In the case of the house price data, each sample is a house that you've measured the number of rooms of, the size of the garden, and the number of schools in the area. So because the fit function is always assuming this is going to be two-dimensional, even if we only have a single column of data, we have to pass in a two-dimensional object which represents even a single column. To explain how this syntax works a bit more, let's have a little look. So let's look at diabetes. Let's look at the whole thing. There we go. So that's the whole table. It is two-dimensional because it's got rows and it's got columns. A row in these tables is often called a sample or an example or a measurement. In general, each of these column headings are called a feature because they're a different feature of the data. You have an age feature and a sex feature and a BMI feature. In the table here, we've also got the target, which is, well, sometimes it's called the target, sometimes it's got other names, but in general, we're going to call it target here. If we look at the number of dimensions of this, which you can use using ndim, it tells us it's 2-dimensional. If we look at the shape of our data, we see it's 422 by 11. 1 dimension, 2 dimensions. So here we've got a 2-dimensional table of data. We want to train our model based on the BMI column. So let's have a look at what that looks like if we just extract the BMI column. It gives us back a single column of data. These are the data in this column. The numbers here are just row labels. So we have a single 1-dimensional column of data. And I can prove to you that it's 1-dimensional by copying that code, pasting it, and doing ndim. And it tells us that it is indeed 1-dimensional. We want to extract this same data here, but we want to have it represented as a 2-dimensional object because Fit always wants your data as a table with n columns. Whether n is 1 or 1,000, it wants it as a table of data. And so to do that, we do diabetes, square brackets, and instead of just doing a single object there, we can pass a list of column titles. So we can pass BMI and age and sex. And when we print this, we get out a subset of that table with just those columns in. If we look at the number of dimensions, of course, it's 2-dimensional. Using this same syntax, we're passing a list in here, but we can pass in a list with only one item in, so we can delete those two things. We're still passing in a list, but it's only got one object in. But because we're passing in a list, Pandas is going to give us back a table of data at the end, rather than a single column. So that gives us back a table of data, in contrast to the single column of data we got here. And that is happening because of that extra pair of square brackets. If we look at the number of dimensions of this, we see that this is now 2-dimensional. So scikit-learn always wants the X data to be as a table because in principle it can have multiple features. In our case here, we only have one feature, but we are still having to pass it in of the same shape of data. Most programming tools have an assumption about shapes of data and so on because it makes their internal logic easier. If we only passed in a 1-dimensional thing, it wouldn't know whether we were passing in a single column with multiple samples or a single sample with multiple features, for example. So I'm going to talk a little bit first, before we get on to other techniques, about what machine learning is, how it works, and how you can think about starting to apply it to your data. And by apply it to your data, I mean think about what it's possible to do with it, so you know what questions you can ask of it, so you can plan right from the beginning to use machine learning in your analysis by making sure you've collected your data in the right kind of format. But on the whole, there are two main classes of machine learning. We have supervised methods and we have unsupervised methods. Now, a supervised method of machine learning is one where you've got a set of features, a set of x's, and you want to, based on the values of those features, predict what the value of a target is going to be, what the value of y is going to be. So a supervised model is one where you're finding a relationship between x and y. You're trying to learn out how to get from one to the other. Remember that x can be multiple different features, so you're trying to see how to get from those data to the y target data. So that's what a supervised model is. Now you can see the linear regression we were doing in the last section was one of those. It was a supervised model. We were trying to find the relationship between our x column and our y column. Similarly with the BMI example, we were finding the relationship between BMI and target. Within supervised techniques, there are two main categories. Those fall into classification and regression. So a regression is what we were finding with our linear regression, hence the name, just there. Our target was a continuous value. Based on our inputs, we were trying to find out where on this scale our estimate was going to end up. With the house prices, that's a regression example because we are trying to guess what the price of this house is going to be from £0 up to £1 billion. It's somewhere on that scale. That's the range of value we want to predict that we want to end up inside. By contrast, some supervised techniques are going to do what's called a classification. They're going to take the set of features, the set of inputs, and it's going to put them into one of a set number of buckets. For example, you might be trying to work out what species a particular kind of flower is. You take some measurements of it, and at the end of the day, you're not going to find out how much of one species or another it is. It is going to be falling into species A, species B, or species C, for example. So they're both starting with some features and trying to end up at some kind of target, but whether that target is quantized or continuous tells you whether you're doing a classification or a regression. So the thing we did in the last section was a supervised regression. Most of the time when people think about machine learning, they are talking about supervised methods. They are talking about these kinds of things where you're finding a relationship between your inputs and your outputs. If you're doing a technique where you're trying to take a picture of an animal and tell you if it's a cat or a dog, that's a classification. If you're trying to take some features about a person and trying to work out whether they should have a loan because they're going to be likely to or not pay back the loan, that could be a regression because it's giving you back a probability which you're going to interpret. The other major class of machine learning is what's called unsupervised. Unsurprisingly, given the other one was called supervised. Now, an unsupervised machine learning model is one which doesn't have a target. You have all your features, you've got all your x values, but you don't have a y. You're not trying to get to a particular place. You are just trying to understand some internal relationship between all of the features that you're putting in. It can be a little bit hard to understand how it can possibly learn anything if it doesn't know where it's supposed to end up. But depending on the kind of question you're asking, there are things that you can extract about your data. The two main classes here are clustering, where you're trying to find subsets of your population of samples and put them into buckets. It's kind of like a classification, but where it's working out its own categories. Or things like dimensionality reduction, where it just looks at your data and it tries to just simplify it in some way. So it's not trying to get to a particular place, it's just trying to reduce down the amount of information you have to think about. So these techniques are often used in concert. You might do a clustering before you do a classification or something like this. They're not, you don't just use one technique and call it done. You often have combinations of these things. But if there's no question on that first section there, then I'm just going to talk through now the process that you go through for supervised learning. Because supervised learning, as I said, is one of the most common techniques that get used. And it's often what you end up doing in your research or scientific contexts. You've made some measurements and you want to make a prediction because you don't want to have to run the real experiment every time because experiments are expensive and difficult, or maybe they can't be run because they were time-based in some way. So you want to make some kind of computer model which is going to represent what you think is happening in that experiment. So the supervised learning process is a fairly standard set of steps that you'll go through, and it all starts with collecting your data. Well, I suppose it starts with deciding the question you want to answer. Let's say, as I was mentioning before, that we want to have an example where we are predicting the price of a house. We want to measure how old the house is, how many rooms it's got, and the size of its garden. Those are all things which are easily measurable. Anyone can count how many rooms a house has, measure its garden, and look up on some records how old it is. But it does take an expert, or it takes the market, to work out how expensive a house is going to be. And it is a question you want to answer before you go into the process of trying to sell your house. You want to make sure you're going to get your money's worth for it. So in order to work out a model which is going to relate the price of a house with those features of it, we need to go out and collect some data to train a model on. So the first step here is to go out into the wild and find some real houses, measure their features, measure their ages, number of rooms, size of gardens, etc. And for each of those, we've got 3 features. So we've got 3 columns in our table. Each house is going to be its own row in the table. And those rows and columns, those features and samples together, those are what make up our X. Those are our things that we're going to be learning from. That is our input to our model. So we take those things, we measure our X, and we set that to one side, we write it down in our notebook. While that process is going on, for each house that we've looked at, we also want to work out what the price of that house is. Now, we only want to do that process for the subset of data that we are looking in detail at. So we do this as a one-off, just for this set of data. So an expert looks at the price of the house and assesses it, or maybe you look at the market records for recently sold houses and you do that slightly more intensive process, and we put that list of house prices in our Y column, so that each row now has the 3 features and a target and a Y. So now we've got all our data. We've done our initial data collection. We are now ready to start doing machine learning to it. The first thing to do before you just start throwing computers at something is to think about the kind of data you have, the shape of the data, the quality of the data, these kinds of things, and think about what relationships are there or do you want to discover between X and Y. In the example we had in the first chapter, a linear regression was just fine, but sometimes there's something more complicated. Deciding which model to use comes with experience and experimentation. It takes some time to discover what tools are out there and what possible things you could use to solve the problem you're trying to do. But let's say we've decided we want to use a linear regression, some kind of multivariate linear regression to represent these things. So we just choose our model, we import it into scikit-learn, let's say, and using our X and Y, we throw them at the machine learning. We let it do its thing. We call the .fit function, as we did before. The machine learning algorithm goes away and does its thing. We don't really have to care too much about how it works behind the scenes. We just trust that it's doing the right thing. At least at this point. Later on, you will want to understand more about how they work. But for now, we're happy just to learn it. Once it's finished learning about the data, we can now effectively throw our data away. You shouldn't. You should keep your data, but you no longer need it for that model to do anything useful. That model has internalized and simplified the relationships between that data down into a few internal parameters. And so now we can use that model to make predictions. It will look up the value of those internal parameters, stick them into some kind of equation, and give us back the answer. So that means in a year's time, someone can come along to us and say, hi, I want to sell my house. We ask them how many rooms it's got, size of the garden, etc., etc., etc. We put those 3 numbers, which I'm going to designate X prime here for sake of argument because they're different to our X from before. We put those numbers into our model and it gives us back a estimate or prediction Y hat. Now Y hat is commonly used as the designator for a predicted value from a model. So you'll see that crop up quite a bit. Y hat is a prediction from a model. Now Y hat is just a prediction. We don't know that it's correct. There is, for any given house, an actual price that that house is worth. It might not be calculable, or it might be hard to calculate, but there's a real value out there. And so in principle, there is a measure of how right we are. If we imagine that person sold their house the next day, we would immediately know how right we were. Now, the measure of how right you are is sometimes easy to calculate and sometimes it's hard, but usually you can go a long way by simply subtracting your prediction from your real value. Now, you don't always know your real value, so that's not always easy. But if you do, just do a difference between the two of them, and that gives you back what's called the residual. Now, the residual is, in general, a measure of how good you did. It's what left over, is what residual means. So I've gone through this section here just to give you an idea of some of the terminology, give you a sense of how the flow of data works, and when things are used and when they stop being needed to be used. Now we've got a sense of the general process that you go through when you're trying to discover relationships in your data. I think it's worth taking a little step back and thinking about, before we throw machine learning at our models, what we can do to discover information about them, because the shape of our data, the type of our data, often strongly informs both what models we can use and how we should go about applying them. And I think one of the really important things to look at when you've got large data sets is looking at the correlation between your data. Now, correlation is one of these things which I feel is oversimplified when it's taught. And so I'm going to go through now what I feel is a better explanation of what correlation is and how it can be useful without going into the maths and so on. And then we're going to see situations where that nuanced opinion of it can actually start being quite useful. So when you're taught correlation at school or university, you're often told the full description, but it's often very, very quickly simplified down to how linearly related are these two parameters. By that I mean, as one parameter increases, how much does the other one increase, and vice versa. As one goes down, how much does the other one go down? That's a useful measure of data. It's a useful thing to understand. One of its real powers is the fact that it's really easy to calculate. Finding out linear relationships between data is almost trivial. There's a good number of easy to use and implement algorithms out there for finding out what the linear correlation between two values is. So I'm not trying to diminish the value of linear regression, but I think there is more to be said about regression than simply how linearly related things are. So you see on the screen here, there's a single plot. It's got an x and a y value. It's got a scatter in the middle. These two values here are strongly, positively, linearly correlated. As x increases, so does y, and as x decreases, so does y. So it's positive because they're both changing in the same direction. It's linear because there's no kind of strange shape to it. And they're correlated because, well, we've got a strong value for that correlation. But beyond linear correlation, I think there's more to be said. So I find it more useful to, instead of thinking about correlation in terms of as one goes up, how much does the other one go up, to instead think about in more detail how related the two sets of data are. Now, this is going to consume linear correlation, but it's a broader concept. So I like to think of it more in the sense of, if I know the value of one of the variables, how much do I know about the other? How much information do I have about y if I know the value of x? So looking at this parabola plot on the screen here, if I worked out what the linear correlation of this was, it would probably tell me that it's 0. If you plotted a line of best fit through it, a linear line, it would just be a straight horizontal line going straight through the middle. So that would be saying that the linear correlation of these two variables is 0, and so there's no relationship between the two of them, or at least that single parameter would simplify it down to that point and would say there's nothing that you can say. If you know x, you have no information about y. That's what linear correlation would tell us. Yet, clearly, looking at this plot, we know if we've got the value of x, we can make a really quite good guess about what y is. If x is 8, for example, well, y is about 15. There's no way that y is going to be 0 or 30. It's going to be about 15. Likewise, if x is 0, then y is going to be about 0. So there is definitely a strong correlation between these two things, but the linear correlation is 0. And this is why I think it's worth thinking more broadly than linear correlations. It comes into play as well because a lot of machine learning models are more than linear. They can discover superlinear relationships between things, and so us being able to describe them is a really useful thing to be able to do. In a more mathematical sense, the way that I like to think about correlation is really in terms of mutual information. And there's a really good, slightly mathsy Wikipedia page on mutual information, which describes this well, but it effectively comes down to how much information overlap or how much information sharing is there between x and y. If there's perfect information sharing, then they are completely overlapping in the Venn diagram, and so they're exactly the same piece of data. If there's no information sharing, then that's saying there's no correlation at all. But if there's some, then you can find out something about y from x, and probably vice versa. So thinking about mutual information and information overlap between your sets of data, I think is a better way of thinking about correlation than simply what is the single linear correlation value of these data. That said, we're going to jump straight into linear correlation because, as I said, it's really easy to calculate, so it's a good place to start. So I'm going to make a new notebook. I'm going to call this one correlation. And I'm going to load up some data. I'm going to import some pandas and NumPy to get some data out. And I'm going to make a list of data, np.arange. This is going to make a range of numbers from 0 to 99. That's what the 100 means. I'm going to make a second variable, which is going to be exactly the same, except this one is multiplied by 2. If I plot this data by sticking it into a data frame, and have a look at the top of it. This is what we see. So we've got one column A, one column B. The numbers are both going up as the other one's going up. So immediately you're probably thinking, well, these are strongly positively correlated. That's a good place to start. So you're almost definitely correct. But with any data like this, there's some other things that we can learn about it along the way using the tools that Python provides. So this data frame df, before we jump in and calculate the correlation, there's a function called describe, which is worth knowing about, which gives you very basic summary statistics about any given data frame. So when we run that, we see printed out how many values there are. There's 100 because we asked for 100 of them. The mean is about 50 of the first one. The second one, the mean is about 99. That's because the first one goes from 0 to 99, and the second one goes from 0 to 200-ish. Doing this describe thing is always a useful thing to do because it gives you a sense of the skew of your data, because you've got your percentiles, your standard deviations, things like that. So it's always worth having a look at your describe just to make sure you haven't got any weird values, weird outliers hanging out. It's a very nice, easy way to spot them. So a question there about why do we use a dictionary for this data frame here. I did that so that I could take this value here, which is this first column, and this value here in this second column, and give them column names so that it would be called A and B. If I did it just by passing a list, they wouldn't have had column names, and so we would lose track of which one was which. Once we've got our data frame, as well as calling describe on it, we can just go ahead and call the correlation function, or as they call it, core, because typing elation is far too much work apparently. And it gives us back a nice small table summarizing the correlation between the two values. First thing to point out on a correlation table like this, you might have come across these before, but if you haven't, then the diagonal terms here are telling us what is the correlation between A, and it's 1.0. And the second value here is telling us what's the correlation between B and B, also 1. We'd always expect the diagonal terms to be exactly 1 because each data set is always perfectly correlated with itself. It is the off-diagonal terms which are the more interesting ones. In this case, they are also still 1.0 because A is perfectly correlated with B, and inversely, B is perfectly correlated with A. Each side of this matrix here is often the exact copy of the other triangle, so the top right is always the same as the bottom left. So have a go at that yourself, run those commands, make sure it's working, then try tweaking your A and B up here so you get a pair of data which are inversely correlated with each other. So they've got negative correlation such that you end up with -1 on your off-diagonal terms. Okay, great. Abada posted in saying that you just multiplied that by -2. That's exactly the right idea. So, as I was saying, positive correlation is if one goes up, the other one goes up. Negative correlation is if one goes up, the other one goes down. So if we make that to be going down each time as A is increasing, B is decreasing, when we look at the correlation, we get -1 on the off diagonals. To get anything which isn't exactly -1 or 1, we'd have to add in some more interesting variants to our data, which require some random functions or just manually doing it. So instead of doing that by hand, let's have a look at some real data and see what we can learn about it. And also how we can do correlations between more than just one column and another column in a boring made-up data set. So again, we're going to have a look at scikit-learn's datasets area. This is where we got the diabetes dataset from before, but this time we are going to import the fetch California housing dataset, and we are going to save that as housing data equals that. So we're just grabbing the data there. I'm then going to put that housing data into a data frame so that it gets presented in a slightly nicer looking way. Data frame housing data dot data as the data in the table itself, and housing data dot columns as the column names are the feature names of that data set. I'm going to call that housing, and I'm going to print out the first few rows of it so we can see what it looks like. So what we have here is a table of data. We have 1, 2, 3, 4, 5, 6, 7, 8 features. The target column is loaded separately, so these are all X. This is basically a big table of our X data. We've got 8 columns and we've got some number of rows. We'll have a look in a little bit and see how many rows there are probably. The meaning of these columns are each row is a census block in America. So it's 100, few hundred people or something like that. So it's some number of houses, but a small enough number that the variation within that little block should be quite small. And we're finding out for each of those blocks what the median income of the people who live there is, the average age of houses, average number of rooms, average number of bedrooms, the population of that area, so 300 people, 400 people, that kind of thing, average number of people per residence, and also where that census block is, so we have a bit of context for that stuff. So before, when we did the correlation function, we took our data frame and we plotted the core function for it, we called the core function for it, and that gave us back for each column the correlation with every other column. With only 2 columns, that's pretty boring, but the exact same syntax works no matter how many columns you have. So if we do housing.core here, it's going to think a little bit harder about it, but it should only take a fraction of a second. And it gives us back a table of data. This table has 8 columns and 8 rows. Again, the diagonal terms are all 1.0 because the age of a house is always correlated with the age of the same house. So we get 1 on all the diagonals, on this main diagonal, sorry. Again, notice that the 2 different halves of the matrix are exact copies of each other. So this value here, minus 0.11, is the same as this value here, minus 0.11. So you can often get away with just looking at one half of the table. Because we've now got this as a real pandas data frame, we can drill down and find out more information about what's going on. So we can, let's actually call this core. And refer to that variable. So we can ask for the median income column. That's going to give us back that one column. Oh, I didn't run that cell. There we go. That gives us back that one column. And then from that column, we can extract out a row like average rooms. So this is going to tell us what is the correlation between the median income and the average rooms in this particular data set. And it gives us a slight positive correlation. So it's telling us that on average, as the income increases, so does the number of rooms, but it's not a solid increase. There's a fair bit of variance to it. So have a go running that code yourself, get that loaded in. And what I want you to do is to have a look at this table of data and see if you can pick out by eye what the most negative and the most positive correlations are in that table. See if you can do it by eye. If you want to, you can have a go at writing some code to do it. It's perfectly possible. But doing it by eye is the first step in that process to get a sense of how this stuff works. So I'll just give you a minute or so to look at that by eye. If you want to have a go at the code, feel free to do it now or later on. And then we'll have a little discussion about what we're seeing here. Could anyone tell me what they think is the strongest negative correlation? Okay, great. And what is the strongest positive correlation? Yeah, rooms to bedrooms is a strong correlation between there in the positive direction. Now that positive correlation makes a lot of sense. We'd expect that if houses have got more bedrooms, they've therefore got more rooms and vice versa. However, that process probably wasn't painless. Scanning through a table by eye, going up and down these columns one by one is hard work. You have to peer into it and try and look at the numbers, remember what the biggest or smallest number you've seen is, and so on. And so, as you all know, plotting large amounts of data as a table isn't the right way to do it. We want to visualize it in some way and make it easy for our eyes to see. So we are going to plot this same set of data here, but in a visual way. So let's have a look at how we do that. I'm going to use a package called Seaborn. which is a plotting package which builds on matplotlib but adds in a bit more functionality, slightly nice API at times, but it adds in at least one default, easy to draw matrix plotting of correlation functions, which is going to be useful for what we want here. We're going to import it as SNS because that's convention. And we're going to do SNS dot heat map, and we just pass in that table. In order to make this look a bit nicer, we're also going to give it a color map so that 0 is a nice neutral white, strong numbers are going to be blue, and strong negative numbers are going to be red. So to make a diverging color map, we are also going to do SNS dot diverging palette. And this is one of the things that Seaborn provides, is nice, easy to use functions like diverging palette, where you specify where you want to start, where you want to end up, and that you want it to be used as a color map. And we pass that to our plotting function with cmap equals cmap. And when we plot this, we get our, actually I'm going to do 220 because it's a slightly nicer blue. There we go. So here, much more easily, we can immediately spot our positive and our negative strong correlations. So looking at the upper end of this graph, we see that blue is used for a correlation of 1. We see strong blues along the diagonal. We also see a next strongest blue between average bedrooms and average rooms. So we're immediately seeing there's a strong correlation there. We didn't have to scour the numbers, we just plot it and we get it out straight away. And so I would recommend the first thing you do with your data is grab it in, look at some of the summary statistics, have a look at the correlation between them. It's worth looking at the table, but don't spend too much time on it. It's a good idea to go as quickly to a plot as you can, because you're going to be able to spot interesting things much more quickly. This here is showing the linear correlation between the variables. So it's telling us that the linear relationship between average bedrooms and average rooms is, 0.32 we saw before, so it's relatively strong. But it isn't necessarily telling us the whole story. We saw before that linear correlation is only a part of how you can describe the relationship between data. It doesn't give us enough information to learn everything about it. So we want to be able to look at the relationship between these variables in a more nuanced way than reducing it down to a single number representing the linear correlation between the two variables. Linear correlation gives us a nice square rectangle on this plot, but we want to get some more information, more detailed information about what's going on. And so Pandas provides a function to help us do this, and it is called scatter matrix. So Pandas, which is how we've been loading our data, has got a plotting sub package, and from there we can import scatter matrix. You use scatter matrix. I'm going to assign it to a variable here because otherwise it's going to print a load of nonsense to the screen, with scatter underscore matrix, and we pass it housing. By default it's going to plot it quite small, and so I am going to pass in the fig size argument, which accepts for some reason in inches the size of the plot, and so let's make it 16 inches square because I know that's about right. This will take a minute to plot, so do be patient with it. It's plotting all of the data, but it will eventually get there. So have a go at doing that yourself, get that plot up, and then I'm going to talk through how you read this plot because it's not always immediately obvious. There we go. So that's showing up on my screen now. So while yours is running, I'm actually going to switch to the notes and get the picture because it's easier to make it big. That is the plot of all of the data. It's effectively the same information as we had before with the correlation matrix, but instead of the relationship between each variable and each other being summarized down to a single variable, it's instead plotting the scatter plot of the relationship between the two. So the best place to look first is at the average bedrooms and average rooms column and row. So that's row 4 and column 3, for example. They had a strong positive correlation, and looking at the data here, we can see why. There is definitely a longitudinal blob going from the bottom left towards the top right. That is therefore making sense. As one goes up, the other one goes up, the linear correlation is strong, and so we're seeing something going on there. But looking at the other parameters on this plot, some of them are definitely a bit more nuanced than just a longitudinal blob. For starters, many of them are very, very skewed distribution. In fact, almost all of them are very skewed distributions. The easiest way to see the skew on the distribution is to look at the diagonals. Looking at the very top left square, for example, there we see what would be the scatter plot between median income and median income. They realised that actually there's no point in drawing that scatter plot, and so they repurposed the diagonal terms on this plot to be a histogram of that variable. So this here is just a distribution of how many entries there are with a median income that's at the low end, at the medium end, and then up towards the high end at 15. So you see here there's a skewed distribution slightly towards the bottom end, but it's not completely skewed across. House age is also nicely balanced. House ages go up to about 60 years or so that's traditional American houses not being very old. And you see many of them are much, much younger than that. When we got into the average rooms and average bedrooms graphs, however, we see there's a very, very skewed distribution. So much so that it looks like it's entirely inside the first bin and nothing in any of the others. Now, it can't be there's nothing in the others, otherwise those bins wouldn't exist. It's simply that this first bin, if you look at the x-axis, is covering everything from about 1 room up to 10 rooms or something. And I think it's fair to say that most houses have 10 or fewer rooms. These larger entries up here, of which there are many fewer, will be mansions or tower blocks or mistakes in the data, potentially. So those are very, very skewed distributions. Down in the bottom left, we see there's sort of the distribution between median income and latitude. There's some structure here. It's not linearly correlated in any sense, but there's definitely some information there. So there's something that we can do with that, potentially. There's something that a machine learning model could discover about that relationship. The last thing to point out on this plot is I was asking before if you could point out what the strongest negative correlation on that table was, and you all pointed out that it was the correlation between latitude and longitude. And that doesn't necessarily make sense to me. Why would the latitude and longitude be correlated on a table like that, on a piece of data like this? We don't expect, to think about a map of the UK, that as the latitude goes up, the longitude should go up, because most places are kind of square blobs. Most geographical entities are roundish. But yet here we were seeing a very, very strong negative correlation. And more interestingly, that is consistent with what we're seeing in our scatter plots here. We see a very strong negative slew of data going from the top left to the bottom right when we're looking at our scatter plots down there in the bottom right. Now, has anyone got any ideas why we might be seeing this kind of correlation between latitude and longitude on this data set when we wouldn't normally expect there to be any relationship between them at all? Has anyone got any ideas? So Joe's saying it could be the coast. Yeah, so absolutely. There's some geographical things going on here. Clearly, where the coast is going to come into effect. It's going to bound the data in some way. So that's going to affect stuff. But the UK has a coast, and I don't think the UK would have this kind of correlation. Anyone else got any other ideas? Yep, okay, so Abada's hit the nail on the head. Think about it for a moment. What do you get if you plot the longitude against the latitude of something? What you get is a map. If you plot the longitude and latitude of all of the census points on a grid, you get a map of all of those census points. It so happens that California is a shape which goes from the top left to the bottom right. It's an artifact of the location as to where this data was collected. This same data set in another state in the US, even with very similar conditions, because it would be a different shape, would have completely different correlation between its latitude and longitude. It is a particular feature of this data that we're seeing this. It's not necessarily something that we would expect. So we've accidentally drawn a map here without realizing what we were doing. I believe that it's the one on the top right that's the map and the bottom left is something else. In fact, if you look at it, you can almost see San Francisco going around the bay, though it's a little bit blurry due to some desert and mountains that get in the way a little bit. Yeah, exactly, Jafe. It suggests people on this one live in a line between those two things, but because we've taken a subset of our data by choosing California, it's kind of imposed that condition on the data when it wouldn't necessarily be there in the first place. It's not a natural thing, it is a data artifact. And this is something that's worth being really, really careful about when you're collecting and analysing data. We could have looked at our data here, thought that this was just a spurious bit of correlation, ignored it, carried on, trained a model based on this stuff to predict what the price of a given house would be, based on its longitude, its latitude, its occupation, the number of bedrooms, etc. We get a model which predicts it really well for California. We do our testing and our validation, and it would all be working well. Even if we took that model to somewhere else in the US, which is similar-ish, somewhere like, I don't know, New York or Washington, you would apply it and suddenly the whole model would collapse and fall apart because the longitude and latitude data has been baked into the model when really it's not relevant to it at all. It's found a relationship there, but it's not a general relationship. It's only a relationship which is specific to the place where the data was collected. It's a Californian relationship. It's not general. So that's a really obvious example once you see it, but the thing to remember is that all of your data is biased in this same way. You always have to be careful about what implicit or explicit assumptions have gone into the data collection, the data sampling, and what models you've chosen. This one here, you can spot it quite quickly. It jumps out when you look at the correlation. You see that there's some structure to it when you look at the data scattered on a plot like this. But you're not seeing it in the other parameters where there is also likely some data relationships which are slightly more hidden. So it's always worth being careful, thinking about where your data is coming from, how you're choosing to analyze it before you put it into your models, and where you then use that model, both elsewhere in the world and over time. Of course, a house price model isn't going to work if it was trained in the 80s and is being used in the 2020s. It's going to give you the wrong answer. All models have bounds, and part of your job as a data scientist is to think really carefully about what those bounds are, both to make them as broad as possible and to understand them so that you don't use a model in a place that it shouldn't be used. So the last thing I wanted to mention about correlation now is why we care about correlation in the context of machine learning. So there are two kind of competing ideas when it comes, or two competing concepts when it comes to correlations. The first is that between the features that go into your X, the things that you're training your model based on, for example here, average rooms and population, we don't want there to be a strong correlation between those two parameters. And this comes back to thinking about it in terms of information sharing. If we looked at average bedrooms and average rooms, they are strongly positively correlated. So we could train our model ignoring one of the two of them. So we just do it with average bedrooms and we'd get perhaps a good model coming out. If we then add in the average rooms parameter, we're not going to be adding much more information into our model because the information overlap between something that's already there is quite large. So we're adding in more data, we're adding in more processing time, but we're not adding in more information. And so that's going to make our model train slower, potentially behave worse, for very little benefit. So looking at the correlation between your variables and thinking about what variables you no longer need, that you can get rid of, or that aren't going to give you any useful information because maybe their skew is so much that they are all inside one bin and you're never going to be able to see anything, is a worthwhile exercise. There are techniques you can do to re-parameterize your features. There's things called dimensionality reduction algorithms. For example, principal component analysis can work out a new set of dimensions which don't have correlations between them, which are orthogonal to each other. And that's a kind of technique which you might want to apply to your data, and there's some information at the end of the course about where you can learn more about that. The other thing to think about with correlation is that while you don't want correlation between your various input values, you do want some kind of correlation or mutual information between a feature and your target. In fact, you need information overlap of some degree between what you're putting in and where you're trying to get to. Otherwise, there's no predictive power. If we were putting into this plot here the favourite colour of the people in each of those areas, that would have no correlation whatsoever with the price of the house. And so that would be a useless piece of information to put in. So looking at the correlation between your inputs and your output is worthwhile as well, because if they've got a strong correlation, then you're going to be able to get a lot of information out of it. And by strong correlation, I mean more than just a strong linear correlation. I mean a strong correlation in the broader sense of what kind of structure is there to the data. So between your features, you don't want correlation, but between your feature and your target, you often do want correlation. The next technique I wanted to cover was clustering. So if you remember near the beginning of the session, I was talking about the different kinds of machine learning. I was saying there was the supervised techniques, which have an X and a Y, and you're trying to find the relationship between X and Y. And there was the other techniques, which were the unsupervised techniques. And these are tools where you show the algorithm your data, and it just tries to learn some kind of information from the data or extract some kind of internal data from it. Now, clustering is probably the most famous example of unsupervised learning. And when I was first learning about unsupervised learning, when it first came across the concept, I was very confused by the whole thing because I couldn't understand how you can have a computer algorithm which learns about your data without knowing where it's supposed to end up. So hopefully I'm going to be able to show you how that is possible and how it works and the kinds of questions that you can answer about it. So we're not going to worry too much about the exact technical definition of how k-means clustering works. We're going to dive in and start just doing stuff with it. But I will then probably refer back to this and explain to you about how the way that this algorithm is implemented imposes certain limitations on what's possible to do with it. So I've made myself a new notebook here, and so I'm going to start off by making some data. Again, I'm going to start from scikit-learn. And scikit-learn's datasets module, as well as having built-in datasets like that California dataset or the diabetes dataset, also has some functions which allow us to generate data, sort of generate toy data. So in there is a function called make blobs. Can I just check that people can hear me okay? Someone in the chat was saying they couldn't. I'm assuming Lester can since he's narrating. Yeah, Lester can hear me at least, so okay, great. Welcome back, 7. So we've got our make blobs function. We can call that function, and it is unsurprisingly going to make us some blobs. There's some parameters we can pass in, of course. For example, how many sub-blobs do we want? How many data sample points do we want? And we want to do a largish number like 500. Then we tell it how many blobs we want. It calls them how many blob centers do we want, and we tell it that we want, let's say, 4. And because it's going to be generating these blobs randomly, and I want to first of all make sure that you're seeing the same random as I am, I'm also going to set the random seed. Now the random seed will make sure that while it's, the random state, sorry, will make sure that while it's technically kind of doing something pseudo-random, it's all going to be starting from the same place, and so we're all going to end up with the same set of pseudo-random numbers. And through extensive research before when I was writing the session, I found out that 6 is a good number. So let's go ahead and just use 6 for now. This returns 2 variables. It returns the data, i.e. the actual samples that make up the blobs, as well as which cluster each of those blobs originated from. So true labels. You can think of this as your X and your Y. I was saying before that since this is an unsupervised technique, we're not going to be using Y, and indeed we're not. We're going to not use this true labels variable at all in the training of our model. We're only going to use it to check how well we're doing, basically, if at all. So it's there as a cross-check for our educational purposes. It's not being used by the machine learning algorithm. So you run that and it generates the data. We then want to have a look at what this data looks like, because I'm sure you're all having trouble visualizing exactly what I'm talking about here. So let's go ahead and do a plot. I'm going to put the data into a pandas data frame first, because I like the pandas plotting interface. If you're comfortable with plain old matplotlib, then feel free to use that, but I like the pandas model. The points are then going to be that same data we got back from the make blobs function, but passed into a data frame. And I'm going to label the 2 columns as x1 and x2. Not x and y, because that would confuse with the features and targets that we had before. These are both effectively features of our data. We're not worrying about y here, because it's an unsupervised model, and so there's no y data. If the y data is anywhere, it's in this variable here, and it's going to stay there, out of the way, without us cheating by looking at it. Let's then plot our data, points.plot.scatter, and plot the x1 column against the x2 column. And there we have it. We have 4 different blobs, and we have 500 total samples, 500 little circles making up our plot. So first of all, I'm just going to ask you to just run those 2 lines of code. Make sure you've got that working, and you should see exactly the same blobs as I do. The same outliers, the same places of the centers, all that being identical. If you don't see something that's identical, make sure you set your random state correctly, and your number of samples and your number of centers. If you still get something different, well, it might be because you're on a different version, but I think they're relatively consistent. So have a go at doing that, give you 30 seconds, and then we'll move on to applying some machine learning to it. So we have here our x1 and our x2. These are input features to our model, in the same way that the size of the garden and the number of bedrooms are input features of the model. You might find that if you plotted size of garden against number of bedrooms, you wouldn't just see a spattering of data, you might see localized clusters of data in your output. Clustering is often used with large census data. For example, when you're doing a census for each individual or for each household, you'll end up with hundreds of different features describing that household. As a way of reducing the amount of information you need to keep about them, you might take a few of those features and simplify them down into some categories. For example, this is often done to put people into socioeconomic categories, whether they're working class, middle class, upper class, or whatever the new titles for these things are. Based on various features about the household to do with income and education and where in the country they live and so on, you might be able to cluster those features, find subsets of people which largely fall into one of a number of categories, and at that point you can effectively throw away those multiple features and replace them with one categorical feature, which is just which cluster are they part of, which can simplify analysis and also simplify human understanding of what's going on, because it allows you to take a whole bunch of features and put them into buckets and give them names, and that's useful for humans to understand what's happening. In order to analyze our data, let's go ahead and call the clustering algorithm. So again, from sklearn.cluster this time, not from linear model, but from cluster, we are going to import k-means. So k-means is a particular kind of clustering algorithm. It's called k-means because when you're deciding how you want to cluster your model, you decide in advance how many centers you want it to cluster it into. Another term for a cluster center is the cluster mean. And so if you want k means, you're saying you want k clusters, where k is a number between 0 and whatever. In our case here, we want to find 4 clusters, and so k is going to be 4. So we want to find 4 means. Same as before, we call our model like a function because it's a class we want to construct. There is a hyperparameter, which is the number of clusters. Deciding on how many clusters you want to use for your model is an art in itself. For example, when they were looking to try and work out how many different socioeconomic classes there are, and thinking in the last census we had, they changed the number and they reclassified them, they would effectively have tried a bunch of different number of clusters, seen which of those divisions worked best and gave them the best explainability, and then stuck with that. There's no absolute truth, except in the cases where it's been generated from something which has absolute truth, and we'll see an example of that a little bit later. In this case here, we generated this with 4 clusters, and so when we plot it, we also see there are 4 clusters, so of course k will be 4. We are then immediately going to call the fit function on it and pass in our points table. That is this table here, which is a data frame with 2 columns, x1 and x2, and 500 samples. I'm going to assign that to a variable. When I call this, it goes away, it does the algorithm, it's done the machine learning on those 500 points, and it's now put them all into categories. Have a go at running yourself that now, make sure you get that successfully running, and then we'll look about how we can extract the data from the model. Alistair's asking, can you get an algorithm to decide how many clusters there are? There are some techniques. I've never been very convinced by any of them. There's one where you look at effectively how good the fit is divided by the number of clusters, and you look at that for a different number of clusters, and you find the point at which that curve kinks most sharply. It's called, I think, the elbow finding technique, because when you plot the graph, it has a sort of an elbow shape, and you look for the point down in the bottom left where you've got fewer clusters but also fewer levels of uncertainty. If you actually try doing this, you'll find that there's never a single clear point at which you can say there are this many clusters. And so really, I would primarily say, let the number of clusters be informed by both your data and by the underlying model which you think that you're representing, and also by what data you're looking to extract. It often comes from starting at the point of, I want to divide my data into this many blobs, or I've looked at my data and I've seen it's probably this many. Beyond that, you can fiddle, and you might find that, oh, there's 10 or 11 or 12. And as you're changing those number of clusters, it could massively vary whether a certain sample goes into one cluster or another. And so you need to think about, what does that mean for your data? There's no magical way of doing it. There are tools that can help, but there's no magical solution. Once you've got your algorithm run, you've got your k-means object, which is containing the result of the fit. Let's go and see what we can see about what's inside it. So, k-means is the name of our object. Dot cluster underscore centers, spelt the American way, with an underscore at the end. Again, the underscore at the end is telling us that this is a computed parameter by the model. If we look at what that gives us back, it gives us back a NumPy array. I like to convert all of my NumPy arrays into pandas data frames because it prints them out more nicely. So let's make a data frame out of that and call the columns, because I know what the columns are called because they're the same columns we started with, are x1 and x2. Cluster centers, I'll use their spelling as well. And let's have a look at it. Oh, I've missed a bracket off the end. There we go, same data. If I array these so we can see them both on the screen at the same time, we look at cluster 0, it's saying that its x1 is at 6.5-ish, x1 is at 6.5. That's looking like it's lining up with one of the right-hand two clusters. Its x2 value is at -9, which if you look at the x2 axis is showing that that is pointing at the center of the bottommost cluster. If you looked at the corresponding x1, x2 coordinates for the other cluster centers, you'd see they would lie in the center of those three other blobs. Of course, doing that by hand, by looking at it visually, is no fun, so let's use the computer to do our job for us. We want to do the same thing we did before, points.plot.scatter x1 against x2. We're going to assign that to a variable, and then we are going to cluster centers.plot.scatter x1 against x2. So we're plotting the data points against each other, and we're plotting the data centers against each other. I'm going to tell it that we want to plot on the same axis. I'm going to say I want the color to be red for the cluster centers. I want the size to be a little bit bigger. These are all parameters I've worked out earlier because I prepared. And I'm going to use a marker of an X. So now when I plot this, we get our original clusters and we get a big red X printed on top of each of those clusters as to where the k-means algorithm thinks the cluster center has ended up. So have a go at that yourself, run those lines of code, get the cluster centers extracted and then plot it on a graph and make sure it's showing up something like this. I'll give you a minute for that and then I'll move on. Alistair's asking, how would clustering work on log scales? It would work fine. So if you take your data and you log your data, you can then cluster it fine. The thing to remember with k-means clustering specifically is that it works on a circular basis. The way it assigns points to clusters and then cluster centers to the center of the points that are on that cluster is with a traditional Euclidean distance. the Pythagorean distance of x squared or x1 squared plus x2 squared square rooted. And so it's implicitly working in a circle around the cluster center to find the points which are nearest to it. If your data has been logged and so it's skewed it in various ways, it may no longer be circularish data. And so your clustering algorithm is going to struggle to solve it. I've got some examples in a little bit of types of data where k-means fails and other clustering algorithms succeed. So we'll have a look at those in a little while and see the pros and cons of various algorithms and how you can go about solving it. And log scales come into play in that same kind of idea to do with transformations of your data. Yes, so I would try and make it so that the actual numerical parameters that are associated with each feature appear linear. So if my data was distributed exponentially, I would log my data so that the new parameter is effectively a linear scale of the exponent, so that my data now appears linear, even though the original data parameter was exponential. So by logging it, I've linearized it a bit more, made it more circular, made it more regular, so that clustering is going to work better on it. So we plotted the graph here by finding the where has it gone? The k-means.clusterCenters underscore parameter, which has given us 4 pieces of information because we set k to be 4. There is one other piece of information that the k-means clustering algorithm has provided for us, and that is k-means.labels. So you remember right at the beginning, if I scroll up, we extracted out our true labels. That was a number 0, 1, 2 or 3 for each of the sample points as to which cluster they were generated from. What the k-means algorithm has done is that when looking at this data without knowing what true labels is, it has, during its process, assigned each sample to a particular cluster, and it's remembered which cluster it's in. Obviously, throughout the algorithm doing its work, the label associated with each sample point is going to change as it's iterating towards a solution. But by the time it's finished, each sample will have a particular label. So we have a look at k-means.labels. We see it's a big old array where it's saying that the first sample is in cluster 3, whatever that means. Second sample is in cluster 0, whatever that means, etc., etc. Now these are effectively random cluster numbers. There's no reason to assume that the clusters are ordered from top left to bottom right. In fact, we saw before that cluster 0 was the bottommost cluster. But these numbers here do relate to our cluster numbers in our table here. So we can relate these two things together. But what we can do with that is we can use this to plot something. So let's again plot our points as a scatter plot. x1 against x2. We then are going to set the colour of each sample, of each small dot, to be based on its label that the k-means cluster has worked out it thinks it's part of. And so we do that by setting the colour to be equal to k-means.labels. That works because matplotlib by default has a colour map which has a colour associated with each integer value. And so it's going to colour each of these based after whatever colour it thinks is colour 0, colour 1, colour 2 and colour 3. In fact, we can tell it which set of colours we want it to use by using color map, and let's use dark 2, and let's not print a colour bar because we don't need to see one, because we know what our different colours mean. And so now when we plot this, this is telling us which cluster the algorithm decided each point belongs to. And you can see that on the whole it seems like it's done a decent job. But there are clearly some points in here where there is potentially some ambiguity. First, my eye is drawn towards that yellow point, which is halfway between the grey and the yellowy orange clusters in the middle there. To me, it looks like it's halfway in between. It's not going to be obvious which cluster it's falling into. It could be one, it could be the other. If we let the algorithm run for longer or for slightly less time, it might have ended up in a different cluster. Similarly for the green and orange points between the green and orange clusters, those 2 points are very close together, so you can easily believe that both of them could have ended up in one or both in the other, depending on how the iteration progressed. And as Alistair asks in the chat, how can you get k-means to infer probability distributions of which cluster each point belongs to? Not by default as it comes out. One technique you could do is, as the thing is iterating through, or once it's finished iterating, iterate it for a longer time, see if over that time period any points change from one cluster to another. And that's representing the clustering algorithm being unsure as to which cluster it belongs to. You could then look at how much time it spends in one cluster or another and assign to that some kind of frequentist probability as to which cluster it belongs to. But I don't know for sure whether that is necessarily statistically rigorous, but it would certainly give you a featureful idea of which points are the contentious ones. So what I'm going to ask you to do now is, as you've already been doing, follow through and do these copy the code examples that I've been doing. But if we have a look on the course notes, the first set of exercises on here, just after that clustering section, first of all have a go at running that through again, but try changing the random state of the original blob generation. You have to rerun the random state and then rerun all of the cells afterwards. See how that affects both the original distribution. See what happens in the situations where you end up with blobs overlapping, how well the clustering algorithm is able to distinguish the two of them. Make sure you understand about what's going on there, and if you have any questions, do please ask in the chat. Once you've had a little play with that, move on to exercise 2, where we're going to load in this iris dataset, which is from the scikit-learn datasets library. There's an iris function. You can load the data there into a data frame by copying this code here. So once you've got this iris thing, and then have a go at doing the clustering on this iris dataset. I do note this iris dataset has 4 features. I cheated a bit here with our x1 and x2 because it's easy to plot x1 against x2 on a 2D plot. Since the iris dataset has got 4 features, you'll have to think a bit hard about how you plot it. And as a trick, I'll remind you that you can use the scatter plot stuff we did for the correlation section on the page before, scatter matrix I think it was called. And if you get to it or you want to have a go, there's also an optional third exercise at which you can start looking at the inertia of these objects. I'll go through the answer to the exercise afterwards to explain what's going on, and exercise 3 comes on a little bit to the question about knowing how many clusters you should use and the techniques which I don't think are always that useful. Have a go with those, spend a few minutes on them, and let me know in the chat if you have any questions. So Serban's got a question there and says, when 2 blobs are very close, it separates them linearly. So let's have a look at what's going on there. So let's do random state. There we go. So when we look at the centers that come out of this. Oh, I need to rerun the algorithm. We see that it's put the 2 centers in the middle of what are probably the 2 blobs at the top of that section there. If we look at how it's assigned the labels, however, we'll see that the line between them is very much a straight line. And so what's going on inside k-means is that it keeps track of where the centers are as it iterates through. They start randomly. It then looks for it looks at each sample and works out which cluster center is nearest to it. Based on all of the samples which are therefore nearest to a given cluster, they will become part of that cluster. It moves the cluster center to the average of all the points in there and then iterates that process again. But because at the core of that, it's looking to see which cluster is nearest to a given data point, you end up with very, very straight lines of separation between cluster centers. This is very similar to a thing called Voronoi tessellation, which is a really interesting way of dividing up a plane based on random centers. You get a very similar thing happening here with k-means. And so even though our metric is circular, in that it's circularly isometric, you end up getting straight lines separating your clusters because along that line it is equidistant from one center and the other. And that's why you get a nice sharp straight line between the purple and the brown clusters down here, for example. That's maybe a better example. These 2 clusters are very close together. It's not obvious to me at all how it should be able to distinguish those into 2 clusters. It's probably just put 2 there because there are more data points in that top left cluster. And that means when we plot it, we again see there's a very straight line of separation between the grey cluster and the purpley cluster. Again, this is due to the metric that's being used. It's which cluster center am I nearest to? So you end up with a straight line separating the two of them. Let's have a look at the iris dataset next then. So this was exercise 2. So let's start by going from sklearn.datasets import load iris. And then I'm going to copy the line that I gave you, which is loading that into a data frame. And let's have a look. So here we have a table. It has 150 samples and it has 4 features. Based on those 4 features, we want to be able to work out what the species of this is. So we know in advance, and in fact we can find out by running asking it for the number of target names, number of categories, number of classes at the end, and have a look at what that is. And there are 3, so there's 3 different species here. And we want to use these 4 features to group each sample into one of 3 clusters. Once we know where the cluster centers are, we can then bring along new fresh data from the wild and work out which cluster center it's nearest to, and therefore make an estimate as to which iris species this flower we've just found in our garden is, for example. So we are going to call our k-means function again, and we are going to pass in n clusters equals number of iris species. So this is a situation where we've worked out in advance how many clusters we should have because we know how many species we've measured our data from. And as long as any new data we put in belongs to one of those 3 species, this is going to work well. Then we fit it by passing in the iris table of data. I'm going to assign that to, again, I'm going to call it k-means because I'm unimaginative. That's now done the algorithm. It's worked out how these things are related to each other. That means we can now plot the scatter matrix. Because we've got multidimensional data, it's good to have something which can represent that multidimensional data. I'm going to plot our iris. I'm going to set the fig size to be, again, 16 by 16 to make it nice and large. And I'm going to set the color based on the calculated labels from the algorithm. And here we have our iris data. So we have, again, I'm going to switch to the notes to see this picture because it's going to be easier to make large. We have our 4 features. Here we have the sepal length and the sepal width. Sepals are part of the flower in some way. I'm not a botanist, don't really ask me. And we've got the petal length and the petal width. I know what petals are, but I don't know how they're different from sepals. So we've got the length and the width of 2 different parts of the flower. And we have taken measurements of 150 flowers, and we have tried to work out, based on how those different variables relate to each other in 4-dimensional space, where the clusters sit. And so that's what the k-means clustering algorithm has attempted to do here. Now, I apologise for the colours. It's hard with this plot to get the colours to look up well. So if you can't see over the network, do have a look in the course notes on your own computer, and the colours might show up a bit better there. But the first thing to point out is that we've got 3 different colours. We've got a purpley colour, sort of a greenish colour, and a yellowish colour. And the other thing is that each of these panels is a projection of 2 of those dimensions against each other. So it's 4-dimensional data, but each of these scatter plots is a 2-dimensional projection of that data. So we end up with 6 different 2-dimensional projections of that 4-dimensional data. It's a little bit hard to think about multidimensional data. This is pretty much the best we can do. Looking at the purplish sample, we see that in almost all of the projections, that is well separated from the other cluster. So it's not surprising that k-means is able to easily pull apart that and draw a nice clear line separating it from the others. Now remember, when we were in 2 dimensions, we had a 2-dimensional, a 2-parameter line separating them. You can parameterize it with 2 variables, gradient and y-intercept effectively. Because we're here in 4 dimensions, we effectively have a 4-dimensional line separating each of our clusters. Hard to visualize, but imagine in 3 dimensions you would have spheres around each cluster. So in 4 dimensions we've got kind of 4-dimensional spheres or Voronoi cells. So the purple one is well separated, but as you can see in a lot of these, for example, the first row, second column, you see that there the yellow and the blue points are actually overlapping with each other. Which might seem strange given that with our clustering we were seeing a nice strict line separating our 2 clusters. But the reason we're able to get information as to which cluster the green and the yellow belong to is because the clustering algorithm isn't working on each 2D projection individually, it's working on all of the 4-dimensional data all at once. And so it's managed to find a 4-dimensional line separating the yellow and the green, such that when you project it down, that projection line is kind of going up and down, but also slightly into the screen. And so it's separating the yellow and the green kind of above each other, if you think about if there were a 3rd dimension. And so even though in each of those projections there's not necessarily a clear separation, once you take into account all of the 6 projections, it starts being a much, much better way of separating your data. Also note that on the whole, thinking back to our correlation chapter, there isn't, in our correlation chapter we were saying that we wanted there to not be correlation between each of our features. We didn't want, for example, if we were doing a supervised model here, petal width and petal length to be correlated with each other. Now in clustering datasets, it's a different story. Because in the clustering dataset, you care less about the linear or scaling variation between the 2 of them. We don't care if petal width and petal length go up with each other necessarily. What we care about is how distinct they are clustered on the screen, not simply their covariance between the 2 of them. So it's a slightly more nuanced thing you need to think about with clustering compared to correlation with supervised learning, which again is why plotting on a graph like this is a really, really useful way of visualizing what your data is doing. So here we have our make blobs again. We've got our same centers before. We've got 500 samples, 4 centers, random state of 6. So it's going to be exactly the same data. As we loop through, trying out different numbers of clusters. So we're going to call k-means with n clusters equals 2, then 3, then 4, then 5, then 6, then 7. And for each of those times round, we are going to ask of the model how well it's feeling by the end. And the way you do that in scikit-learn is ask for the .inertia parameter. Now the inertia parameter basically relates to, by the time the algorithm has finished its job, how much were the points still jumping around? How much were the cluster centers still varying? i.e. how much inertia did they still have by the time it called it quits and said, I've finished clustering. So low inertias are good because that means that by the time the algorithm's finished, all the cluster centers had settled. A high inertia means that while the algorithm was running, those centers were jumping around a lot, and so it still hadn't found a good solution. So we want low inertias. We then take the inertia values for each of those numbers of clusters, and we plot a graph of one against the other. And this is getting to that elbow plot thing I was alluding to earlier. Number of clusters on the x-axis, so 2, 3, 4, 5, 6, 7 clusters. The inertia is, I don't know what units it's in, but lower numbers are a better fit. And so you see by the time you've got to 7 clusters, it's managed to settle down quite well and work out where everything should be. However, we know there's 4 clusters, so we look at the value for 4 and we see, well, 4 got quite low as well. So the idea with these plots is you're supposed to be able to look sort of bottom left, see where it elbows and choose that as your number of clusters. But I've never ever been able to look at one of these plots and spot an obvious elbow. I wouldn't be able to pick between 3 and 4 on this unless I spent a lot more time doing this. So it's not always, to me, the most useful technique to decide how many clusters you should use. A more useful technique is to think about your data and think about the question you're asking, and see if that's going to give you useful information at the end of the day. That said, plotting an inertia curve over a couple of numbers of clusters is often a nice thing to do in case you spot any particularly interesting features. As I was alluding to before, and Al was asking when he was saying about logging your data and so on, there are limits to what k-means clustering can do. We saw, for example, that when you've got two blobs that are very close together, it's going to struggle to identify which cluster the points belong to. That somewhat is a fundamental restriction on what you can possibly expect a computer to guess from your data, but you can somewhat use some models if you know how the data is being generated to work out how you should cluster your data. So there are more advanced techniques you could apply. So k-means, which the clustering algorithm we're using here, is good because it's simple, fast, and easy to implement, but it famously has problems with clusters which are elongated. And so I'm going to switch now to a picture which is in the notes, so feel free to look at it there, which I've stolen from the scikit-learn documentation. So what we have here is a column for each different clustering algorithm. These are all fundamentally doing the same thing, just with different implementations. And each row here is a particular example of potentially tricky data, although I guess that row 5 is supposedly easy data. The k-means algorithm we've been using is that very first column there. So if you look at row 5, you see it's done the job just fine, like we saw. But looking at row 4, where we've got these elongated blobs, this is somewhere where k-means famously struggles. And that's because, as I was saying before, it always makes the assumption that the data you're working on is circularly distributed, or hyperspherically distributed if you're working in more dimensions. And that's because it always works by putting the center of the cluster in a place and working out the linear distance from there to any of the points. And that means if you've got two clusters which are next to each other and elongated, if you put the cluster in the center of one of them, then the points in the center of the other cluster are going to be nearer to that center than the points at the end of the elongated cluster that you've selected. And so it's going to do a bad job of working out which points each cluster should have in them. Looking across the row, we see there are other algorithms which do a better job because they do various other bits of transformation to your data. But there is other stuff we can do to our data first before we use k-means to kind of make it work a bit better. So one of them is dimensionality reduction. I mentioned principal component analysis earlier. One of the things that principal component analysis can do is take something that looks like the stuff on row 4 and turn it into the stuff that looks like row 5. And it does that by working out the principal components of the dataset, which would be along the length of the blob and across the width of the blob, and renormalizing the data so that it becomes more circular. Then you can apply k-means to your dataset and you get it working. So by combining a dimensionality reduction like PCA with k-means, you can deal with a lot of messy data. That, however, isn't going to help with the stuff on the first row. The first row, PCA isn't going to give you anything directly useful because PCA tends to work with linear models. So here you can see that k-means has failed because while the outer and the inner ring are distinct, they share a center. They've got the same cluster center, and so it's not going to be able to distinguish which point each cluster should be in. So what you would normally do with this kind of data is look at it by hand and think about how you could transform the data mathematically to make it more easily clusterable. So one thing you could do with that first row, for example, is instead of plotting it in x1 and x2 axes, you could plot it in an r and theta axis. So you make some kind of radial symmetry. So you've got one, so you end up with two blobs, one at radius 1, one at radius 2, and the theta would then be all the way around, so you end up with two vertical blobs. That you could then cluster and get the right stuff working. In essence, that's what some of the other clustering algorithms that have worked here have done. They've done various transformations to the data implicitly in order to make the data more easily clusterable. So what I suggest you take away from this is A, if your data isn't going to work with k-means, either pre-process it with some kind of transformation, whether it's logging your data, making it radial, or using PCA, or consider using a different clustering algorithm and see which one works best for your data. So we're going to move on to the last section here, and that is using clustering for something which isn't just plain old data, but is something a little bit more visual. And so I'm going to open up a new console, new notebook. And we have 15 minutes left, and so I'm largely going to go through this and explain what I'm doing along the way. And I'm going to leave the exercise at the end, probably as homework exercises for you. So we're going to start off by loading in a photograph. This is a photograph from Wikimedia Commons, and so it's openly licensed under Creative Commons. And we're on a new line, and we want to print out how big this picture is. So Scikit Image is a sister project to Scikit-learn, which deals with loading images. With io.imread, you can just load a JPEG from a URL and you get access to it as an array on your computer. So let's have a look at this. It's a photograph which is 480 by 480 by 3. It is 3 at the end. It's a 3-dimensional picture because we have a separate 480 by 480 matrix for red, for green, and for blue. So it's a cube of data, 480 by 480 by 3. And the fact that that's 3 is going to be important as we go through this. But let's have a look at what the picture actually looks like, because that's what we really care about. Show, another function from the scikit-image.io library. And let's plot the picture. And we get a rather nice picture of a swallow-tailed bee-eater bird. Again, I'm not an ornithologist, so I don't know any more about it than that, though I guess they probably eat bees. By default, the data in these images is ranging from, each value in the matrix is varying from 0 to 255. It's conventional to normally transform your data so that it goes between 0 and 1. Many machine learning algorithms just work a little bit nicer like that. You get normalized data, things end up just working a little bit better. So let's go ahead and scale our image by taking our data, loading it into an array. Oh, I need to import NumPy. Loading into array with a data type of float, and that's because when it was a 0 to 255, it was an integer. We want to convert it into a float so we can represent it between 0 and 1, and then we divide it by 255, and we're just going to overwrite the same variable. So it's the same picture, it's just all been made effectively much darker, but it's all got the same relative values. We then want to extract out the shape of our photo, because later on we're going to be changing the shape and we want to be able to reform the shape. So photo.shape returns the width, the height, and the depth of the image. That's 480, 480, and 3. We're going to save that in a tuple called original shape as well, and we're going to pull it out there. Once we've saved what the original shape of the image is, we are going to do something to it, where we are going to reshape it from being a 480 by 480 by 3 image, and we're going to change it so that the spatial dimensions just get thrown away. We are going to stop caring about where the pixels are, and we're just going to keep track of what the pixels are. So we turn it into something which has one dimension, which is width times height, which is going to be some number of thousands, and another dimension, which is the depth. And I'm going to save that as image array. And let's have a look at what that looks like. So here we see there is an array here, which has got red, green, and blue values between 0 and 1 for the first pixel, red, green, and blue values for the second pixel, red, green, and blue values for the third pixel, and so on until the red, green, and blue value for the last pixel down in the bottom right-hand corner. So this has effectively taken our picture here and has flattened it. So instead of being two-dimensional, it's just one long list of pixels, each of which has a red, a green, and a blue value. And that's because we're going to apply clustering on this, and we're not going to do spatial clustering in the sense of find out a pixel and then the pixels that are near it in XY space. We're instead going to find out the pixels that are near it in color space. So if we find a pixel that's yellow, we're going to try and find all the other pixels that are yellow. And we're going to try and make a yellow cluster and a green cluster and a blue cluster. And the reason we're going to do that is because if we can represent our bird with fewer number of colours, at the moment this bird is represented with 16 million colours or something. If we can represent it with fewer colours, one green, one blue, one yellow, while the picture becomes less nice looking, it also becomes much, much smaller in terms of memory usage. And so effectively what we're doing is creating a compression algorithm, something which can make our pictures smaller in memory, which means you can email them to people more easily and so on. And that's something we can do with clustering. We've got our image array here, but we want to stick it into a pandas data frame because then we've got column names and it will look something like this. A table with 230,000 rows because there are 230,000 pixels. Each pixel has got a red, a green, and a blue value. Once we've got those red, green, and blue values, we want to have a look and see how they're distributed. Now, red, green, and blue, you can plot it in one of two ways. You can plot it as a photo by using the red to change the amount of red on a pixel, the green the amount of green on a pixel, and the blue to change the amount of blue on a pixel. Or you could plot it as a cube with red on x-axis, green on the y-axis, and blue on the z-axis. And that will give you a sense of how the different pixels are distributed in colour space. And so we're hoping that all of the yellow pixels will be globbed together in one space in this cube, all the blue pixels will be globbed together in another place in this cube, and we'll be able to make that into a blue cluster and turn all the bluish pixels in the original image into that blue colour, therefore reducing the amount of different colours in the image, therefore reducing the memory usage. In order to plot this data, matplotlib doesn't understand 3 columns with different integers inside them, so we have to do a little bit of trickery, and I'm just going to copy and paste this. I'm not going to worry too much about how it works, but effectively it's creating a new column called colour, which has a hexadecimal representation of the colour made out of the red, the green, and the blue values. So here we've got the red, the green, and the blue, and we've got a new column, which is colour, which has got 69 representing the amount of red, 64 representing the amount of green, 46 representing the amount of blue, and then 60 representing how transparent we want it to be. So this is RGBA hexadecimal code. The only reason we're doing this colour column here is for plotting purposes. This isn't going to be used as part of the clustering. We're just doing this to be able to draw a picture. Now, before we can draw a picture, we've currently got, what did I say there were, 230,000 pixels. That's way more than we need on our plot. So let's go ahead and take a subsample of our data randomly so that we've just got fewer pixels to worry about. So I'm going to take 5% of the data. So pixel sample is just taking a random subset of our pixels. So instead of having 230,000, we'll have 5% of 230,000. We can then go ahead and plot it. Feel free to have a look through this code later about what it does, but it passes in the samples, it tells us which columns we want to plot, and then it plots each of those pairs of columns against each other. So it's going to plot red against green, red against blue, and then green against blue. And so when we have a look at this, we get our scatter plots like we had for our iris example. So we have here on the first plot, red on the x-axis and green on the y-axis. So we were hoping that we were going to be seeing distinct blue blobs, yellow blobs, green blobs, but the most thing we're seeing is there's a big streak of sort of browny purple through the middle, and that's because the majority of the original image was background and the stick that the bird's on. So we're hoping that's not going to affect our stuff too much, but we'll have to see. But based on this 3-dimensional data here, this no longer is a photograph. It no longer knows where the pixels go. It just knows how many of each pixel there are and what their values are. But because we've got some multi-dimensional data, we can just throw k-means at it and see what happens. So let's load in our k-means and then call k-means n clusters and underscore equals something. So at this point we want to choose how many colours we want to end up with. Now a photograph by default has got something like 16 million colours, 256 times 256 times 256, whatever that is. We want to reduce it down to something much, much smaller. For now, because my computer won't survive otherwise, I'm going to do 10. I ran this course last week, and when I tried to do 100, my laptop broke, so I'm not going to be doing that again. But we're going to try and cluster this data here with 10 different clusters and see what clusters it finds. And we fit it with our pixels subsample data, because we don't need all of our data. The 5% data is enough. And we're going to use the red, the green, and the blue columns. And we save that to a variable. Now this will take a little bit longer. It took maybe half a second. If I try with 100, my computer ran out of memory. Let's have a look and see which clusters it found. So we do that using k-means.clusterCenters, same as before. This is going to be a 3-column data set, which is going to be the red, the green, and the blue center for cluster 1, the red, the green, the blue center for cluster 2, the red, the green, the blue center for cluster 3, etc. But let's do a graph of it, because otherwise we won't be able to see it. In show, I'm using matplotlib here to draw a graph of that data. So you see here, these are the cluster centers that it's managed to find. Our original bird, I'll just scan back up to it for a moment, had yellow, green and blue as its main feather colours, and the rest was kind of brown for the background. Our cluster centres from our data there has found a bluish one at the end. It's found a kind of muddy yellow in the middle, and it's found a grassy green at number 8 at the end. So it's kind of found some main colours, but you see the majority of it is brown. Using these found clusters, what we're going to do, we're going to replace, for each pixel, we're going to look up what the red-green value of that pixel is in the original image, work out which cluster centre it's nearest to, and replace it with the value of that cluster centre. And then we're going to plot that picture and see how it looks. So we do that by asking it for its labels, same as we did before. We are going to call the predict function. We're going to pass in all the pixels from our original image, and we're going to get back for each pixel in our original image the cluster centre that the k-means algorithm reckons it's nearest to. And we've got a whole bunch of 5, 1, 1, etc, etc. There'll be numbers between 0 and 9. Once we've got that, we can go ahead and reshape it back to being square. So remember, our pixels was taken from being 480 by 480 by 3 to being some long list of numbers by 3. So we're going to put up our cluster centres back into the original shape and then have a look at what that looks like. So first we'll run reduced. And what I'm going to do is a plot of the original picture against our reduced picture. And you see here, it looks kind of ugly. But in terms of memory usage, this image is going to be thousands of times smaller to store on disk, and we're only using 10 different colours to do so. So what we can do with that, we can go up and we can have a look at how it looks if we change this to 15. I'm going to be cautious because I don't want my computer to break again. That 15 worked absolutely fine. And we run this and we're going to see that that picture on the right should become a bit better looking. Some yellows have started appearing, which they weren't showing up properly before. So as we increase this, we'll slowly get better and better representation, but we're going to get there a long time before we ever get to 16 million. This is actually often used as an artistic tool to make nice looking pictures if you choose your spatial orientation correctly. With the remaining few minutes, I'm just going to show you very quickly another technique that you can do to make your representation look a bit better. I'm going to change this back to 10. So I'm just going to copy this code in for demonstration purposes. So what we're doing here is we're going to take our red, green, blue scatter plot and we are going to perform a transformation on it by changing what's called the colour space. So instead of representing each pixel in terms of how much red, green and blue it has, we're going to represent it by how light it is, which is what L stands for in lab, and how much of two other parameters it has. You can kind of think of this as doing a principal component analysis on it. We're then going to reorganize our data and look at what our new projection of 3D space looks like. So here we have the same data, but transformed mathematically into a different representation in 3D space. So instead of red, green, blue, we have L, A, and B. And you see here the clusters are much better distinguished. All that brown is no longer a streak through the middle, it's a blob. So hopefully that will be clustered more effectively. The yellow is distinct, the green is distinct, and the blue is distinct. So that means if we go ahead and ask it for a clustering of that data set, again using k-means fit of this new data, and have a look at what the clusters look like, we see we've now got slightly more variation in colour. We've got two different types of green and yellow and blue. Still got a lot of brown, but right now there's not a lot we can do about that. If we want to have a look at what our original bird transformed onto this clustered set looks like, we can do that. And here we see a different kind of reduction happening. With only 10 colours, it's got all of the main colours, two different greens, a blue and a yellow. But you see it's reduced the colours in other directions. Best way to see this is to plot all three of the pictures on one plot together. So here we have the original picture on the left, the RGB with 10 clusters in the middle, and the lab cluster with, again, 10 clusters on the right-hand side. Now, there might be pros or cons to one or the other, but certainly the one on the right-hand side has managed to pick out more of the interesting colours, whereas the one in the middle hasn't managed to find the yellow at all. So by choosing a appropriate transformation for your data, you can sometimes find more representative blobs which are telling you interesting things about your data. For example, the middle one never found the yellow, whereas the lab cluster does manage to find the yellow. So we're basically at the end of the session now. So after the session, feel free to have another little scan through this page. There's some exercises at the bottom, which I'll leave for you to do for homework. So do have a go at those. And I'm just going to finish off with a bit of a summary as to what you might want to look into next. So this course has covered linear regression and clustering on the whole, but there's some other techniques which are really useful and can solve simple-ish problems but can be very powerful. One of those is naive Bayes, so it's worth having a read into that. That's a way of saying if the data was generated, how was it generated and what would the distribution look like. Support vector machines allow you to draw lines and separate your clusters of data, which is a really, really nice way of deciding how you should classify your data. Principal component analysis, I've mentioned. And neural networks, we have a course called Intro to Deep Learning, which we'll be running sometime in the future, so feel free to keep an eye out for that. And I'll finally point out some further reading you might want to look into. So the Python Data Science Handbook by Jake van der Plas is a really, really great book. It's free online. Do have a look at that. The scikit-learn documentation's got lots of interesting pages describing how these techniques work. And if you're looking for a good book to talk through this stuff, right from the very basics through to advanced data analysis techniques, I very, very strongly recommend Hands-on Machine Learning with scikit-learn, Keras, and Tensorflow. I suggest you get the second edition if you can, which came out about a year ago. It's a really, really good book. It teaches almost everything you need to know about machine learning, data science, and data analysis. So do go ahead and grab that if you get a chance. With that, I'm just going to say thank you all very much for coming along the session today. We got through a lot of stuff, so I hope hopefully it hasn't been too quick, but it's been really great having you all along, and I hope to see you again in another course in the future. Thanks and goodbye. So, let's start from the basics. This course is called Introduction to Deep Learning, but before we can get to deep learning, we need to understand the context about how that fits into the larger scheme of things. So machine learning is where I'm going to start, and that's a lot of what we covered in the course yesterday. But at its core, machine learning is any technique which uses computers to discover patterns of information. So it's what would traditionally have been called statistics, but because you're using computers to do it, it allows you to get greater reproducibility, and most importantly for some of the stuff we're going to be talking about today, much greater scale. You can go to much larger amounts of data, much larger depths of information you're trying to seek out. And that's what differs machine learning from what would traditionally be called statistics, is this scale of what you can do with it. Now, machine learning sits inside the wider field of artificial intelligence. Artificial intelligence is a very poorly defined term. It basically means anything where computers are trying to make decisions. So that can be something as simple as trying to make a decision as to what the value of y should be, given x. That's a very, very narrow form of artificial intelligence, all the way up to self-driving cars, and potentially, according to sci-fi anyway, well beyond into generalized artificial intelligence. But within artificial intelligence, there sits machine learning, which is a better defined field where it's about statistics and data science and things like this. But of course, even machine learning, being a narrower field than artificial intelligence, is still incredibly broad and is full of loads and loads of different techniques and concepts. In the course yesterday, we covered things like k-means clustering for doing unsupervised clustering algorithms, as well as linear regression and correlation studies. So these were some of the tools you would apply to your data. And what we're learning about today, on a much larger scale, is deep learning and neural networks around that. So inside machine learning, which remember is sitting inside artificial intelligence, is a whole bunch of different things. Yesterday, one of those we looked at is a linear regression. It is a very simple concept we got across. You've got a scatter plot, you draw a straight line through it. That is nonetheless machine learning because you're using a computer to discover what the values of the gradient and the y-intercept are going to be. Slightly more advanced technique is something like k-means clustering. It's trying to discover things about your data without you having to explicitly tell it where you want to end up. There are hundreds, maybe even thousands of different algorithms that sit inside machine learning, variations therein, but obviously we don't have time to go through all of those. Possibly one of the most famous examples of machine learning algorithm, particularly over the last 10-15 years or so, are neural networks. Now, neural networks have been around a long time. Decades and decades neural networks have been around, and at their core they're a relatively simple concept. But over the decades, as computers have got more powerful and the kind of questions that we want to scale up have got more difficult, we've had to become cleverer about how we apply neural networks to try and solve the problem. And so for a long time, neural networks were relatively constrained in the kinds of complicated problems they could solve. But since about 2010, the last 10 years or so, there's been a second wave, or maybe even third or fourth wave, depending on how you measure your history, about how you can create neural networks which are what is called deep. Now, I'm going to come across shortly what I mean by a deep neural network, but it's a specific structural shape of a neural network which has been managed to be solved by applying more advanced statistical techniques by very, very clever mathematicians. And it's this resurgence of neural networks which are deep, which has led into the modern fad, last 5 years or so perhaps in research, of deep learning. So deep learning is applying a deep neural network to some kind of problem. So, I've given you artificial intelligence, I've drilled down into machine learning, and from there we've drilled down into neural networks. So this course is titled An Introduction to Deep Learning, but before I can really give you a sense of what deep learning is and why it's interesting, we first need to make sure we understand what a neural network is. At their most basic elementary level, how do they work? Because the terminology and the few bits of maths that I'm going to be putting in today are important to understand how the problem scales up, and when you're wanting to use these things, how you can solve the problems that you're going to come across when you're trying to get stuff done. So a neural network is a collection of artificial neurons. So the place we need to start before we think about a network is to think about the subset, the things that make up that network, the nodes that connect together, and those are neurons. And before I go any further, I need to apologise and say that I am not a brain scientist. I have no idea how the human or animal brain works, so if anyone in the chat here does, you might want to cover your ears for a second. But at their core, a neural network is modelled after a real animal brain. A brain is constructed by having a whole bunch of neuron cells all connected together, well, not all connected together, but connected together in some kind of network. And as inputs and impetuses come in from the outside world, electrical signals are triggered off in some of the neurons, and then depending on which neurons they're connected to, and the conditions under which those following neurons are going to activate, you get a kind of ripple effect going through, with different scales and sections firing and other parts not. And it's that complex interplay of all these different neurons which is what gives us intelligence. And now the idea with neural networks was to take a simplified model of how that works, some kind of mathematical description, and see if we can try and solve some of those same problems that the human brain can solve. So from this point on, you can forget all about the animal brain, pretty much, because everything I'm saying isn't really how nature works, but it is how our mathematical model, inspired model, is going to work. So an artificial neuron, which is designed after the idea of what a real animal neuron is like, has multiple inputs coming into it, and it parts its output out. You can think of it as like being a little function with a bunch of inputs and one output. At their most simplest, the function that a neuron encompasses is adding together all of the inputs coming into it and then putting the output out the far side. It's slightly more complicated than that because it doesn't just take each input, it takes the first input and multiplies it by a number, adds that to the second input multiplied by a different number, and adds that to the third input multiplied by a different number, and so on, depending on how many inputs a particular neuron has. Neurons can have potentially 0 inputs, but realistically the minimum would be 1. They can have thousands of inputs. But at its core, it is this bit of maths here, which is what is going on inside a neuron when you're passing information through the network. It's the sum over the input values and their corresponding weights. And notice that each input value xi has a wi. Each input has its own weight. If there are 10 inputs to a neuron, there are going to be 10 weights. Also bear in mind that every neuron is going to have its own set of weights. So if there's another neuron somewhere else in the network, its W1 will be different to this neuron's W1. So you can imagine if you've got a network full of 100 different neurons and they're connected together, you're going to end up with millions of these weights all connecting together and trying to give you some kind of realistic output. The one other thing to be aware of in this simplified model that I just described is there's an extra step which happens. After this sum here is calculated P, it then gets passed through an activation function. Now, an activation function in nature will be something like don't trigger the output until the sum here is above a certain threshold. But because we're doing maths here, we can do absolutely any activation function we might want. There are various reasons for choosing one activation function over another, but often on the whole, they'll do something like if the sum is negative, then just ignore it, and if it's positive, pass it on through. So before I go any further, I'm just going to ask if there are any questions about how this part of it works, how a single neuron is interacting before we then think about how we connect it through into a network. Right, so there's a question there from Jan. Is there a reason for using a linear combinations of inputs only? I think because it is the easiest thing to do mathematically. It's a simple function you can apply which gives you an effective result. You do want to pass it through an activation function because activation functions can give you extra bits of magic. So if your whole network was just linear combinations of inputs and weights, then if you add a whole bunch of linear sums together, what you get at the end is a linear sum. And if that was the case, the most powerful thing a network would be able to do would be to evaluate some kind of linear relationship between the inputs and the outputs. By having the activation function at the end, that allows you to encapsulate non-linearity in the thing you're trying to model. So you can keep the core of your model simple and then allow for non-linearity by passing it through this activation function, and that gives you the space to explore more interesting models. Yvette asks, so the weights are associated with the neurons, not the inputs. Yes, that's the easiest way to think about it. Think about each neuron having a bunch of pipes coming into it, and on each of those pipes it's got a valve which it can use to multiply the input or divide the input by. So each neuron has inputs coming into it, and it has its own value that it's being multiplied by to decide how that neuron is going to treat that particular input. Shreya asks, can we use non-linear combination as well? In principle, a neural network can do whatever you want. There's no reason why a neural network has to have a simple function like that. And in fact, in reality, there might be neural networks out there which have more complicated summing functions inside. There's no reason to think that it's necessarily this. But at least conceptually, it's the easiest way to think about it. Reality might be more messy, but conceptually consider it as a sum over the inputs and the weights multiplied together. Reality might be more difficult, but until you start having a full degree in neural networks and deep learning, you won't have to worry about anything more complicated than that in order to get your job done. At the end of the day here, we want to learn enough to be able to use these things and understand how to fix them. We don't necessarily, for today at least, need to understand the full mathematical description of how it all works. Okay, so I'm going to carry on to the next slide now. So as we go through, do feel free to pipe up and ask any questions you might have. Even if it's on a slide that we've already been through, that's fine. I'm happy to reiterate over things because you might think, oh yeah, I understand this. And then I mention something in 2 slides time and you realise, I really didn't understand that. I obviously misunderstood. So do feel free to ask as we go. So now we've got our description of a single neuron. We're now going to see how we can connect them all together. Now, again, it is possible in principle to connect your network together however you want. You could just turn it into a big net of things connected together in all sorts of directions. But because we want our networks to be able to be understood by humans to some extent, we want to be able to design them and understand what the different elements of it do, there is a general structure which most neural networks follow. Now, most simple neural networks anyway, the complicated stuff comes from people breaking these rules and discovering new and interesting ways of structuring their networks. But certainly for the examples today, our networks are all going to be this kind of structure which I'm going to describe now. And that is, you start on the left-hand side of this picture, on the input layer, and this is where you take your values that you want to put into your model. So an example that we used in the course yesterday was looking at the price of a house. So you might go out and measure how many bedrooms a house has, how large its garden is, and how close it is to the nearest school, for example. So those are 3 quantitative measurements that you can make. So those would be the values that you put into each of these 3 neurons on the left-hand side. Now note that these 3 neurons on the left-hand side kind of don't have inputs. That's because that's where the data is going to start from. So the left-hand side is where we put our data in. Now each of these neurons on the left-hand side is connected to every one of the neurons in the next layer. That doesn't necessarily have to be the case. A neural network where everything is connected to every other one is called fully connected, but it's perfectly reasonable to have some neurons on the first layer connected to only some on the next, in whatever combination you see fit. But you can see, looking at this second layer here, the first one that's got 2 neurons on it, each of them have 3 inputs coming into it, and they have an output coming out. Now looking at the output coming out of the top neuron here, you see it's connected to 2 neurons in the third layer. That's not to say that this neuron has 2 outputs. It's simply that that one single output is being passed on to both of the neurons in the following layer. And each of those neurons in the following layer will have their own weight that's being applied to the output of the first neuron here. This process just gets applied all the way through. You work out the first layer, you work out the sums and the activation function, you pass it into the second layer, you add up the sums, you do the activation function, you pass it through to the third, until eventually you get through to the output layer. When you get to the output layer, this is your result. This will give you some kind of number, because at the end of the day we're doing maths, it's all going to be numbers. We'll end up with a number at the end, and it's up to us to then interpret what this number means in the context of the question we're trying to ask. But overall, this is the structure that they all have. They have an input layer on the left-hand side. I say left-hand side, it's all virtual, but I think of it going left to right. If you find it easier to think right to left, that's perfectly fine. Input layer on the left-hand side, a single output layer on the right-hand side, and then some number of hidden layers in between. In this example here, we have 2 hidden layers, each of which have 2 neurons. In principle, you can have any number of hidden layers you like, with any number of neurons in each. The thing that makes a deep neural network deep is having lots of hidden layers. That's pretty much the definition of a deep neural network. And we'll see later on why that's a useful thing to have. Great, so I was to ask if anyone's got any questions. There's already one from Sumet. So how many layers and how many neurons should we have? It depends on the problem you're trying to solve. So I'll get on to how you go about designing your networks later, so I will go through this in a bit more detail. But the number one rule I would suggest is find someone who knows what they're doing, who has solved a similar problem to what you're trying to do, and use the same structure as they have. That is going to get you 90% of the way. After that, you can feel free to tweak it, but by using pre-existing and published network structures, that's going to help you. Shreya asks, how many layers is considered deep? That's one of those questions where there's no real answer. I would say as soon as you've got 4 or 5, you're getting to the point where networks would have struggled with it in the past. Once you're at 100 layers, you're definitely in the situation where you've got a deep neural network. Going much beyond that, you're going to have to start bringing real firepower to be able to evaluate anything to do with the network. But I would say, rule of thumb, you can start answering those really interesting deep learning questions by the time you get to sort of 6, 7, 8, 9, 10 and beyond. Though as with all things, the benchmark kind of shifts over time. What might have been considered a deep neural network 10 years ago might not be considered quite so deep these days. And Tim asked, what's the precise definition of a layer here? So there's no one universal definition of a layer which can capture every single different situation. But under the structure of a network we have here, where we take all of our neurons and we put them into boxes where they are lined up on top of each other, such that in one layer, in one box on the left-hand side here, they are only connected to neurons in the next layer. And in this next box here, these are only connected to neurons in the next box. That allows you to have an absolute definition of the ordering of the neurons, which lets you decide absolutely what layer each neuron is in, and therefore how many layers you have. Of course, because these are just networks and you can in principle do whatever you want, you could take the output of the third layer and connect it back to the input layer if you wanted and do something with that, at which point it's harder to define what's a layer. However, you can do a lot of really interesting stuff without having to cycle through. So the networks we're working today are what are called acyclic, i.e. they don't have cycles. They are simply feed forward from the left-hand side over to the right. Exactly, Tim. That's a good way of putting it. The neurons on layer n only have inputs from layer n-1. Nitin asks, can more layers lead to overfitting? Absolutely. We're going to cover one of the main techniques, well, actually two techniques, which you can use to reduce the chances of overfitting as we go through. Okay, I'm going to carry on. So, these are some of the questions you've been asking. So it's good you've been asking intelligent questions before I've even got to it. So, a question you've been asking is, what shape should it be? So there is some art and some science to this. There are rules of thumb. If you've got a certain number of input layers, if you've got 10 input parameters, then your hidden layers should, to an order of magnitude, be about 10. There's no point in having an input with 10 inputs, and then the first hidden layer being 100 million different neurons. That's not going to extract any useful information. If you've got 10 inputs, you're not going to want more than 100 in the next layer. Realistically, anyway. This is one of the things which you can assess using mathematical techniques, which we're not going to cover in this course because they're very complicated, and also a certain amount of trial and error and data science applied to the shape of the network. Also, as I think someone mentioned in the chat, the number of hidden layers kind of relates to how complicated a question you can answer. Every hidden layer provides a layer of abstraction. So if you're trying to start from some very generalized information and to pull out a really specific answer, you're going to need lots and lots of hidden layers to work through the layers of questions that the network is implicitly answering. So if you've got a hard question, you're going to need a deeper network. If you've got an easy question, you can get away with one hidden layer for simple things. It doesn't need to be a complicated situation. The flip side of this is the deeper the network and the larger the network, the harder it is to train. That means it's going to take longer to train, you're going to be more at risk from overfitting. And we're going to see how this sort of balance comes through as we go through the course today. The next question that you might have had sitting in the back of your head, but you haven't worked out how to formalize it yet, is I've been talking about the neurons and the inputs coming in and how they're going to be multiplied by some kind of weight. And the question you hopefully have is, how do you know what that weight should be? Because at its core, there are two things which describe how the network is going to answer your question. The first is the structure of it, which neurons are connected to which, how many layers, how many neurons, these kinds of things. And the second part of the problem is the weights that are being applied on each individual neuron's input. So the first part we decide and we design upfront. We describe a network and we say this is the thing that's going to solve our problem. But for the weights, we have no way as a human of working out what these millions of different values should be. And so this is where we use computers. This is what makes it a machine learning algorithm, because we are going to use a mathematical process on the computer to discover what the values of those weights should be for the particular problem that we're trying to solve. This process is called training, and it effectively works by showing it loads of examples, and it ends up giving you something which can replicate the effect of those examples. So a question there from Ali. How can we decide how many layers we need? Again, I would say that the number one way you should discover how many layers you need and the shape of your network is to think about the problem you're solving, find someone else who solved a similar problem, and start from their example. If you're doing something where you're trying to identify heart disease in CT scans of a heart tissue, then you might start from someone else who's done the same thing with liver disease or something like that. So it's something working with 3D data, you're looking for certain features in the data. You don't have to start from scratch to design your network, you start from someone else who solved a similar problem and has analysed how it works, and you start by using theirs. If you can show that it performs well, then you've succeeded and you can use that to do the things you want to do. If it doesn't perform well, then at that point you have to start talking to data scientists and experts and trying to work out how to go from there. So, to dive into that question there, how do we go about training the neural networks? What is the process by which the values of the weights get assigned? Now again, there's lots of potential algorithms you could use here. There's lots of different ways that you can decide to use a computer to work out what those weights should be. But the main technique that's used is something called backpropagation. Now again, backpropagation is a technique that was applied to neural networks quite a long time ago, and in the preceding time, so in the time since, there's been lots and lots of nuances and changes to it and replacement techniques. But backpropagation at its core, as to how it works in principle, is still pretty much how neural networks are trained, even if there's lots and lots of clever hacks applied on top of it. And so to do this training technique, you need 3 different things, pretty much. You only need 2 of them, but the third one isn't going to be doing very good data science without it. So first of all, you need a training data set. You need a bunch of examples where you've got the inputs to it, using the examples from before, a bunch of houses where you've measured the size of the garden, counted the number of bedrooms, and measured the distance to the nearest school. And for each of those examples, you have a label assigned to it. You've said, how much is this house worth? So that is what we mean when we say a labeled training dataset. For checking how well our network is performing, we also need a labeled test or evaluation dataset. Now, it's important that your training dataset and your test dataset are distinct and disjoint to make sure you avoid overfitting. Now, we're going to cover exactly how overfitting feeds in a little bit, but we did cover it in our course yesterday as well. But you want to make sure you have 2 distinct subsets of training data. They can look the same, but you should choose randomly about 80% of your data to be used for training, and then keep aside about 20% to check how well your network is performing. And for the backpropagation algorithm to work, you need to start off with some set of initial weights. So now I'm going to go through and show you how these different things can be designed, collected, and evaluated. Before I do this, 2 questions. So Pratap's asking that the same output can be achieved by multiple combinations of inputs across layers. How is precise connectivity and weights decided? So you're right, you can have repeated information existing inside a network. You might have 2 parts of your network which are deciding the same piece of information, in which case you've got more neurons and weights than you really need. There are techniques you can use to try and find correlations between weights as they progress, and that gives you some sense as if you might be able to prune your network or reduce your network down. If it's affecting the ability of your result to be accurate, then you're going to want to do that pruning. If it's not, then you don't. So the precise connectivity is hard to do. Connectivity is generally done on a coarse layer. It's called coarse level, although it's of course possible to apply specific techniques to prune parts of it. As for weights, we're going to show you now how this particular weights are decided, and it does feed into that question you were just asking. And Jan asks, is training always mandatory with neural networks? Realistically, yes. If you have an off-the-shelf neural network which has been trained to identify the difference between cats and dogs, you don't have to do any more training on it, you can just use it. But if you start with the empty structure, you need to do something to work out what the values of the weights should be. And to work out what the weights should be, you have to train the network. So, starting with the initial weights, lots of different opinions and techniques as you can use to start off your network with some kind of values. But the easiest way to do, and conceptually the thing that we're going to do, is setting all of your weights randomly. There are ways to be smarter about it, but for today, let's just assume that they're all being set completely randomly. So every neuron is having inputs coming into it, and it's multiplying each of those numbers initially by a random number. And we're going to train it to try and fine-tune those random numbers in the direction of something which is useful. And then for the test and training test data sets. So we're going to need 2. So we need one, as I said, to train the network on so it can learn about stuff. And the other one is going to tell us how well it did. It's important to separate your training and test datasets to avoid overfitting. And to give a bit more information about why that's the case, it's because a neural network inside it has got tens, hundreds, millions potentially of different weights. And if your data has fewer degrees of freedom than that, then your network is able to learn potentially every single piece of information about your data that you're showing it when it's learning. It would be possible for every single neuron to each take their turn and remember one particular input into the network. And so as you're going through, it's going to start looking like your network is able to perfectly replicate the training data that you're showing it. And that's because it's remembered every single little nuance up and down of the data you've been showing it. By keeping some of that data aside for testing at the end, even if your network has learned every single little detail about your train dataset, it's not going to have learned any of the nuances of your testing dataset. Your testing dataset is therefore not going to have those same ups and downs, and so when you show it to the network, it's going to behave very, very poorly. It's not going to do a good job. And so the dance you need to get is the balance between getting your training dataset behaving well, while also keeping your testing dataset still also performing well. The common split you generally see is about 80% for training and 20% for test, but depending on how much data you have, you can jiggle those numbers around. And there are also more advanced techniques, things like k-folds, where you end up using all of your data for training, but you split it into different subsets and you repeat it over and over again, and then you aggregate it at the end in a clever mathematical way. Umair says, by disjoint, do you mean statistically? What I mean is you want, of all the samples you've collected, when you divide your set into two halves, you don't want any overlap between the two. They should be sampled from the same distribution, is one way of thinking about it, but they should be separate samples from that same distribution. Shreya asks, is it ideal to set weights randomly? If there's repetition, will it not be wasteful? Possibly, yes. Random setting your initial weights isn't necessarily the thing to do. There are clever ways you can work out what your initial weights should be set to. But as far as us as researchers using neural networks to solve problems, we're going to leave that to the software to decide, and they're going to do a better job than we would be able to decide. And Yvette suggests that you need a massive data set to do useful stuff. You generally do. You do need a lot of data to train a neural network. However, if you're answering a simpler question, and therefore you've got fewer neurons and fewer weights, you can get away with less data. We'll see an example in a minute where we only have around 100, 150 examples, and that's enough on that particular example to answer the question well. On later examples, you might need... I generally think 1,000 examples is a good kind of rule of thumb for a neural network for most problems, but having more than that is always going to help. One of the problems with data science and neural networks is having that data that's nice and clean and well prepared. So, I'm going to talk briefly about the mathsy bit, and this is probably one of the last bits of maths on the screen. So, I'm not going to be using any maths that's beyond A level, but if anyone wants a bit of clarification, I'm happy to explain it in more detail. But backpropagation is the process by which we assign weights to the network. It's an algorithm which we use to decide what those weights should be. It's an iterative algorithm, so we're going to apply this over and over again, and over that time, the weights are going to get closer and closer to that which the algorithm considers to be optimal in some way. But before you can apply the algorithm, you need to start off with your network structure. So we've decided how many inputs we've got and outputs, how many hidden layers and how many neurons we have in each hidden layer. We need to have some initial weights. We need to have somewhere to start our iterative algorithm from. And you need to have a training data set. You need to have some examples you can show to it, and those examples are going to inform how the weights progress as the algorithm is applied. Now, there's lots and lots of different ways you can do the training, but the core of how it's generally done these days is using backpropagation. And this is a very simplified description of how backpropagation works. So you need to start off by looking at the structure of your network, looking at the inputs and at the outputs. And you need to look at every single weight in your network. So every single input to a neuron is going to have its own individual weight. You're going to have maybe thousands of potential weights. And you need to work out how much do you need to change each weight by to affect the output of the whole network by a certain amount? If I change a particular weight by a small amount, is the output of the network going to only change by a small amount, or is it going to change by a relatively large amount? If a weight has a disproportionately large effect on the output of a network, then the derivative of that weight is a large number. If that weight only has a small effect on the eventual output of the network, then it's said to have a small derivative and it's only going to have a small effect. So working out this derivative independently for every single weight, and assuming they are independent, which largely works in the situations that we're talking about here, this gives you a list of derivatives, one for every single weight in your whole network. Every weight will have its own dn, its own derivative. So this is telling us how much you need to change that weight by to have a certain effect on the output. Note also that these derivatives are signed, so it could be that if you make your weight slightly larger, the output goes down, and that would be a negative derivative, for example. So all this information is captured in a big list of derivatives that's stored alongside the network. So that's the first step that happens once up front before you start doing any training, because for the networks we're looking at, those derivatives don't change over time. What you then do is start the training process, and this is where you repeatedly do these steps over and over again. And the core of how this works is you take a training entry, which has, for example, 3 values, the number of rooms, the size of the garden, and the distance to the nearest school, 3 numbers. You put it in the left-hand side of your network. You then work out what the output to that layer is going to be, pass it into the next layer. That layer is then going to take each of the inputs. It's going to multiply them by its initially random weight. It's going to do that all the way through right out the other side. So the weights are initially set randomly, and you're going to get out the far side a random number, effectively. You're going to get some kind of result. It's going to be a numerical value between minus infinity and infinity, but you're going to get a number out. What you then need to do is look at how far away that random number you got is from the true number. Maybe the true value of the house was £200,000. Your network gave you a random number of £0,000. You know you're therefore 200,000 away. So you then need to look at all of the weights and adjust them by how much they need to change to make the result you got out of that network move in the direction of the correct answer. Now you don't move it all the way in one go. You don't jump the result up by 200,000. You move it by a very small amount so that you can slowly move in the direction of something which is going to get you a right answer. So after this, you go through all of your weights and you update each of them by a small amount by looking at what their derivative is with respect to what how wrong you was. Scale that down a little bit to try and slow things down. And then you do the same thing again. You show it another example. And this means that the more wrong the weights are, the more they work toward the answer. And as they get close, they slow down and start propagating towards a settled result. The idea being that after this magic, if you put in 3 values which represent a house, it is going to give you back something which is going to make a good guess as to what the value of that house should be. So, I'm just going to answer a few questions from chat before I move on. Nitin asks, how does it know when to stop and what's ideal? You keep on running until your training data set is your testing data set, you keep on going until your test data set looks like it's giving you a good result. At its core, there's more nuance than that, but that's the basic answer. You keep going until your test data set, your validation set, is saying, this is looking good, this is answering the question quite well. Connor asks an insightful question. In a network with a huge number of weights, wouldn't analysing them individually be an inefficient method of tweaking? Indeed. So the way I'm describing it here is how you would do it if you were doing this on paper. In reality, modern techniques represent the network as a huge multi-dimensional tensor, and you just do tensor arithmetic on it, and it has the effect of doing this simplified maths. And by doing this tensor arithmetic, you get nice, fast results because hardware can be designed to do tensor arithmetic very, very quickly. Kunal asks, how should we determine the learning rate? Use the defaults of the software that you have in front of you. They will generally have a default learning rate which works well. If you find that it's behaving poorly as it's training, you can tweak that learning rate. And there are in fact algorithms, and in fact we're going to be using one today, where the learning rate adapts automatically as it goes through. And Roy White asks, is this essentially manual optimization? In a way, yes, but we're doing it using a computer, and so it can do it a lot faster than we can. You can imagine looking at each individual thing, tweaking it up and down, seeing how it affects the answer, tweaking the next one, and so on and so on. We can do it all in one go using the network, and it becomes scalable. And Michael asks, does this always converge? No, it doesn't. There's no reason to assume it's always going to converge. It's an extremely complicated mathematical object, and even if it does converge, it won't necessarily converge where you want it to. At its core, most neural network training methods are doing a form of gradient descent. And you can imagine that in a two-dimensional way on a big plane covered in hills and valleys, and you're trying to find the lowest point in that plane. So you start by rolling a ball down a hill. It's very possible in that situation to end up in a valley that's near where you started that is not as deep as a valley which is further away. So that you've ended up in a local minimum and you haven't ended up in the true result. So there are techniques you try and use using randomness and adaptive learning rates to try and avoid getting stuck in a local minimum. So, to reiterate what we were just talking about there, here is a much cuter example than a house. Here is a lovely picture of a dog. Imagine you can extract some properties of this photograph of the dog. Maybe we add up all the pixels and look at their red, green and blue values. And so we end up with 20,000 input neurons, for example, one for each pixel, however you want to describe the picture. We start with a random network. We put all the numbers going through. So all the pixels end up in this input layer on the left-hand side, the 3 neurons. We then pass it through to the next layer and the next layer and the next layer. Of course, we need a more complicated network than this, but we would still get an answer with this network. We run this example through and we get some kind of answer. It's randomly weighted to start with, and so it says something like 37 or 0.37, which we decide means it's 37% dog and 63% cat. We know that the truth in this example, because all of our examples are labelled, is that it is 100% dog and 0% cat. And that means that we are 100% minus 37%, i.e. 0.63% wrong. And so we use that 0.63% to work out how much we should change all of our weights by. It's a positive number, so we should generally multiply all of our weights in that equation by a positive number, and that's going to slowly tweak our network towards an answer. We're going to do this thousands of times, each time taking a really, really small step, and that's hopefully going to, over time, push the network into configuration where it's able to answer questions similar to that one that we started with. Alistair asks, are there ways of assessing the rate of conversion as a proxy of the confidence that the conversion is general rather than a local optima? In principle, you can, but it could just be that you happen to be in a flat bit of the terrain at that particular time. You could start off in hill country out in the distance, then have to go through a large flat area before then ending up in a really valley-ish area in the middle of the country. So you can't necessarily assume that because it's converging slowly that you've ended up in the right place. You have to use clever techniques. You have to be careful to not end up assuming that you've solved the problem before you have. And as Lester says there, you also start off in lots and lots of different initial places, and you see if any of those are going to push you towards an answer. I've been talking through so far effectively how you would do this by hand. You can imagine that you could sit down with a bit of paper. Lovely picture, Umair, good job. You imagine you could sit down with a piece of paper, draw your network out, work out what the derivative of all the weights are, and look at the numbers of the inputs, do the maths, do the inversion, and keep going and keep going. As I said, the way this actually works is by doing this using very, very large tensors, using GPU, accelerated hardware, all this kind of thing, because the scale to which you can get is not codable, obviously, if you're doing it by hand. You have to use computers, which is why it's a classic machine learning algorithm. Again, we also don't write the software by hand to describe the network and to do the backpropagation and to do all these things. We use software that exists already to do that work for us. We're not going to spend 5 years trying to compete with Google or Facebook with their techniques. We're going to use the software they provided, which is shown by the whole industry to work really well. Now, there are lots and lots of different pieces of software out there which can provide a way of describing a network, of training a network, and evaluating a network. And some of the most popular ones are, well, the two most popular are PyTorch and TensorFlow. So PyTorch, I believe, was originally produced by Facebook, and TensorFlow was produced by Google. They are both fantastic neural network libraries which do all of the bells and whistles you'll need for any kind of complicated network. In the course today, we're going to be using TensorFlow, but PyTorch works brilliantly well, so I'm not going to say anything bad against PyTorch. There's also a package called Keras, which isn't itself containing any algorithms for doing the training. It is a wrapper on top of the other packages to give a nicer way of describing the problems you're trying to solve. It's a bunch of niceties and add-ons, basically. And so what we're going to be using today is Keras's nice add-on layer on top of TensorFlow. There's also a package called Cafe2, which isn't getting quite as much publicity these days, but it and its derivatives are still thought of very well and they do a good job. And finally, scikit-learn. So yesterday in the Applied Data Analysis course, we used scikit-learn for doing other machine learning algorithms. It does have a neural network, a whole set of neural network packages and modules built in, but it's not going to be anywhere near as performant as things like PyTorch or TensorFlow. It's not going to perform very well for your very, very deep neural networks, and it's not going to take advantage of the GPUs in the way the other packages would. But for exploring and playing around and getting started, scikit-learn works perfectly well, and you get the advantage of being able to easily compare to other machine learning libraries. So as I said, we're going to be using TensorFlow, and we're going to be using a bit of a Keras layer on top of it. So let's get on and actually see how we can use some code to describe, train, and evaluate our neural networks with a real example. So the example we're going to use is a famous one. If you've ever done a machine learning course before, and in this I include our course we gave yesterday, you will have seen the iris example. So this is a data set that was collected quite a way back, and it is been used for decades for giving machine learning training. And the dataset at its core is information collected about 3 different species of iris flower. So the 3 pictures here are 3 different species, and we are going to try and design a network which, based on measurements made of these flowers, not based on photos, but based on measurements made of the flowers, we're going to try and decide which species the flower belongs to. So these 3 are Iris setosa, Iris versicolor, and Iris virginica. That is the extent about which I know anything about these flowers. However, I do know about the data set that describes the flowers. So there are 150 examples in the data set, and the link there I think takes you to the Wikipedia page. Let's have a look. Yes, it's famous enough that it's got a Wikipedia page, so if you're interested, do have a look at that page later on and learn about the nuances of this data set. So each flower that was measured by a particular person back in the day, they went and measured 4 different properties of each flower. They took a ruler, they wrote down in their notebook in a table, and they measured these 4 things that we see in the table in front of us. The length and the width of the sepal, and the length and the width of the main petal. And their idea was that based on just those 4 measurements, they should be able to distinguish which species the flower belongs to. And remember that we need to have this being a labelled data set. We need to know what the truth is so that we can nudge our network in the right direction as it's training. And so we also record the species. So species 2, 1, 2, 0, etc. Remember that we're dealing with maths here. All of neural networks are maths. And so anything that we come up with that describes something human or physical, we have to convert that into something numerical in some way. And so in this data set here, we are using the number 0 to represent the setosa, 1 to represent the versicolor, and 2 to represent the virginica. And so you can imagine that we want to try and train our network so that if we show it a set of sepals and petal measurements which represent a setosa, we want the network to output a number which is near to 0. So now we've seen what the data set looks like, we now have to think about how we can design a network which can take these first 4 columns. Now the inputs to a network are often referred to as the features. We want to take something which can take these 4 features and give us out our label. And do that consistently, even for examples that it's never seen before. Okay. So to see a bit more of a visual idea of how this works, this picture was taken from the Wikipedia page. we have here a multi-scatter plot of the 4 different features. So along the rows, we have the length, width of the sepals, and then the length and width of the petals. And likewise, down the columns, we have the length and width of the sepals, and the length and the width of the petals. And so in each off diagonal, we have a scatter plot of one of those features against the other. So in the second row in the first column, we have here a scatter plot of sepal length against sepal width. And we have each of the dots in that coloured by what the true label of that particular flower is. And so you see here there is a fairly distinct cluster of the red, which is the setosa, whereas the blue and the green are relatively intermingled with each other. So based purely on this scatter plot, you would probably be able to make a good guess about whether a flower is a setosa or not, but you wouldn't be able to easily distinguish between a versicolor and a virginica. And if we go back 2 slides, you'll see that you can probably guess which one's which. The setosa is this one on the left, and the other 2 flowers do look very similar to each other. To my untrained eye, I would struggle to tell those 2 apart. However, if we look in other projections, some of them do have better separations, but there's no one projection which has perfect separation between the datasets. They all have at least some overlap between the blue and the green, and I do apologise if you're colourblind. I'll try and do a better plot for next time with better colourblind friendly colours. The idea, however, here is that even though no one single projection can distinguish the 2, we're hoping that by combining together all 6 projections, because those are the 4 features combined together, all 6 of those different projections, we can come up with some kind of complex, multi-dimensional description of what's going on. In a way, you can imagine that the network is going to divide these things with kind of dividing areas in the different planes with certain probabilities, and then sum together those probabilities at the end and give us an estimate of which flower species each example is. That's not exactly how a neural network works. There are other machine learning techniques which effectively do that, and they would also behave quite well on this. This isn't the kind of problem that you need a neural network to solve. This is something which can be solved with other relatively simple techniques, but this is a good place to start when learning about how we can design a network and train it and go through that mechanical process. So, the code for this is all linked at this link here. So on this page in the notes, click on iris.ipynb. I'll click on it as well to show you what it looks like. It will take you to a page on Google Colab, which looks like this. I'll show you how to run through it in a bit, so if you want to follow along and keep track of where I am, feel free to have this page open in another tab, but I'm going to have all the code samples on the slides and I'm going to talk through it bit by bit to explain what the different parts of the code are being used for. So the code we're using today is using Tensorflow and Keras, and it's being written in Python, but all of the concepts and ideas I'm going through will apply for any other kind of programming language or tool. So the same steps we're doing here, we would have to do in PyTorch, we'd have to do if we were using R, or we'd have to do if we were using Julia or some other language. So it's not necessarily today about learning about the Python, it's learning about the steps you go through, and as a side effect, we're learning how to use TensorFlow. I'm going to jump into the question or 2 in chat before carrying on this slide. So Tim asks, how come the categorical output are integer encoded rather than one-hot encoded? In reality, Tim, they are one-hot encoded. It's just that in the original data set, they are integer encoded. When it comes to the network, it is going to treat them automatically as being one-hot, and that's one of the features that Keras and TensorFlow just handled for us. We tell it it's categorical, and it does that work. Marius asks, when working with categorical features, should we convert those into numerical features? More or less, yes. And so Tim's and Marius's questions are related. Now, I don't cover in detail what one-hot encoding is here, but Les has posted it there in the chat. But at its core, you can imagine that we have 3 different features here. We've got, 3 different labels here. We've got, is it flower 1, is it flower 0, flower 1, or flower 2? Now, when we're training a network, it's going to be trying to aim for flower 0, 1, or 2. If it's flower 2 and it's actually giving a value of 3, for example, then we need to bring it down. But also if it's below, we need to bring it up. And so it's got some ambiguity about if you're between 2 flowers, which one it's going to be, and other flowers, even if it's likely probability, they are necessarily further away because of the inevitable ordering of integers. So what you can do instead is take those 3 different features and turn it into a 3-bit binary number. So you have a 0 or 1, followed by a 0 or a 1, followed by a 0 or a 1. And you use the first digit to describe how much of it is the first species, how much of the second species in the second digit, and how much of the third species in the third digit. So if it is a flower species 0, the number would be 1, 0, 0. If it's a flower species 1, it would be 0, 1, 0. If it's a flower species 2, it would be 0, 0, 1. So the place where the 1 is tells you which category the particular measurement is in. And that's why it's called 1 hot, because the number 1 labels the hot place in that measurement. And this allows you to find scalable probabilities for all of the different classes in a clever way. But the nice thing about TensorFlow and Keras is they hide that for us. We don't have to worry about binary digits. It's just going to do the right thing for us. So the first thing we need to do is load in our data. So to cut to the chase with this, scikit-learn, which isn't the package we're going to use to do our training with, but it does provide us with some data loading facilities, has a function called loadiris. And this gives us the table that we saw on the previous slide as a piece of code. It's something which we can use and analyze and pass through the system. So we are going to load into our x parameter the data of the loadiris dataset, and into the y value we are going to load the target. So x is going to contain the values which were measured with a ruler. It is going to be the length and width of the sepals and the length and width of the petals. 4 columns of this data. And then the y parameter is going to contain which species each of those samples relates to. So we're keeping our training data and our labels associated with it in separate variables, and that makes sure you don't accidentally leak some of your labels into your training set and skew the whole thing. Once we've got it loaded in, the next thing we need to do is turn it into our training and test dataset. We just split those apart. And again, for this, there is a scikit-learn function called train test split, which we give it our x and y, and it gives us back our train and our test for x, and our train and our test for y. So this has done it randomly. We can trust this to do it, well, pseudo-randomly. We can trust this to do our job for us. By default, this does a 25% split for testing, and therefore a 75% split for training. If we look at our x train value, we see we have an array of lists, or array of arrays, 2-dimensional thing. Each sample is a row, and each sample has 4 measurements, 1 for each of those things we measured with a ruler on the flower. So this is one sample, i.e. one flower, this is a second flower, and this is a third flower. And these are the numbers that are going to be put into the input layer of our network. These 4 numerical values. If we look at the y thing, and the first 3 that corresponded to it, we see we have the numbers 0, 1, and 0. So that's saying this first sample here is flower 0, flower species 0. This here is flower species 1. This here is flower species 0. If we look at the shape of these 2 things, we see that our x data has 112 samples and 4 columns, and our labels, there's just 112 numbers. It's just a 1-dimensional thing. So our x is a table of data, our y is a list of numbers. And in general, this kind of shape of things is going to help. Tim asks, is the capital letter for input data and lowercase for outputs a convention? There's a bunch of different conventions. You often see X, capital X, being used because it's representing something which is a vector of samples. So you've got something that's got multiple dimensions to it. The fact that this is 2-dimensional is it's capital lettered. Same reason when you're doing a vector in maths, you sometimes do an arrow over it to sort of designate it as being a vector. Also sometimes use capital letters for matrices, and this is effectively a matrix. The conventions are a bit wobbly, but it's more or less the convention that I'm using in the notes here. And I think I'm consistent. If I'm not, please do ask. But this is our data. We've got this for the training. We've got equivalent shape stuff for the test data set. We've got 112 training samples, and therefore we've got 38 testing samples. Simply having your data in a two-dimensional table isn't itself enough. We need to do some prep work on it so that TensorFlow understands what the data means. We have our training samples, but we want to be able to show them to the network repeatedly over and over again, randomizing the order so that it doesn't do things like remembering the order of the samples, for example. It's not going to bias towards remembering the ones at the beginning or the end more strongly, so we're going to randomly shuffle them together. And by doing over and over again, each sample will contribute a small amount towards the result, but at different points in the training, and so hopefully you'll get a nice balanced result. So the 2 bits of code here, again, the code details aren't important, but it's good to know the kind of thing you need to do. We take our data sets, our training data set, X and Y, and we turn it into what TensorFlow calls a data set. The data set in TensorFlow kind of encapsulates all the stuff that the network needs to know to train from it. And that includes things like the fact that the data should be repeated over and over again. Those 112 examples should be 112 the way through, and then show them again, and then again, and then again. They should all be shuffled together. Here we're shuffling them in batches of 1,000, so the ordering that they were in the original sample isn't going to factor in. And finally, we do a thing called batching. And this is another way that you get a more generalized, smooth approximation of the answer. And that is by showing it not just one example at a time, as I was explaining we do before. In fact, we actually show it 32 examples all at once. And because this thing's being represented as a big, complicated tensor, it just adds another dimension to the tensor, which we end up inverting and multiplying and doing math stuff to. And so we can show it multiple at once, and effectively the average effect of this batch is what gets applied to the training weights. And that smooths things out, stops you ending up jumping around too much, and makes it more likely you're going to find a generalized answer. The numbers we use here, 1,000 or 32, you find them by tweaking the numbers, messing around with it, seeing what works. We then do the same thing with our test dataset, except in our test dataset, we don't need to repeat it and we don't need to shuffle it because those things aren't affecting anything. And we just batch it into batches of 1 because, again, we don't need to worry about this dataset having any effect on the network. It's only being used to measure it. Does batching affect the degree of overfitting? It's possible by having larger batches you can reduce overfitting. You'd have to fit the network for a lot longer to get the same overfitting effect. But it's not the primary use of it. The primary use of it is to smooth out the training and to stop you ending up in weird local minima too much. Exactly, Umair. We show it 32 examples, and then based on the effect of those 32 samples, we then update the weights all in one go. And Nitin asks, is it similar to cross-validation? With the test and trained data sets, this is effectively a form of cross-validation we're doing. It's not there are more details and nuances to advanced cross-validation to really avoid the nitty-gritty of overfitting, but this, at its most basic, is the first step towards doing cross-validation to avoid overfitting. And Venkata asks, does batching help the time taken for training? It can do. As long as the computer hardware you're using is able to hold 4 samples times 32 samples in a batch, so 4 times 32 numbers, in its little cache register to do the maths to, then it's going to make it faster. If you make this number too large, then it's not going to be able to fit in the memory of the machine, and it's then not going to be able to train at all. You'd often go the approach of making this number as large as possible such that it fits into the memory of the machine. In the example we're doing here, we've only got 4 features, and so you're not really ever going to have problems. But I've dealt with networks where you've got a million features or something like that. And then when you start having a batch of 100 or something, you start potentially pushing into memory limits of some computers. Right, so we've got our data set up. We're all ready to go with that. The data's ready to be shown to the network. It just needs a network to be shown to. And so we need to design a network which is able to do this evaluation. And the network we're going to design here is a very, very similar structure to that which I showed in the earlier slides. It's got an input layer at the far left, an output layer at the far right, and it has 2 hidden layers. We use Keras here because Keras is what allows us to write layer after layer after layer after layer, just in a Python list. And so we start off with our input layer. We say our input has 4 features, and so we've got 4 neurons in our input layer. That's all we need to do to tell this how it's going to work. Based on this, it's going to know to ask from our dataset for things which have a dimensionality of 4 in one of the dimensions. Sorry, a size of 4 in one of the dimensions. Then we're going to have a hidden layer. Both of these layers here are the hidden layers because they're between the input and the output. And our input layer here is going to have 10 neurons in it, followed by another hidden layer with 10 neurons in it. And then the final output of our network is going to be a layer which has 3 neurons on it. We choose the number 3 here because there are 3 different categories that we want to put our iris samples into. What this is actually going to do is, instead of having one single output neuron which has a number and we try and push that number towards the result, we actually end up with 3 different neurons, each of which is going to represent the probability of a particular measurement being one of the particular flowers. So if neuron 1 has a high value and neuron 2 and 3 have got low values, that's saying it's likely to be neuron 1 is the answer, and we'll say that neuron 1 will decide in advance is flower 0, for example. We apply the softmax activation function to the output of those neurons because that is what turns it into a probability. It basically works out it normalizes it so the sum of them add up to 1. And so we end up with an effective probability being the output of each neuron of it being each particular species. I mentioned activation functions earlier, and it was more or less in passing. And here you see we have to specify what the activation function is. We have to say, based on what gets added up and multiplied inside the neuron, what function do we apply to that number before passing it on? And if you don't know any better, a good place to start is using the ReLU, which is, let's have a look at the Wikipedia page for it. It's the rectifier, and this is a particular form of the rectifier at linear unit. It's a function which looks like this. It's the blue line there. You see that if the output from the neuron, which is x, is negative, it sets it to 0. If the output is positive, it just sets it to be the number. Now, this particular activation function has some nice properties which mean that it works well at describing nonlinearity and things like that. If in doubt, go ahead and use the ReLU or spend a few weeks reading the literature out there to try and decide on a better activation function. ReLU, for most purposes, is going to do the job quite well. Okay, so I'm just going to check for any questions. Lester's answered a bunch of them. So Umair asked, why do we need the comma after 4 for input neurons 4 comma? That is a particular Pythonism, which is saying that this input function here takes arguments, and the argument it takes has to be a list of dimensions. In this case in Python, this is how we make a Python tuple, which only has one element inside it, which is the number 4. Nitin asked, do we have to do feature selection before, or does the model do it for us? So if you want to do feature selection and think about what features are important and not, you should do that before the network. You can, however, query how the network is training to try and discover which features are interesting or not. But I always recommend the best thing to do is to use your scientific intuition to think about the different features and decide which ones are important, which ones are not. Look at correlations between them, look at the effect that different ones have based on other machine learning models, and decide which features are important. You can also do various post-processing to your features if you think that's a useful thing to do. Otherwise, one of the nice things about neural networks in many situations is if you put in a useless input feature, then it will just get pushed to the side. All of the weights coming out of that feature are going to get set to 0 because they're going to have no effect on the output. They're going to kind of get ignored. Now, that's not necessarily a situation you want to be in, but it does mean you can sometimes get away with it if you've just got a weak feature in your dataset. But obviously, the more features you have, the slower your network is to train. So we've described our training dataset and we've described our network. So in principle, we're ready to go now. Now we just need to describe how we're going to mesh the two of those things together. So before we can actually train it, we need to tell the algorithm how it's going to work. And remember, this is more or less a backpropagation thing being applied, but there was some unspoken details that went into that backpropagation algorithm, which I didn't cover at the time because we need a real example to actually understand what's going on. So remember I talked before with backpropagation about you show the network a sample of data, you push it forward through the network, and you see what result you get. And based on how wrong that answer is, you need to decide how much to change the weights by. And you can see if you've got 3 different outputs and you've got a class you want to end up at, you need some way of describing how wrong that is. So if, for example, the 3 neurons on the output were 0.4, 0.3 and 0.3, and the real answer is 0, naively, there's no obvious way to be able to say, well, I need a single numerical value to describe how wrong I am. So we need to come up with a mathematical function which can take the 3 neuron outputs and the place we want to be and give a number out of it. For example, we might want to get a number like 1.13. We need a single numerical value. And this is what the loss function is for. Now, there is an art to choosing loss functions, but mostly it comes down to what kind of problem are you trying to solve. In our case, we're trying to put things into categories. So we want to use some kind of categorical loss function. And in the situation where we have multiple neurons as outputs with values, and we have a single integer describing the class that we want to assign it to, then Tensorflow comes with a loss function called sparse categorical cross entropy. If you really want to, you can read the documentation page and the paper about it and learn about it. But for our purposes, it's good to know that it does the job well. And in most similar cases, it's going to do the job well. Almost every network I've trained in my career so far has used the sparse categorical cross entropy loss function, or a very similar variant on it. So that's going to tell us how wrong we are. So we can use that, we can feed that into our backpropagation. Now the other thing in the backpropagation is the particular function that we use to accept all these arguments and decide how much to change the weight by. On the earlier slide, I had that sum over the differentials, and then you shift the weight by that amount with a delta omega. That was a simplified version of how gradient descent works. Of course, when we actually come to doing the real job, we have to have a specific real answer about how the backpropagation is going to work. And so we need to tell the network what algorithm should you use. And here we are going to use the Adam algorithm, which does something very similar to how I described it before, except it's a little bit smarter. One of the things that the Adam algorithm does is it has an adaptive learning rate. So if, going back to our example of being out on the plains with some mountains and hills and valleys and stuff around, when it's on really flat land, it will move more quickly. It will move across flat land really quickly. But as soon as it gets to the hills, it's going to slow down to make sure it doesn't jump over any particular local minima in the whole domain. The last thing we have is the metrics. This isn't used to inform the training per se. It's only used to tell us how the training is progressing, like how well it's doing, so we can keep an eye on it as it's going through. So we've prepared all the pieces. We have our data, we have our network, we've described how they're going to fit together. Then we just need to actually kick off the algorithm which is going to do the job. And so we've created our model, which was made up from these different layers. And every model in TensorFlow and Keras has a fit function. So we just call that fit function, we show it our training data, and it's going to go away and do the fitting. That's pretty much all we have to do. The nuance on top of what I just said is that as well as showing it the training data, we also want to give it access to the test data, so that while it's training, it can be printing out onto the screen how the network at the point it's got to is working on the validation dataset. And so as it's printing these things out and it's training on the trained dataset and evaluating in a side channel on the validation dataset, we should see the progression of the network improving. For example, one of the things that we asked it to tell us about, if I go back to the previous slide, we asked it to tell us about the accuracy. That is, of the samples that you have there, how many are you getting right and how many are you getting wrong? We want that number to be 100%, and anything short of that is less good, and 0 is terrible. So what we'll see as the network progresses is that the accuracy by looking at the training dataset is going to improve over time, and the accuracy on the validation dataset is going to, hopefully, also improve over time. The way that you spot whether your network is overfitting is whether the accuracy of your training dataset keeps on getting better and better, because it keeps on learning more and more nuances about the training data that it's seeing. But then your validation data starts getting worse all of a sudden because your network is no longer generalizing well, it's learning specifically about the training data set. And so it's the combination of looking at the accuracy on the training data and the accuracy on the test data that tell you about overfitting and things like this. The very last thing we need to do is tell it how long to train for. So we say for each big loop of training data, you should do 150, look at 150 examples. This is actually 150 batches. So it's going to be 150 times 32 different flower examples it's going to look at. And it's going to evaluate against the test data. And then it's going to do that 10 times. It's going to do it over and over again, 10 times until it's finished. Now, I've chosen these numbers because I know that by the time it's done that 10 times, it's going to give a nice answer. But in reality, there are more advanced techniques to work out how long you should train your network for. So when we run this function, it's going to go off, do the machine learning, do the backpropagation, and it's going to output the information to the screen. And it should only take a second or two with the data that we're looking at. Nitin asks a question, how does the model handle unbalanced data sets? And there are techniques there by choosing the right metrics is one of the main ways that you do so. You choose a metric which, rather than looking at accuracy, which if you have a very imbalanced data set, is going to tell you that you're often doing quite well because one of your classes only crops up 1% of the time. So you have to think of a different metric to accuracy to describe it. Or you do some clever stuff to rebalance your data set. And I know this is something that Lester, who's working on a machine learning project at the moment, is currently fighting with, and it's not always very fun. Umair asks what steps per epoch's doing. So steps per epoch is how many batches should it look at before it prints some statistics to the screen. Historically, steps per epoch would be how many samples should I look at, or rather how many samples do I have, and then epochs would be how many times should I look at the full data set. When you're repeating and randomizing and batching your data, those definitions fall apart a little bit. So mostly you can think of it looking at all of the batches 1,500 times, 150 times 100 times 10. However, I break it down into 150 and 10 so that it's going to print out summary statistics as it goes along. So mostly that's a hack to make TensorFlow describe what it's doing as it progresses. So we call fit, it goes away and does it, and then as it's going through, it's going to print this stuff. And I'm going to just describe what you see on the screen, and then we're actually going to run this stuff for ourselves. So for example, on epoch 10, the last epoch, it's going to print out the value of the loss function. Remember that sparse categorical cross entropy thing? That has a number. We're trying to make that number small. We're trying to reduce how much it's lost. And we're also trying to measure the accuracy. We're trying to make the accuracy large. We want it to be accurate when assessing the data that it's training over. As well as the loss and accuracy on the training data set, we're also looking at the loss and accuracy on the validation or the test data set. So we want these numbers to be moving down at the same kind of rate as those two numbers. They should have similar values and they should progress at a similar rate. If they start diverging from each other, that's a sign that you're probably overfitting on your data set and you need to reevaluate how you're balancing things up. So this is telling us that at the end of this, it's got a 75% accuracy. Once we've trained our network and we've got everything all working, then we have to actually use the model. So this is after the model's trained, it's learned everything, the weights are set and they are fixed. At this point, the weights don't change anymore. They are just going to be used. We're no longer going to do any backpropagation. We no longer have any true labels we're comparing with. We're no longer doing loss functions, any of that stuff. We have a fixed network which is designed to answer questions. So we're going to pretend that we've, since training the network, gone out into the garden and measured some more flowers. Using my brain, I know which one is which. I know I've got one of each flowers. And the 4 features of the first flower are those 4. 4 features of the second flower are those. And the 4 features are those. We take this data, this data we want to predict over, these 3 samples, and we pass it to the predict function of the model. It takes in data that's the same shape as the training data, and it's going to give us back some predictions. This predictions is going to contain the values of the output neurons for each of the 3 samples that we've shown it. We then do a bit of Python magic where it takes those predictions, loops over them, finds the one that has the maximum probability, and then grabs the actual name of the flower out of the lookup table, which made 0 be one flower, 1 be the other flower, and 2 be the other flower. We run that bit of code and it gives us back its prediction of what the species of those 3 flowers are. And if we look, we see that it matches what we had at the beginning. It's also worth noting that during this process, while we upfront wrote what the 3 flowers were, we never actually used that in the prediction. That was just for our human purposes. It wasn't used by the code at all. It's not cheating and looking at the answer. It's only looking at these data here. Umay asks, where did it convert the binary numbers 0, 1 or 2 like in ytest? It did that automatically by us describing the loss function as being the sparse categorical cross entropy. That function there understands how to take an integer value like this and turn it into a one-hot encoding, which can be compared to the 3 output neurons. This function is designed to kind of do that one-hot thing automatically for us. And it is just a function which you can call with the value 0 and a list of numbers, and it will give you back a loss value. Right, enough talking for me. Let's actually go ahead and run it. So go ahead and click on that link there. I'll just go through this in a second. So let's click on this link here. If you're not logged into your Google account already, then you'll have to sign in. And to do that, you'll click on the sign in button up here in the top right. Once you're logged in, go to Runtime up here at the top and click Run All. Once you click that, it's going to run all the code and it's going to run all the way through. And while that's running, I'm going to answer some questions. It will warn you that this code is coming from GitHub. It is coming from my GitHub account. So if you trust me, go ahead and run it. If you don't trust me, press cancel. But I do hope that you trust me and you can see the code here and understand everything we've just done. Annika asks, how would you look at the layers and see how the network makes decisions, i.e. the plane separating the 3 species? There are things you can apply on top of the data, the network, to try and do this. TensorFlow comes with some tools to do these kind of things, but it is a whole field of research to try and understand what's going on. To see the planes here, for example, you could just sample the phase space and do a 3D plot and try and see these clusters, but more advanced techniques would take more than this course to apply, but the TensorFlow documentation does have some information about this. So this has now worked. It has loaded the data, it's done all the shuffling of the data, we've designed our network. I'm going to make my screen a little bit bigger, that's much better. And then it's done the training. And so you see here, we've started out and the loss function was, after the first epoch, quite large. And the accuracy was quite small, only 20%. Notice at the very beginning here, while the training accuracy was 20%, the validation accuracy was 40%. And that's just random chance. After the first iteration, you could easily expect them to be the other way around. What we want to see as we progress, however, is this accuracy increasing over time. And that's it saying that based on the examples that it's being shown, it is doing a better and better job of representing them. But remember, as well as that increasing over time, we want to make sure that the test dataset, the validation dataset, is also increasing. And we see here it does, and it quickly kind of starts aligning with the values, 79%, 81%. After a while, the network has got to the point where the validation accuracy has topped out. It's no longer getting any higher because 97% is probably, of the 40 or so examples, probably only one example that it's no longer getting it. It's failing to, it's not able to resolve that one last example, but it's doing all the rest of them quite well. And from that point on, it never gets any better on the validation dataset. We might need more validation examples to get a better idea of why, but it's not necessarily a problem that the validation accuracy tops out. What would matter was if this validation accuracy started going down. We also note that the validation loss is still reducing, which is a good sign that it's continuing to go down in concert with the loss function of the training dataset. So going right to the bottom, we see that example, and it says the Sosa is 98% sure that it's correct. The versicolor is 97% sure that it's correct, and the Virginica is 92% sure that it's correct. And so you wouldn't necessarily expect to see exactly the same numbers as that because there's a random element, but you should expect to see numbers in the 90s. Right, I'm just going to go through a few questions here. I've seen some things cropping up. Jan's asking about the role of the test and training data set. So I'll go back to the beginning and briefly show what's going on here. So we have all our data, we split it into training and testing, and from that point on, those two data sets are completely treated independently. Our training data set gets shuffled and blocked up, and our test data set just gets left how it is, pretty much. When we come to the fitting, we show it the train data, and the training data is what's going to be used during the backpropagation process. That's the one that's going to be having the loss function applied to it. It's going to have the weights being recalculated from it, and it's the one that's going to cause the network to collect towards a result. So the network is only going to learn from the things that are in the train data set. It is never going to see, for its training purposes, anything from the test data set. The only thing that the validation data test is used for is for calculating these numbers. It's not used to inform the network in any way, it's just used to give us this output so that we as humans can assess how well the network is working. Tim asks, if you restart the window and start again, it will, by default in this case, start again from scratch entirely, or wipe all the weights and run it all. If you run just the fit function again, I think it will carry on from the previous weights. And Ozalpas asks, can we access model metrics and model selection comparison? Yes, so Keras and Tensorflow have a whole bunch of functions built in to extract information from these models for doing comparisons and whole kind of cross-validation, hyperparameter tuning setups. So that's all possible in Tensorflow. We're not going to cover it all in this course because it's a large topic. We're trying to focus on as simple an example as I can come up with. Okay, looks like I'm up to date with the notes, and thank you, Lester, for posting those links. I'm going to close that page. So that's the end of the iris example. That is arguably the simplest neural network you can think of designing. And you see that even though it's a simple example, there's still a lot of questions you have to ask and answer along the way. You have to think about structure of data, about tests and trained data splits. You've got to think about your loss functions and how you're going to repeat your data. You've got to think about your optimization functions. There's lots of choices you make along the way. But the first thing to think about or to remember in that situation is you don't always have to make those decisions up front. I'll say this again because I think it's worth reiterating. The best place to start with a network is what someone else has created before you. You can go online, you can find pre-designed and set up models in TensorFlow to solve a problem. You just import that code, show it your data, and see how it performs. That is going to get you a lot of the way there. By understanding what we've gone through today, that's going to give you the ability to tune and tweak what you're seeing to slowly start to understand how to apply it to your particular situation. So Thomas is asking why the validation accuracy didn't keep increasing as the loss decreased on the validation dataset. And that's because the accuracy is a coarse measure. It's measuring of all the samples, add up how many I got right and wrong, and give that as a fraction. The loss function, as Lester mentioned earlier, is differentiable. It is smooth, and so it can keep on increasing. And so while the accuracy wasn't going up, the degree to which it was sure about each of its answers would have kept on going up. It might have, once it got to that threshold, been saying, I've got the right answer, but I'm only 53% sure. By the end, it might have been saying, I've got that same answer, but now I'm 90% sure, for example. So that's why the loss can keep on improving, while the accuracy doesn't necessarily change. So I'm going to start covering this section here, and then we're going to have a break and come back through the last example. So this should only be maybe 10 minutes, and then we'll have a break. And so for this, we're going to go through some image analysis stuff, because we want to learn how we can apply neural networks to pictures, as well as how we can apply neural networks to plain old numbers. But before we can dive into applying neural networks to images, we need to understand how computers treat images, because images are more complex things than measurements made with a ruler. So the flip side of this is that pictures are also much easier to collect. It's much easier to go into your garden and take a photograph of a bunch of flowers than it is to go out with a ruler and measure all of their parameters. It also requires less skill, so you can collect larger data sets by using crowdsourcing and so on. So I'm going to go through now and explain how image analysis techniques work. So to get a sense from the class, could people just post in the chat what kind of experience you have with image analysis using kernels and convolutions and things like that? Is it completely new to you, or have you done some of this before? I'm assuming it's completely new to you, which is why I'm going to go through it all. I'm seeing lots of news and nuns. Wonderful. I'm sure there's going to be some people in the room who've done this before, and hopefully I'll be able to answer questions you have as well, but let's start right from the basics. So the idea of applying neural networks to pictures starts with the maths and computer science approach to dealing with pictures. And so the place you have to start, because we're going to be doing maths to this stuff, because neural networks at their core are multiplications and sums and function applications, we have to turn our picture into numbers. And we need a consistent way of representing images as numbers. And so I hope you're comfortable with the idea of taking a grayscale image, just a black and white image, and assigning for every pixel in that image a number. And that number represents how bright that pixel is. Commonly, these numbers are between 0 and 255. You've seen these sort of binary power of two numbers before. So a pixel being 255 would be completely white, and a pixel being 0 would be completely black. A number like 105 is slightly under halfway, so that's a darkish grey. In fact, all the numbers on this little snippet here are a darkish grey. The dots here are to represent that these pictures can be very large. The numbers we have here is only a 5x5 sample in the top left corner, but these pictures can be hundreds or thousands of pixels across in each dimension. Megapixels means millions of pixels, which means millions of numbers, which in our case corresponds to millions of input neurons. And that's a lot of data you need to deal with. So we have a grid of numbers. Sometimes people refer to these as matrices of numbers, but don't think of these as mathematical matrices as you might have done in school or undergrad. These are a grid. It's a grid of numbers and nothing more than that. So once we've got our grid of numbers, we need to describe some kind of mathematical process we can do to that grid. And the way this is commonly done is by using a technique called kernel convolution. And I'm going to explain the two parts of that term as I go through. So let's start with the first part, a kernel. Now a kernel in image analysis is another smaller grid of numbers. Usually they're 2x2, 3x3, 5x5, that kind of size. And they contain inside them a bunch of numbers. And the magic of kernel convolution is depending on which numbers you put inside that kernel, when you apply it to the image, and we'll see how it gets applied in a moment, when you apply it to the image, different things happen. So for example, these particular numbers here will sharpen the image. They'll make it less blurry. You might have come across the sharpen mask or the unsharp mask if you've played around in Photoshop or something like that. A different selection of numbers, with one which didn't have the negatives here, for example, would blur the image. You apply a particular small kernel to the image and it blurs it. This is how all image blurring works in any kind of computer sense. There's other kernels you can choose which do edge detection. And now edge detection is a very common computer vision technique for example, working out outlines of things, or it's also the core of what we're going to be seeing today. Now, you might be wondering, how can you know what particular numbers are going to give particular outputs? And that's because some clever mathematicians have done that work for us. They are all published and online. You just choose the one that does the job for you. If you want to blur the image, you go on the Wikipedia page, you find the blurring kernel, and you apply it. That's all you have to do. You don't have to think about what these numbers should do. Shreya asks, is it analogous to normalization? In a sense. So one of the things you might notice is that the sum of all of the numbers in here add up to 1. And so after applying this kernel, you expect it to have a sort of a normal effect. Normalization can be applied in lots of different ways. So there might not be an image kernel which can perform it, but it's going to be a similar technique that's going to be done to it. So the idea here is we have a set of predefined kernels designed by computer scientists and mathematicians, which have effects which we can describe with words. That's how these kernels are described. The next question then is, once we've got a kernel, how can we use it to do something to our image? And what we do is we take our image, which is here on the left-hand side. So you've got the purple section and the lighter blue out going into the distance. We take our kernel matrix. I say it's not really a matrix, it's just a grid. And we overlay it over those top 3 squares. Our kernel is 3x3, and so we overlay it over the top 3x3 grid. And then we kind of shine a light through it. We look at the top left number that's being shadowed and the top left number in the kernel matrix, We multiply those two numbers together, so 105 times 0. And then we add that to the next two pairs that are over top of each other. So 102 times minus 1, 100 times 0, and so on and so on. We add up all of those total numbers and we put that in where the middle of that kernel is currently sitting. So should we ask, why do we apply a kernel? That's a tricky question. So we apply a kernel because it has the effect that we want it to. We apply a kernel because, for example, we want to blur our image. And if we want to blur our image, we choose a blurring kernel and we apply it to the image and we end up with a blurred image. But at its core, all kernels work the same. Regardless of what the numbers in the kernel itself are, the process that's applied is the same. And if we change the numbers, the effect in the output image is also going to be different. It'll end up with a blurred image or a sharpened image or an image which represents where the edges are, for example. So to take that picture and kind of turn it on its side a little bit, we have the picture on the left-hand side, we have our kernel, and we've done 105 times 0, 102 times minus 1, 100 times 0, adding these up as I go, 103 times minus 1, etc. And so we see this in the sum at the bottom. We see that's the calculation that's done, and that gives us the number 89. And because this kernel was 3 by 3, and it was overlaid on the 3 by 3 purple area, the result of that calculation goes in the middle of the kernel. So the 99 gets replaced with an 89. So what we do after we've applied the kernel the first time is we shuffle it across by just one square, and we do the same thing again. So it's overlapping with the original one, but the middle of the kernel is now in the next space. So now we're going to do the same maths again, but we've got different numbers. So now the 103 gets mapped to a 111, for example. And we keep on doing that all the way along the row, and on the next row, and the next row, and the next row, filling up the whole image. Now what you might have noticed is that in that situation, you're not filling in the edge values at all. There's no way to represent what the number in the top left-hand corner should be, because 5 of the numbers in the kernel won't have corresponding image values to multiply against. And so we have to make a choice. How do we deal with that? And that's just a choice that we make. In our case here, we can decide to just pad the edges with zeros. That's perfectly valid. You get slightly weird effects at the edge of the image, but it's mathematically valid and it's consistent at least. Alternatively, we could pad the outside with a repeat of the value. So this top row would be, well, undefined, but then it would be 105, 102, 100, 97, 96, repeating above the actual image there. So depending on whether you want to zero pad or same pad, it gives you a choice about how you want to deal with this edge condition. You do this to an image by repeating that process over and over again. Obviously you use computer. If you use the right kernel, for example, there's a kernel that does Sobel edge detection. You start with the image on the left and you end up with the image on the right. Anywhere where the image is smooth, just stays black. Anywhere where there's a sharp change ends up white. So we've got an image now which shows where the edges are. And that's a useful thing to have because edges are often where interesting stuff happens in pictures. So we saw just before the break how, at its core, image analysis is done. Most image analysis algorithms have some element of kernel convolution being done to them. Now, the kernel is that little 3 by 3 matrix we saw, and the convolution part is the bit that applies it to the picture and gives some kind of result. So, in principle, it would be possible to take a whole bunch of kernels, really carefully design them such that you can show them to an image, one after another, layering them on top of each other to get some kind of answer. For example, you could start off with one kernel which does the edge detection. And then based on the result of that edge detection, you could have another kernel which says, are there two edges next to each other here? So they're parallel, at which point you say, okay, the result of this is a image which represents where parallel edges are. From that, you can have another kernel which looks for circles. And then based on that, you have another kernel which looks for circles next to each other. And you start building up these questions, getting more and more abstracted away from the picture, but more and more towards human concepts like, is this a person? And at its core, that's what convolutional neural networks are going to do. Now, I alluded before to the fact that kernels in convolutional image analysis are designed by mathematicians and computer scientists. And the example I just gave there, I said, if you choose your kernels really carefully, you can do such and such a thing. So what we're going to do is try and make those two things meet in the middle using neural networks. We're going to try and train a neural network to automatically discover what the values of the kernel should be. We are going to design brand new kernels and a whole slew of them. We're going to layer them on top of each other. And through the magic of the backpropagation stuff we saw before, this is going to give us an answer which can, based on a picture, say, is it a cat or a dog, for example. So the process is going to be the same. We're going to be showing it examples, checking how far away we are from the answer, doing the same backpropagation thing to the weights. But the difference here is that the weights in the network are going to be representing the values in the kernel. So going back to the previous section, this matrix here, for example, has got 9 values inside it. You can imagine in our network that we have a weight associated with each of these numbers. If this 0 was a different number, you can expect that the output of the network would be different, and therefore this number here, this weight, has an effect on the output, and therefore we can do the same thing we did before where we work out what the derivative of that is, and therefore work out how much this number in the top left of the kernel needs to be changed in order to make our answer more correct. So it's the same idea as before, but in this situation, the weights are the values inside the convolution kernels. The way we apply it ends up working exactly the same, and that's the beauty of convolutional neural networks, that the process is the same, but the way that you treat those weights and the way you apply those weights, you get a very different kind of idea. A convolutional neural network, or a CNN, is a classic example of a deep neural network. They're deep because we're going to need lots of layers. We need lots of layers because we need those layer levels of abstraction. We need to start at one end with, is there an edge here? Right at the other end to saying, is this a cat? There's lots of questions we have to ask along the way. Like, where are the ears with respect to the nose? What shape are the ears? How do you describe an ear? How do you find the edges that go into that? Where are those edges, etc. There's lots of questions you have to ask, and so you need lots of layers. In the situation where we're asking things about the location of something on an image with respect to the pixels around it on the image, we have to use what are called convolutional layers. Now, a convolutional layer doesn't connect every neuron in one layer with every neuron on the left, in the next layer. It only connects the neurons in one layer with the neurons in the next, which map to the same part of the image. So each neuron is representing a pixel, but you only connect the neuron on the output with the neurons that are near to it on the previous layer. As well as these convolutional layers, which are the layers that are basically doing this same convolutional kernel thing we saw before, just it's kind of encoded into a neural network language. We also have pooling layers. Now, a pooling layer is a much simpler thing. A pooling layer takes a picture, which is 1000 by 1000, and makes it smaller. So it takes 1000 by 1000 image, and for example, takes every 2 by 2 pixel and squidges it into a 1 by 1 pixel, and therefore it goes from being 1000 by 1000 into 500 by 500. And we do that because by applying convolutional layers and then pooling layers, we create layers of abstraction. So in the output, a particular neuron is having a larger area of effect on the earlier layers than it is on the later layers. And so you get global information as well as local information. The classic pooling algorithm is max pooling. So based on a 2 by 2 little grid, you find the largest of the 4 numbers inside there, and that's the number that survives and goes on to the next layer. And the third kind of layer we have in a CNN is the dense layers. Now, dense layers are the same stuff as we saw before. These are just the traditional neural network layers where everything's connected to everything and information just flows on through. So here we see an example of what this is doing. So we have an input image. This feature maps blob here, this is a layer. This is one layer of the neural network. Now that layer has a bunch of feature maps. Each of those feature maps is encoding a kernel being applied to the image. So by the first layer here, we've got, in this situation, 4 different kernels being applied to the input image. So if this input image was a 10 by 10 image, then in the output we'd have 4 10 by 10 images. And each of those feature maps would be representing a different thing. One of them might be looking for horizontal edges, one might be looking for vertical edges, one might be looking for dots that are by themselves. Who knows what they're actually looking for? The point is each of the feature maps are likely to be different. We then do this subsampling, this pooling layer. We make the thing smaller. We do some more convolutions to make more feature maps with different algorithms being applied to them. We then subsample again to get a whole bunch of smaller feature maps which have loads and loads of different pieces of information inside them. And at this point, we treat each of these last very, very small feature maps as inputs to a standard neural network like we had before. By this point, each of these can be represented as a single number. We just put them in as the input layer to a traditional neural network. So this is kind of in two halves. The first part is finding sort of a graphical and spatial information about where things are in the image. And then the second part takes where those things have been found and makes a decision based on that as to what the image is of. We can do some amazing stuff with convolutional neural networks, and I'm sure Lester's got some examples he might post as we go through these sections. One example I really like is image segmentation. So here you can train a network so that it can identify objects in the image, and it can overlay each pixel in that image with what kind of thing it is. And this is how some self-driving cars work. So it can identify that there's the car over here is a car and it's been outlined with blue. We've got the road, we've got the arrows on the road, we've got traffic lights, we've got all sorts of things. This is a convolutional neural network. Admittedly a complicated one, but nonetheless a convolutional neural network. You can also do things like style transfer. Now, style transfer is a really fun thing to Google for because since this example here, there's been much better examples, but this is a fun one nonetheless. You show it an example of a picture on the left-hand side by a particular artist. You can then add things into that image just based on photographs, and the network has learnt how this artist draws. And so it's able to draw the things you've added in the style of the artist. So you can end up with this McDonald's balloon being inserted right into a streetscape in New York in a style which looks consistent with the rest of the image. And in this case, the network has learnt how the artist draws. That's what the kernel convolutional layers are representing, in a very complicated way, nonetheless. And finally, again, apologies to any people who actually understand, this is approximately how animal vision works. So animal vision does largely work by looking for basic features. It looks for horizontal and vertical lines, simple patterns like that. Then it takes those simple features and your brain and your optical nerves and all this processing system in your head takes those things and consecutively applies more and more abstracted ideas on top of it until it ends up at the end with your brain able to identify this as a picture of a cat, for example. And most animal vision and brain systems work in a similar way to this, although, of course, because these are evolved and not designed, they are much more complex and complicated and also much cleverer in some ways. So that's what convolutional neural networks are and how they work. It is the same as we had before, but we design a network so that it can calculate what the weights of these kernels should be. And we're going to say, give me 60 different kernels. Work out what the weights in those kernels should be in order to answer this particular question. And through the magic of backpropagation, it's going to manage to do that. It really is quite amazing. The thing that convolutional neural networks are for is for images. That's at least 95% true. So if you've got image analysis, you almost always want a convolutional neural network of some kind. If you're using convolutional neural networks, it's almost always because you're dealing with images. They are designed for each other, effectively. So we have an example here where we're going to be dealing with this dataset called the MNIST dataset. It's again a classic dataset based on numbers, I think, written for automatic check processing in the US. This is a dataset which is freely available of 70,000 pictures of handwritten digits by all sorts of different people from the wild, from actual real people writing checks to people. Each picture is 28 by 28 pixels, so it's quite small, and that's useful for us because remember what I said before, that each pixel is going to end up being an input layer, and then we're going to be doing our feature maps, and so by starting with a small picture, you manage to keep your network under control. So we want to design a network where we can show it a picture, one of these examples, and it's going to say that's a 4, that's a 0, that's a 9. That's our task that we've got ahead of us. So we're going to go through a similar process that we did with the iris dataset. So again, feel free to click on this link here. It's going to take you to the Actually, that one takes you to my GitHub page, but at the end there'll be a link to the Colab where you can follow through the notes if you want to. So we're going to do the same things. We're going to specify the shape of the network, we're going to say how it should be trained, and we're going to specify our training data set. Same process before. This is the process you always go through with neural networks. So, designing the network. Now, we've had the question a few times about how do you know how many neurons, how many layers, how big the layer should be. This layout of this network is a standard layout of a network for an image classification problem. If you've got a relatively simple image classification problem, this layout of a network is going to do a decent job. As long as you haven't got 10,000 different categories, as long as you're not trying to identify multiple objects in one image, things like that, then this is going to do a good job of classifying the images. And the way it works is by starting with a convolutional layer. Now this is going to describe and design 16 different filters. Each filter is going to be a 5x5 kernel. So a filter and a kernel, its terminology means the same thing. So you have 16 different kernels. Each of them are going to be 5x5. And it's going to make a new layer, which is therefore the same size as the input, but that has had this layer, this kernel applied to it. But it's going to do that 16 times, all in parallel. So if we had 10 input neurons, we're going to have 160 neurons in the first layer. We've actually got 28 by 28 input neurons, and so we're going to end up with 28 times 28 times 16 neurons in the next layer, or objects in the next layer. Then we have a pooling layer, which makes our image half the size, so it goes from 28 by 28 to 14 by 14, and then another convolutional layer and another pooling layer. So you do convolution pooling, convolution, and pooling. That's a common sort of technique you get. So you've got 2 layers of abstraction over the spatial information in the image. Then we finish off with a dense layer, which combines together all of the outputs of the convolutions and tries to sort of ask the questions about how those different features that it's discovered relate to each other. In the same way as we were evaluating how the 4 different features of the iris flowers related to each other to give us the answer that we wanted. The final output is the 10 neurons, which represent 1 for each digit. So is it a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9? There's 10 possible categories, so we have 10 neurons in the final image. In the iris example, we had 3 categories, and so we had 3 neurons in the final image. There's some details in here, but I'm going to go through that as we go through. So this structure works really well for MNIST. MNIST is a simpler problem. You could get away with a smaller network for MNIST, but this is a nice generalizable classification network. So you can use this in your work if you were doing classification stuff. So we're going to do the same things we did before. We're going to build up our network. We're using Keras, and we're going to use a sequential thing, which means we're going to pass a list of layers. They're going to start from the input and work their way through. So the first layer is a convolutional layer. It's 2-dimensional, so it understands, sort of built into these functions is the understanding of what images are and how they relate. It's kind of wrapping that stuff up for us. So all we have to tell it is that we want 16 different kernels, 16 different filters. Each filter should be a 5x5. There was that thing before where at the edge we had to decide, are we going to pad it with zeros or pad it with the same number? Here we tell it that we need to pad with the same. And then again, because this is eventually actually doing a mathematical operation of some kind, we have to have an activation function. And like before, we use our ReLU function, and that does the job well. It lets us represent our non-linearity in our model. So we have 16 5x5 filters. The layer will be 28 by 28, but we've got 16 filters. So the overall size of this layer is now 12,500. So we now have 12,500 neurons in our next layer. So a lot of neurons, and each of those are going to have a whole bunch of weights. They're each going to have 25 weights. A lot of numbers to deal with already, as you can see. But nothing that modern computers can't handle. We then, into this list here, we add a pooling layer. And I've pulled it out as a variable here because we're going to be repeating this in a little bit. And all we say here is we want a 2x2 pooling, so it's going to make our image half as big in every direction. And this one here is saying how much do you want to jump along by each time. And the same here is the same padding as we had before. So we've now shrunk this down. Instead of being 28 by 28 by 16, it's now 14 by 14 by 16. So we've only got 3,000 neurons in the next layer. Then we do the same dance again. We have another convolutional layer and another pooling layer. So remember, we have convolution pool, convolution pool. Same bit of code. Only difference is that this time we have more filters. We've more abstracted away, so we're further away from the original image, but we want to be able to represent more different types of things we're looking for. Particular curls and curves in the handwriting of the original image is what this layer here is going to represent. The first convolutional layer is going to represent more things to do with where the lines are and if there's two lines next to each other. This part here is going to be describing more precisely where different circles and curves and spaces are in the image as a whole. And you see this number here is again getting smaller. The layers are getting smaller as we go because we are abstracting away the information. We are reducing down our phase space. So we may ask, each neuron will have a different kernel. So it's a bit more complex than I was making out. There won't be the thing times 25. I misspoke when I said that. Each of the filters, each of the 16 or 32 filters will have a 5x5 filter associated with it. So there'll be 32 5x5 filters, and therefore there'll be that many weights. So some of the weights are going to be sort of correlated with each other in some ways. So it reduces the total number of weights you're actually having to analyse, which is helpful. Then we have our same thing as we had before. This is the same as we had in the iris. We have a dense layer. Now a dense layer means connect everything to everything. 128 neurons, so this is a number chosen which is big enough to be able to represent the variation in the images, but small enough that it's going to be able to train quickly. We end with a dense layer with 10 neurons, and we have this softmax thing again to turn it into probabilities. The only tricky part in all of this is this layer in here, which I didn't mention before, called dropout layer. And what a dropout layer does is not actually a layer of neurons per se, it's simply a thing that gets applied to the process. And what this layer does is, as the network is training, once after each set of examples, it will randomly delete 40% of the connections. It won't set the weights to 0, it just, for this example, will not use those inputs on the training. And this is used to avoid overfitting. It spreads around the information, stops you getting stuck in local minima, and makes sure you end up with a more generalized model. So you're artificially snipping connections and then reconnecting them next time, so that no one connection becomes too powerful and too important. So this dropout thing is often used to smooth the network out and allow it to be more general. This bit of code here is exactly the same as we had last time. We're doing the same classification task. We are trying to put things into, is it this thing, this thing, this thing, or this thing? Is it one of these flowers? Is it one of these numbers? Same optimizers as before, and the same metrics. So we are doing the same task as last time. The way that it works, the way the network is training is the same. This is one of the nice things, that once you've done this a few times, you start seeing the commonalities, and you stop having to worry about how you should make these decisions, because you just use the same stuff as last time, which makes your life a lot easier. So as I said before, if you're doing a classification problem, and the labels are the integer index of the class that you want to get to, then sparse categorical cross entropy is the TensorFlow solution to your problem. Use that one and you're going to be fine. There's also a sparse, I think, binary cross entropy if you want to have a yes-no answer at the end, rather than a, is it one of these 10, 20 categories. We've designed our network and we've said how it's going to be trained. The order is a little bit different this time. We are going to load in our data. And for this, TensorFlow comes with a TensorFlow dataset function, which gives us our MNIST data. It splits it into test and train for us. It shuffles it for us. It does all the magic, well, much of the magic automatically for us. So after this function's been called, dstrain and dstest, that's our test and train dataset, they are both sequences of 128 by 128 by 1 matrices. So it's a 3D matrix, but one of the dimensions is only one big because it's only got grey, it's not red, green, and blue. And the values in each of those are the numbers from 0 to 255, so the same as we were seeing before. There's a few things we do have to do to that data to make it suitable for our network to train. One of them is that in most networks, you end up working best if you have numbers between 0 and 1 rather than numbers between 0 and 255. So we apply a function which divides every pixel by 255 and make sure it's a floating point number. So that just turns them from 0 to 255 into 0 to 1. Then we do the same thing before, we cache it and shuffle it and this kind of stuff. Details here don't matter too much. This is just the process it's going through to get stuff in the right shape. You would start, if you were doing this for yourself, you'd start with these things and you play around with them and read the documentation and see where it takes you from there. You then do the same thing to the test data set, but simpler. You need to normalize it, but you don't have to do all the shuffling and stuff. Like we had last time, the test data set analysis is a simpler process. And then we call the fitting. Same as before, we call the fit function and we give it the training data. We're not giving the validation data this time because we do underneath. So the same process before, but we're only going to do it through once. So this notebook that I've got here on the screen, that is exactly the same code as I've just gone through. We set up the data, we shuffle it all, we do the normalization, add all our layers together, and call the fitting. And you'll see here, after the end of the fitting step, the accuracy on the training data set is 94%, and the accuracy on the validation data set is 98%. So those are both large, but it's got there very, very quickly. With only one epoch, it's already got a very good accuracy. If we kept on training, it could increase further, but that would be something to have a play around with after the session. These Colab notebooks will stay up for as long as you need them to. The last thing we get printed out, and I want to switch back to the notes for this, is a table of predictions on certain images and what it thinks they are. So let's have a look at what it looks like. This is a good example. Training networks can take a long time sometimes, so it's a good excuse to pretend you're working while your computer's doing all the hard work for you. But it gives you a table that looks something like this. It's got an image which is a number 1. It thinks it's a 3 because it's got it wrong. We've given it a picture of a number 2. Oh, it got that one right. It thinks it's a 2. I'm not going to go on any further because it's a bad way to look at data. This is a much better way to look at data. So in this table here, down the left-hand side, we have a bunch of images which, once our network has finished training, we are showing to the network and saying, what do you think of this? Can you get anywhere with this kind of image? And we'll see that it's done some of them quite well, but many of them it's done a terrible job at. And this is on purpose. We're going to get to solving this in a moment. This isn't just a demonstration of how bad your networks are. It is, however, a demonstration of how you've got to be careful about the difference between the data you train your network on and the data you apply it to. So the data we had up at the beginning was all 28 by 28 pictures, which were white ink on a black background. Now the only one that's white ink on a black background is number 5, and it's got that one successfully correct. But the other images are mostly from a different source. They're not handwritten, they're different, they're inverted contrast, things like that. And some of them it's got right, but many of them it's got wrong. So we've trained a network to identify white on black handwritten digits, and it doesn't really behave well outside of that. It gives an answer, but it doesn't always give you the right answer, so it's not reliable. I would also, importantly, draw your attention to the very last row. There we have that little dog we saw earlier. So if we put a picture of a dog into this network, it's going to give us back an answer. It's not going to say none of the above. It's going to say its best guess is that this looks like a number 2. Maybe its nose has got the right kind of curve to it or something. And so this is something you really need to be aware of. You need to make sure that when you're training your network, it's being trained on the kind of data that it's going to be applied to. There's a classic example, which was mentioned in the course yesterday, which I'm just going to post a picture to. Came up recently, and this is the COVID cat, where a similar kind of situation, network trained to look for COVID-19. If you show it a cat, a bunch of the networks say that yes, that's definitely got COVID. And even though they have no information really about what's going on inside, they were trained on one thing and they are making spurious guesses about data outside of that. So you have to be careful about the data you train it on and the environment in which you apply your network. Think about how general or not general it is. Jan asks, is there a way to get a none of it answer? With some networks, you can have a go with that, and that's what the writers of the publishers of that COVID cat image have tried to do. They've got a none of it example. You've got to be quite careful about what you consider to be none of it and how that blends in with the categories you do care about. It's a tricky problem to solve. The important thing to do is think about it from the beginning. Think about the scope of data you're training on and think about how that relates to the data that you're going to be using the network on. Regardless, it's giving an answer for every single thing. It's always going to tell us something, and that's a common problem in machine learning. Machine learning doesn't tend to be well designed to give you an I don't know answer. It's a hard problem to solve. But we can, in this situation, for these numbers, do an attempt to improve that domain that we care about. And I think the main difference between the numbers that worked well and those that didn't is that this was white on black and these were black on white. The answer to this is doing something called data augmentation. Basically adding in more training data to represent a larger range of possibilities so the network learns a more general model of what the world looks like. If you're doing something to identify dogs, you don't just want really nice framed dogs made with a good camera. You want pictures of dogs made with really bad cameras in dark conditions, in snowy conditions, all these different things. You want to have all of those so the network can learn the full scope of the world. In our case, we've got some white on black images, so we want to just put in some black on white images as well, and that's hopefully going to make it able to understand the full scope of handwritten digits. In general, you're going to want to do data augmentation on any network. It's a really, really powerful thing to do. If you can't collect more data, then fake it by blurring, rotating, scaling the data that you do have. In our case, we are going to invert the images. We're going to take our original data set and we're going to add onto it the same data set again, but with black turned into white and white turned into black. So we multiply it by -1 and then add 1 to it. So that turns 1 to 0 and 0 into 1. And 0.5 stays the same. So let's have a go and see what effect that has. So go back to that notebook, and at the very top, in the top cell, I made it super easy for you. There's a variable that says invert equals false. Change that into invert equals true and go to runtime run all again and see what effect that has on it. You do need to run all the cells again. So make sure it's true with a capital T because that's what Python expects. Then runtime run all. While that's running, Mia says this raises the issue of implicit bias. Absolutely, and this is something I'm going to cover on my very last slide about being careful about the kind of things you train on and the kinds of questions that you're asking your computer to answer. It's not as simple as throw the numbers in and get a number out. You have to think about the human in the loop, for example. So that's all run through. It's currently fitting. It's finished, and it's doing the analysis. And this is, again, going to print out our table of results, and I'm going to skip that table of results and show you it in a better format. Umeya asks how to evaluate bias of a network. Well, it depends on what kind of bias you're talking about. One of the primary biases you get is sort of a selection bias, where you've only trained your network on a subset of data, and so it's only going to know things about that subset of data, or sampling bias as well, I suppose it could be as well. So the way to do that is to try using your network on data that represents where it's actually going to be used and make sure it's performing well on that whole set. But we see here it's worked well. Simply by showing it inverted color images, it's able to generalize well across data which wasn't even part of the original data set. The number 1 is an inverted image, but 2, 3, and 4 are computer-generated numbers. They are, printed to the screen. They aren't handwritten. But it's still able to recognize them. We trained it on handwriting. It can recognize non-handwriting, which is perhaps surprising, and it's not something you should rely on. We should add into our training examples like these if we want it to perform well. We see here, however, that it is performing reliably on these examples. It's not only saying that there's a high probability of it being a 2, it's saying there's a low probability of it being anything else. And that's a useful thing to see. All the way through, it's doing very well. 97% is one of the lowest. We get 71% there, probably because of the low contrast on the number 1. So we want to add in maybe some more images with washed out colours, and that's going to help the training. The number 9 here isn't handwritten or computer generated. There's noise around the edge because this is actually a photograph of someone's door number, and so it does a bad job. It thinks it's a 0 because it's getting confused. Again, if we want it to recognise door numbers, we need to train it on door numbers. Once again, we see that the dog has given us a wrong answer. You see that the probabilities are better spread out, so you might not in this situation say, well, 23 is the highest, and so therefore it's a number 8. You might want to say, none of them stand more than a certain amount amongst their peers, and therefore it's an I don't know. That's one of the ways you can say, I don't know, because there's no one conclusive answer. But it's up to you to think about the thresholds and the statistics and the probabilities of these things to make a decision about where that threshold should be put. But this hopefully shows you the power of data augmentation, the stuff that you can do just by using the same data, tweaking it a bit, adding it into the mix. You suddenly get a network which is way more powerful and way more general. So in summary, these are the things you need to think about when you're training the data. So here we had, on our previous example, we had the number 9, the door number. It doesn't represent the training data set. So if we want it to, we need to get some pictures that do. We need to add them in. If we want to make our network perform better, we want to do more data augmentation. We may want to rotate images around or flip them or blur them or change the colors or delete parts of them. You mess around with them to represent lossy data and hope that the lossy data we apply is a good approximation of the kind of lossiness that exists in reality. If you can, get a larger base training data set. If you can't, if you want to do the best job, then getting more actual data, collecting real data is going to do the best job. If you can go out and collect more photographs and get more pictures of handwriting, that is going to help you a lot. If you can't get real data, then data augmentation is going to help on top of that. If it's taking a while to give you a good network, then just train it for longer. You can, in general, keep on training and it will keep on getting better. But bear in mind, keep an eye on the validation accuracy and the loss to make sure that it's not overfitting against the training dataset. The more data you have that you're training on, the less likely it is to overfit as well. So that's also a benefit you get. And also there's loads of numbers that we've included in this process. The batch size, the learning rates, the dropouts, the kernel size, all these things we put in there. Play around with those numbers, make your network larger or smaller, see how they affect things, and understand the effect that they have on your eventual result. So the last thing I want to talk about is something which comes up a lot when you're talking about machine learning. And I think in a research context, it's very important as well, because as researchers, we have a sort of responsibility to be honest and good about how we're approaching things. Now, machine learning and neural networks in particular do have a bit of this black box problem. You put numbers in, you do an algorithm, you get a number out, and it always gives you some kind of answer. And it's very easy to end up in a computer says no situation here, where you're creating a network to decide whether someone is deserving of getting a loan, for example. So you put in the description of them to do with their socioeconomic background and where they live and what their income is. And it gives a number like yes or no, a result like yes or no. And you don't have any recourse there. It's just a machine giving you an answer. So you need to think about, is that an appropriate thing to do as a society? But inevitably, machine learning is becoming more important. It's taking over everything. It's cropping up all over the place. And so you need to think about how you can do this stuff in an honest way. Now, Google have a set of AI principles, and I've grabbed the few of them from here. I also wouldn't say that necessarily Google follow their own AI principles, but it's nice to see them written down somewhere, and we can choose to follow them. So the first thing, I think one really useful for researchers, especially those that are publicly funded, is to be socially beneficial. Don't design a neural network which is going to not give loans to people of colour, or that's going to make a missile kill someone, or anything like this. Design stuff that is going to be good. Be good people. Be nice. Be helpful. Avoid creating or reinforcing unfair bias. There's a classic example with the Microsoft Kinect, their Xbox controller, where they designed some machine learning and networks to be able to identify people standing in positions so they can dance around and control the machine. When they took it on tour to all the game shows, people from the public were coming along and having a go, and it wasn't seeing them. It wasn't seeing their faces. And it turned out it was doing a bad job of seeing them because they hadn't trained the networks on people with a diverse set of skin colours. They trained it on the people who were the engineers at that particular group in the company, and they were mostly white, and they'd failed to identify the broad spectrum of people that would be using the technology. And that is an unfair bias, for sure. Make sure stuff's designed for safety, so have things which fail safely. If it's unsure about something, err on the side of asking a human and including people in the loop as well. Make sure you don't fall on the side of, I'm not sure, so let's not give them a loan and, subject them to a lifetime of misery or whatever. Think about how it's going to be affecting the humans in the process. Be private with things. It's easy when you're designing a network to accidentally have the eventual network containing personal information. You might have a weight in there which accidentally represents the age of a particular person you've trained it on. And there are techniques, statistical techniques, which you can use to extract that out. So be really careful about the data that you're training it on and how you're going to incorporate privacy into that. And as many of us are researchers or scientists, uphold high standards of scientific excellence. This means be honest about how you're training your data set. Be honest about the testing you've done on it. Make sure you honestly split your test and training data sets. Make sure you've analysed the results in a thorough and comprehensive way. Be good citizens and be good scientists is a big summary coming out of this. But that's the end of the session today. Thank you all for your attention. I know it's a lot of information in 3 hours, and I really appreciate all the brilliant questions we've had. So thank you all very much, and I hopefully will see you again soon.